Hello everyone, welcome to Simplilearn's YouTube channel. We are stepping into a new year with new resolutions. Resolutions of mastering a new technology and getting ahead and much more. So we have conducted a survey and got a list of top trending IT jobs in the current IT industry. This week, we will help you learn about all those interesting technologies and get ahead and be future ready by 2022. On day 1, we will be learning about the artificial intelligence and machine learning. Artificial intelligence and machine learning have been in the industry for many years, but the buzzword started to skyrocket in the recent years due to the evolution of business intelligence and data analytics. Organizations worldwide are incorporating artificial intelligence and machine learning to automate their operations and elevate productivity. Recent surveys prove the technology's potential in the future and also finds a huge demand for the professionals with the knowledge of AI and ML. In today's session, our real-time industry experts will take you through the end-to-end AI and ML tutorial with real-time examples for better understanding. So without further ado, over to our experts.
So we will start off by learning the basics of AI and machine learning from short animated videos. Then we will understand the different supervised and unsupervised learning algorithms such as linear regression, logistic regression, decision trees, SVM, KNN, as well as k-means clustering. Then we will shift our focus towards learning deep learning, where we will look at what is deep learning and how neural networks work. We will also cover two important deep learning frameworks, TensorFlow and Keras. Finally, we will understand about generative adversarial network and recurrent neural networks. So let's get started.
Picture this, a machine that could organize your cupboard just as you like it, or serve every member of the house a customized cup of coffee. Makes your day easier, doesn't it? These are the products of artificial intelligence. But why use the term artificial intelligence? Well, these machines are artificially incorporated with human-like intelligence to perform tasks as we do. This intelligence is built using complex algorithms and mathematical functions. But AI may not be as obvious as in the previous examples. In fact, AI is used in smartphones, cars, social media feeds, video games, banking, surveillance, and many other aspects of our daily life. The real question is, what does an AI do at its core? Here is a robot we built in our lab, which is now dropped onto a field. In spite of a variation in lighting, landscape, and dimensions of the field, the AI robot must perform as expected. This ability to react appropriately to a new situation is called generalized learning. The robot is now at a crossroad, one that is paved and the other rocky. The robot must determine which path to take based on the circumstances. This portrays the robot's reasoning ability. After a short stroll, the robot now encounters a stream that it cannot swim across. Using the plank provided as an input, the robot is able to cross this stream. So, our robot uses the given input and finds the solution for a problem. This is problem solving. These three capabilities make the robot artificially intelligent. In short, AI provides machines with the capability to adapt, reason, and provide solutions. Well, now that we know what AI is, let's have a look at the two broad categories an AI is classified into. Weak AI, also called narrow AI, focuses solely on one task. For example, AlphaGo is a maestro of the game Go, but you can't expect it to be even remotely good at chess. This makes AlphaGo a weak AI. You might say Alexa is definitely not a weak AI, since it can perform multiple tasks. Well, that's not really true. When you ask Alexa to play Despacito, it picks up the keywords play and Despacito and runs a program it is trained to. Alexa cannot respond to a question it isn't trained to answer. For instance, try asking Alexa the status of traffic from work to home. Alexa cannot provide you this information, as she is not trained to. And that brings us to our second category of AI, strong AI. Now, this is much like the robots that only exist in fiction as of now. Ultron from Avengers is an ideal example of a strong AI. That's because it's self-aware and eventually even develops emotions. This makes the AI's response unpredictable. You must be wondering, well, how is artificial intelligence different from machine learning and deep learning? We saw what AI is. Machine learning is a technique to achieve AI, and deep learning, in turn, is a subset of machine learning. Machine learning provides a machine with the capability to learn from data and experience through algorithms. Deep learning does this learning through ways inspired by the human brain. This means through deep learning, data and patterns can be better perceived. Ray Kurzweil, a well-known futurist, predicts that by the year 2045, we would have robots as smart as humans. This is called the point of singularity. Well, that's not all. In fact, Elon Musk predicts that the human mind and body will be enhanced by AI implants, which would make us partly cyborgs. So, here's a question for you. Which of the below AI projects don't exist yet? A. An AI robot with citizenship. B. A robot with a muscular skeletal system. C. AI that can read its owner's emotions. D. AI that develops emotions over time. Give it a thought and leave your answers in the comment section below. Since the human brain is still a mystery, it's no surprise that AI too has a lot of unventured domains. For now, AI is built to work with humans and make our tasks easier. However, with the maturation of technology, we can only wait and watch what the future of AI holds for us. Well, that is artificial intelligence for you in short.
We know humans learn from their past experiences, and machines follow instructions given by humans. But what if humans can train the machines to learn from their past data and do what humans can do and much faster? Well, that's called machine learning. But it's a lot more than just learning. It's also about understanding and reasoning. So today, we will learn about the basics of machine learning. So that's Paul. He loves listening to new songs. He either likes them or dislikes them. Paul decides this on the basis of the song's tempo, genre, intensity, and the gender of voice. For simplicity, let's just use tempo and intensity for now. So here, tempo is on the x-axis, ranging from relaxed to fast, whereas intensity is on the y-axis, ranging from light to soaring. We see that Paul likes the song with fast tempo and soaring intensity, while he dislikes the song with relaxed tempo and light intensity. So now we know Paul's choices. Let's say Paul listens to a new song. Let's name it as Song A. Song A has fast tempo and a soaring intensity, so it lies somewhere here. Looking at the data, can you guess whether Paul will like the song or not? Correct. So Paul likes this song. By looking at Paul's past choices, we were able to classify the unknown song very easily, right? Let's say now Paul listens to a new song. Let's label it as Song B. So Song B lies somewhere here with medium tempo and medium intensity. Neither relaxed nor fast, neither light nor soaring. Now can you guess whether Paul likes it or not? Not able to guess whether Paul will like it or dislike it? Are the choices unclear? Correct. We could easily classify Song A. But when the choice became complicated, as in the case of Song B, yes, and that's where machine learning comes in. Let's see how. In the same example, for Song B, if we draw a circle around the Song B, we see that there are 4 votes for like, whereas 1 vote for dislike. If we go for the majority votes, we can say that Paul will definitely like the song. That's all. This was a basic machine learning algorithm also. It's called k-nearest neighbors. So this is just a small example in one of the many machine learning algorithms. Quite easy, right? Believe me, it is. But what happens when the choices become complicated, as in the case of Song B? That's when machine learning comes in. It learns the data, builds the prediction model, and when the new data point comes in, it can easily predict for it. More the data, better the model, higher will be the accuracy. There are many ways in which the machine learns. It could be either supervised learning, unsupervised learning, or reinforcement learning. Let's first quickly understand supervised learning. Suppose your friend gives you 1 million coins of 3 different currencies, say 1 rupee, 1 euro and 1 dirham. Each coin has different weights. For example, a coin of 1 rupee weighs 3 grams, 1 euro weighs 7 grams and 1 dirham weighs 4 grams. Your model will predict the currency of the coin. Here, your weight becomes the feature of coins, while currency becomes their label. When you feed this data to the machine learning model, it learns which feature is associated with which label. For example, it will learn that if a coin is of 3 grams, it will be a 1 rupee coin. Let's give a new coin to the machine. On the basis of the weight of the new coin, your model will predict the currency. Hence, supervised learning uses labeled data to train the model. Here the machine knew the features of the object and also the labels associated with those features. On this note, let's move to unsupervised learning and see the difference. Suppose you have cricket dataset of various players with their respective scores and wickets taken. When we feed this dataset to the machine identifies the pattern of player performance. So it plots this data with the respective wickets on the x-axis while runs on the y-axis. While looking at the data, you will clearly see that there are 2 clusters. The one cluster are the players who scored high runs and took less wickets, while the other cluster is of the players who scored less runs but took many wickets. So here we interpret these 2 clusters as batsmen and bowlers. The important point to note here is that there were no labels of batsmen and bowlers. Hence, the learning with unlabeled data is unsupervised learning. So we saw supervised learning where the data was labeled and the unsupervised learning where the data was unlabeled. And then there is reinforcement learning, which is reward-based learning, or we can say that it works on the principle of feedback. Here, let's say you provide the system with an image of a dog and ask it to identify it. The system identifies it as a cat. So you give a negative feedback to the machine saying that it's a dog's image. The machine will learn from the feedback, and finally if it comes across any other image of a dog, it will be able to classify it correctly. That is reinforcement learning. To generalize machine learning model, let's see a flowchart. Input is given to a machine learning model, which then gives the output according to the algorithm applied. If it's right, we take the output as our final result. Else, we provide feedback to the training model and ask it to predict until it learns. I hope you've understood supervised and unsupervised learning. So let's have a quick quiz. You have to determine whether the given scenarios uses supervised or unsupervised learning. Simple, right? Scenario 1. Facebook recognizes your friend in a picture from an album of tagged photographs. Scenario 2. Netflix recommends new movies based on someone's past movie choices. Scenario 3. Analyzing bank data for suspicious transactions and flagging the fraud transactions. Think wisely and comment below your answers. Moving on, don't you sometimes wonder, how is machine learning possible in today's era? Well, that's because today we have humongous data available. Everybody is online, either making a transaction or just surfing the internet, and that's generating a huge amount of data every minute. And that data, my friend, is the key to analysis. Also, the memory handling capabilities of computers have largely increased, which helps them to process such a huge amount of data at hand without any delay. And yes, computers now have great computational powers. So there are a lot of applications of machine learning out there. To name a few, machine learning is used in healthcare, where diagnostics are predicted for doctors' review. The sentiment analysis that the tech giants are doing on social media is another interesting application of machine learning. Fraud detection in the finance sector, and also to predict customer churn in the e-commerce sector. While booking a cab, you must have encountered surge pricing often, where it says the fare of your trip has been updated. Continue booking? Yes, please, I'm getting late for office. Well, that's an interesting machine learning model which is used by global taxi giant Uber and others, where they have differential pricing in real time based on demand, the number of cars available, bad weather, rush hour, etc. So they use the surge pricing model to ensure that those who need a cab can get one. Also, it uses predictive modeling to predict where the demand will be high, with the goal that drivers can take care of the demand and surge pricing can be minimized. Great! Hey Siri, can you remind me to book a cab at 6 p.m. today?
Okay, I'll remind you.
Thanks!
No problem.
Comment below some interesting everyday examples around you where machines are learning and doing amazing jobs. So that's all for machine learning basics today from my side.
Welcome to Artificial Intelligence Tutorial. What's in it for you today? What is artificial intelligence? So we'll start with a general concept. Types of artificial intelligence, covering the 4 main areas. Ways of achieving artificial intelligence. And some general applications of artificial intelligence in today's world. Finally, we'll dive into a use case predicting if a person has diabetes or not. And we'll be using TensorFlow for that in the Python environment. What is artificial intelligence? In today's world, it's probably one of the most exciting advancements that we're in the middle of experiencing as humans. So, what is artificial intelligence? And here we have a robot with nice little clampy hands. Hey, what am I? You are what we call artificial intelligence. I am your creator, reminding him who programmed him and who he's supposed to take care of. Artificial intelligence is a branch of computer science dedicated to creating intelligent machines that work and react like humans. In today's place where we're at with artificial intelligence, I really want to highlight the fact that they work and react like humans, because that is where the development of artificial intelligence is, and that's what we're comparing it to, is how it looks like next to a human. Thanks. Any tasks you want me to do for you? Get me a cup of coffee? Poof, here you go. And he brings him a cup of coffee. That's my kind of robot. I love my coffee in the morning. You'll see there's kind of a side theme of coffee today's tutorial. So here we have a robot that's able to bring him a cup of coffee. Seems pretty far out there, that we have a walking robot that's doing this, but it's not as far out there as you think. We have automatic coffee pots. We have devices that can move an object from one point to the other. Anything from Amazon delivering packages or whatever you want. All these things are in today's world. We're right on the edge of all this. That's what makes this so exciting, such an exciting topic and a place of study. So let's take a real general look at types of artificial intelligence in the really big picture. When we drill into it, there's like machine learning and all kinds of different aspects, but just a generic level of artificial intelligence. So, hi there, discovered 4 different types. Come have a look. So we have our kind of Einstein-looking guy or professor at some college. So the very first part that this is reactive machines. They've been around a long time. This kind of AI are purely reactive and do not hold the ability to form memories or use past experiences to make decisions. These machines are designed to do specific jobs. Remember I talked about the programmable coffee maker that makes coffee in the morning? It doesn't remember yesterday from tomorrow. It runs its program. Even to our washing machines, they have automatic load balancers that have been around for decades. So reactive machines, we program to do certain tasks, and they have no memory, but they're very functional. Then we have limited memory. And this is kind of right where we're at right now. This kind of AI uses past experience and the present data to make a decision. Self-driving cars are kind of limited memory AI. We bring up self-driving cars because that's a big thing, especially in today's market. They have all these images that they brought in and videos of what's gone on before, and they use that to teach the automatic car what to do. So it's based on a limited memory. Limited memory means it's not evolving new ideas. They have to actually, when they need to make a change, they have the program built on the memory, but then they have to make those changes outside of that and then put the new setup in there. So it's continually reprogramming itself. Theory of mind. These AI machines can socialize and understand human emotions. Machines with such abilities are yet to be developed. Of course, that's under debate because there's a lot of places that are working on the theory of mind and having it be able to cognitively understand somebody based on the environment, their facial features, all kinds of things, and evolve with them. So they have some kind of reflective ability to evolve with that. And finally, self-awareness. This is the future of AI. These machines will be super intelligent, sentient, and conscious. So they'll be able to react very much like a human being, although they'll have their own flavor, I'm sure. Achieving artificial intelligence. So how in today's world right now are we going to achieve artificial intelligence? Well, the main arena right now is machine learning. Machine learning provides artificial intelligence with the ability to learn. This is achieved by using algorithms to discover patterns and generate insights from the data they are exposed to. And here we have a computer as we get more and more to the human realm of artificial intelligence. You see this guy splits in two and he's inside his hidden networks and machine learning programs. Deep learning, which is a subcategory of machine learning. Deep learning provides artificial intelligence the ability to mimic a human brain's neural network. It can make sense of patterns, noise, and sources of confusion in the data. Let's try to segregate different kinds of photos using deep learning. So first we have our pile of photographs, much more organized than my boxes in my closet of photographs. The machine goes through the features of every photo to distinguish them. This is called feature extraction. Bingo, it figures out the different features in the photos. And so based on those different features, labels the photos, it says these are landscapes, these are portraits, these are others. So it separates them in there. And if you've ever been on Google Photos, a favorite of mine, I go through there and I type in dog and I get all the images of my dog. It's pretty amazing how it's able to pull those features out. So when we're achieving artificial intelligence and the deep learning, let's take a closer look and see just how deep learning works. There are a lot of models out there. This is the most basic model used. This is a neural network. There are 3 main layers in a neural network. The photos that we want to segregate go into the input layer. And so we have a picture of Mona Lisa, it looks like, and a couple of people. When it goes into the first input layer, the arrows are drawn to like individual dots. Each one of those white dots in the yellow layer or in the input layer would be a pixel in the picture, maybe, a value for that pixel. So the picture of the mountains goes in there and it fills in that whole input layer. And then the next picture of the nightscape goes in there. The hidden layers are responsible for all the mathematical computations or feature extraction on our inputs. So when you see here, we have the 2 kind of orangish red layers here, and there's all these lines in there. Those lines are the weights. Each one of those represents usually a float number or a decimal number. And then it multiplies it by the value in the input layer. And you'll see that as it adds all these up in the hidden layer, each one of those dots in the hidden layer then has a value based on the sum of the weights. And then it takes those and it puts it into another hidden layer. And you might ask, well, why do we have multiple hidden layers? Well, the hidden layers function as different alternatives to some degree. So the more hidden layers you have, the more complex the data that goes in and what they can produce coming out. The accuracy of the predicted output generally depends on the number of hidden layers we have. So there we go. The accuracy is based on how many hidden layers we have. And again, it has to do with how complex the data is going in. The output layer gives us the segregated photos. So once it adds up all these weights, and you'll see there's weights also going into the output layer, based on those weights, it'll say, yes, it's a portrait, no, it's a portrait. Yes, it's a landscape, no, it's a landscape. And that's how we get our setup in there. So now we were able to label our photos. Let's take a look and see what that looks like in another domain. We have photograph domain. Now let's look at it in the airline ticket. So let's predict the airline ticket prices using machine learning. These are the factors based on which we're going to make the predictions. And choosing your factors is so important. But for right here, we'll just go ahead and take a look at what we got. We have airlines, we have the origin airport, the destination airport, the departure date. Here are some historical data of ticket prices to train the machine. So we pull in the old data. This is what's happened over the years. Now that our machine is trained, let's give it new data for which it will predict the prices. And if you remember from our 4 different kinds of machines, we have machines with memory. Well, this is the memory part. It remembers all the old data and then it compares what you put in to produce the new data, to predict the new prices. The price is $1,000. That's an expensive flight. Of course, if that is US dollars, if it's India, I don't know what the price range is on that. Hopefully it's a good deal for wherever you're going. So we predict the prices, and this is kind of nice because if you're looking way ahead, it'd be nice to know if you're planning a trip for next year, how much those tickets are going to cost, and they certainly fluctuate a lot. So let's take a look at the applications of artificial intelligence. We're going to dive just a little deeper because we talked about photos, we've talked about airline ticket prices, kind of very specific, you get one specific number. But let's look at some more things that are probably more in-home, more common right now. Speaking of in-home, this young gentleman is entering his room. Of course, makes a comment like we all do when we walk into a room. This room is dark, isn't it? Let's see what happens when I enter it. The sensors in my room detect my presence and switch on the lights. This is an example of non-memory machines. Okay, it senses you. It doesn't have a memory of whether you've gone in or not. Some of the new models start running a prediction as to whether you're in the room or not, when you show up, when you don't. So they turn things on before you come down the stairs in the morning, especially if you're trying to save energy. You might have one of those fancy thermostats, which starts guessing when you get up in the morning, so it doesn't start the heater until it knows you're going to get up. So here he comes in here, and this is one of the examples of smart machine, and that is one of the many applications of artificial intelligence, one of the things we're developing here in our homes. Okay, bye. Abruptly he leaves, leaving his nice steaming cup of coffee there on the table. And when he leaves, the sensors detect he's gone and turn off the lights. Let's watch some TV. Did someone say TV? The sound sensors on the TV detect my voice and turn on the TV. Sounds kind of strange, but with the Google dongle and a Google Home Mini, you can actually do just that. You can ask it to play a movie downstairs on your downstairs TV. True also with the Amazon Fire Stick and all the different artificial intelligent home appliances that are coming out. Pretty amazing time to be alive and in this industry. Here you have one more application of artificial intelligence, and you can probably think of dozens of others that are right now on the cutting edge of development. So let's jump into my favorite part, which is a use case. Predict if a person has diabetes. And in the medical domain, if you read any of these, they say predict if a person has diabetes. But in the medical domain, we would want to restate this as, what is the risk? Is a person a high risk of diabetes? It should just be something on their radar to be looking out for. And we'll be helping you out with the use case. There we are with our cup of coffee again. I forgot to shave, as you can see. We'll start with the problem statement. The problem statement is to predict if a person has diabetes or not. And we might start with this prediction statement, but if you were actually using this in a real case, again, you would say you're high risk of diabetes would be the proper way to present that to somebody if you ran their test data through here. But that's very domain specific, which is outside of the problem statement as far as a computer programmer is involved. So we're going to have a look at the features. These are the things that have been recorded, and they already have this data from the hospitals. One of them would be number of times pregnant. Obviously, if you're a guy, that'd be 0. Glucose concentration. So these are people who've had their glucose measured. Blood pressure. Age. Age is a big factor, an easy thing to look at. Insulin level. So if someone's on insulin, they probably have diabetes. Otherwise, they wouldn't be taking insulin. But that would affect everything else, and we add that in there if they're using insulin. Let's start off with the code. So we're going to start off by importing parts of our data set. And if we're going to do this, let's jump into one of our favorite tools. We're going to use the Anaconda Jupyter Notebook. So let me flip over to there, and we'll talk just briefly about that, and then we'll look over this code. So here we are in the Jupyter Notebook, and this is an inline editor, which is just really cool for messing with Python on the fly. You can do demos in it. It's very visual. You can add pieces of code. It has cells, so you can run each cell individually. You can delete them. You can tell the cell to be a comment, so that instead of running it, it just skips over it. There's all kinds of cool things you can do with Jupyter Notebook. We're not going to go into that. We're actually going to go with the TensorFlow. And you do have to import all the different modules in your Python. Now, if you're in a different Python IDE, that's fine. It'll work in just about any of your Python IDEs. And I'll point out the one difference in code when we get to that, which is the inline for doing our graph. And in this code, we're going to go through, we're going to load our data up, we're going to explore it, we're going to label it, and then we'll use the TensorFlow, and then we'll get down to the end where we're going to take a look at how good the model is. Does it work? So let's start with the top part here. And let me go ahead and let's paste that code in there. I've added a line in at the top. I've added the folder, because I didn't put it in the same folder as the program that's running. You don't need to worry too much about that, but if you have a folder issue or it says file doesn't exist, you probably have it in the wrong folder, or you need to add the folder path. And then we're going to import pandas. And let me just, one of the cool things, since it's in Chrome, we can just do that Control plus and zoom right in there. And we have the import pandas as PD. So go ahead and draw a line in there. You can see that the pandas as PD, add a little drawing thing in there to make it a little easier to see. Pandas is a data set. It's a really nice package you can add into your Python. Usually it's done as pandas as PD. That's very common to see the PD here. Let's circle that. It's basically like an Excel spreadsheet. It adds columns, it adds headers, it adds a lot of functionality to look at your data. And the first thing we're going to do with that is we're going to come down here and we're going to read. And this is a CSV. It's a CSV file. You can open up the file on your computer if you want. If you need access to the file, you can either search it and download it from the main thing or type a note in down below on the YouTube video. And Simplilearn will help you get that file also. And that's true of any questions you have on this. You can add comments down there, and somebody at Simplilearn actually keeps an eye on that, and we'll try to answer those questions for you. I put in the full path. You don't have to if you have your data file saved in the same folder you're running your program in. And this is just a CSV file, comma-separated variables. And with the pandas, we can read it in there, and we're going to put it right in a variable called diabetes. And then finally we take diabetes, and you'll see diabetes.head. This is a pandas command, and it's really nice because it just displays the data for us. Let me go ahead and erase that. And so we go up to the run button up here in our Jupyter notebook, which runs the script in this. That's the cell we're in. And as you can see with the diabetes.head, since it's a pandas data frame, it prints everything out nice and neat for us. And this is really great. And if I go ahead and do a control minus, I can get it all to fit on the same screen. And this is the first 5 lines. When you do the head of the data, it just prints out the first 5 lines. In programming, of course, we start with 0. So we have 0, 1, 2, 3, and 4. Here we go. Here we go. We start with 0. We have 0, 1, 2, 3, and 4. We have our titles going across the top. And of course, the first column is number of pregnancies, glucose concentration for the second one, blood pressure, measurements of triceps. As we keep going, you'll see, you can guess what most of these things are. Group, I'm not sure, this is probably the test group. I didn't look it up to see specifically what that is. Anytime you start exploring data, and for this example, we don't really need to get too much in detail, you want to know the domain. What does this information mean? Are we duplicating information going in? That's beyond the scope of this. For right now, though, we're just going to look at this data and we're going to take apart the different pieces of this data. So let's jump in there and take a look at what the next set of code is. So in our next setup, or our next step, we got to start looking at cleaning the data. We got to start looking at these different columns and how are we going to bring them in? Which columns are what? And I'm going to jump ahead a little bit, and also as we look at the columns, we're going to do our import our TensorFlow as TF. That's a common import, but that's our TensorFlow model. TensorFlow was developed by Google, and then they put it into open source so that it's free for everybody to use, which is always a nice thing. So let's take a look at what these 2 steps look like in our Jupyter notebook. So let's paste this code in here, and this is something that happens when you're messing with data, is you'll repeat yourself numerous times. We already have diabetes head, so I'm going to put the little pound sign, which tells Python that this is just going to be a comment. We're not going to run it a second time. In here we have diabetes.columns, and then diabetes columns to norm equals diabetes columns to norm.apply lambda x. Let's talk about that, but let me first run that, and let's see what that comes out with that. And then let's put the next set of code in also. And I'm going to run that. Let me just hit the run button. It doesn't really have an output, but we did a lot of stuff here. So let's go over what we did on this. So I've turned on my drawing implement to help go through all this, because there's a lot going on here. The first thing is we have all of our columns up here, all of our column names. Let me just highlight that and draw a circle around that like we did earlier. And we want to look at just specific columns. And we're going to start, let me change the color on this so it really sticks out. I'll use like a blue. I'm going to look at these columns. And we're not going to do age, class, or group. We're going to look at those in a different way. And I'll explain in a little bit what that's about. So we're looking at number of pregnancies, basically anything that can be read as a float number. And you might say age could be read as a float number. We're going to address that differently because when you're doing statistics, we usually take the ages and we group them into buckets. And we'll talk about that. And so we're going to take these columns and we're going to do what they call normalize them. Column to normalize. What is normalize? If you're using the Sklearn module, one of their neural networks, they call it scaling or scalar. This is in all of these neural networks. What happens is if I have 2 pieces of data, and let's say one of them is, in this case, 0 to 6, and one of them is in insulin level is 0 to maybe 0.2 would be a very high level. I don't know what they actually go to. A neural network will look at this 6 and it'll go 0 to 6, and as you get into 0, 6, here's an 8, even a higher number, it will weight those heavier. And so it'll skew the results based more on the number of pregnancies than based on the insulin or based on the blood pressure. So we want to level the playing field. We want these values to all be in the same area. We do that by normalizing it here. And we use a lambda function. This is always a kind of a fun thing. We take the diabetes. It's a panda setup, and let me just erase all that so we can go down here, put it back to red. And we take our diabetes, which is a panda data set, and we only want to look at the columns to normalize, because that's what we built. We built a list of those columns, and we're going to apply a lambda function, and you'll see lambda in all kinds of Python programming. It just means it's a function. We put x in, and whatever is outside of the x over here, it then takes that and returns that value. So the new value is going to be whatever x is minus x min. Again, it's a pandas data set, so we can get by with that, which is really cool. It makes it easy to read. So we take x, we look for the minimum value of x, and then we divide that by the maximum value of x minus the x min, or the width. And what this essentially does is if you're going from 0 to 15, it's going to divide by 15, and then we subtract it. Let's make this 2 instead of 0. Or 20 to 115. There we go. First off, we set this to 0, so we subtract x min. So right off the bat, the minimal value is going to be 0. And then we divide it by the difference here, x min minus x max, or x max minus x min. This basically sets all the values between 0 to 1. And that's very important if we want to make sure that it's not going to be a skew in the results, if it's not going to weight the values one direction or the other. 0 to 1. That's what this is doing. And again, there's like so many different ways to scale our data. This is the most basic scale, it's standard scaling, and it's the most common. And we spelled it out in the lambda. There's actual modules that do that, but lambda it's such an easy thing to do, and you can really see what we're doing here. So now we've taken these columns, we've scaled them all and changed them to a 0 to 1 value. We now need to let the program know, the TensorFlow model that we're going to create, we need to let it know what these things are. So to do that, I create a variable called number pregnancy, keep it simple, and we've imported the TensorFlow as TF. One line of code brings our TensorFlow in for us. Awesome. Love Python. So you get number of pregnancies and tf.featureColumn.numeric column. We're going to tell it's a numeric column, so it knows that this is a float value, 0 to 1, and then number underscore pregnant. So we're taking that column and we've reshaped that column from 0 to 1. And no, that doesn't mean you have a 0.1 pregnancy. It just means 0.1 equals 1 or something. Number pregnant. So we're just mapping this data. So TensorFlow knows what to do with it. And we go through all of these. We go through all the way up to, again, we're not doing age. Let me just separate age down here. These have all been adjusted. Age, we're going to handle differently. We still put it as a numerical column because it is. So let me just circle age. And group, we didn't even touch group yet. We're going to look at group and age, and we're going to do some special stuff with that. Class, we're going to look at last. Why? Because this is whether they have diabetes or not. That's what we're testing for. So this is our history. We know these people have diabetes or not, and we want to find out, we want to create a model, and then we want to test that model predicting whether somebody new has diabetes or not. So here I am still with my cup of coffee working away, refill number 3. Let's explore both the categorical group, which is going to be the A, B, C, and D on the end, and also the age. We're going to talk about those a little bit more. And then we're going to combine all those features, and we'll jump into splitting the data, although that's kind of the next step. But we'll put that all together. What are we doing with the age, and what are we doing with the group down there? So let's flip on over and take a look at our Jupyter Notebook. So the first thing is let's put this new set of code in here and run it. And let's talk about what we're doing on this set of code. And I actually want to go one more step forward on the next set of code, or part of it. There we go. And I can go ahead and just run that while we have it. That's fine. Let's just scroll up a little bit here, and let's go through what we just did with this set of code. If we go back up here to the top part, we have group B, C, B, B, C. We learned from the header. So when I come down here, we're going to create assigned group. And let me get my drawing pad out. So we're looking at this first one up here, assigned group, TF feature column categorical column with vocabulary list. Whew, that is a mouthful. This is saying that this is a categorical list. In this case, we have A, B, C, D. You see this a lot in TensorFlow. A lot of times TensorFlow is used to analyze text or logs, error logs, and they're just full of all this information, and they take these, in this case A, B, C, D, but in other cases it'd be words, and they create numbers out of them. So it has 0, this is one column, this is another column, this is another column, this is another column. And it's just this way of being able to look at this in a different light and assigning them different values. You really don't want to assign this a float value. First thought might be, let's assign this 0 to 3, 0, 1, 2, 3 for A, B, C, D. But if you did that, it would try to add 1 plus 2 to get 3 as part of its math and functions. And that just isn't true. C does not equal A plus B. C is just a categorical name. It could have been the Frank group and Laura's group and Abid's group, but it's not. They're not float numbers. So very important that you have that distinction in your data. The next step we're looking at is our matplot. And we're going to do this. This is a cool, useful tool. We're going to import matplotlibary.pyplot as PLT, a standard import. And this next line here is really important. We're doing the matplot library. We want it to be inline. That's because we're in a Jupyter notebook. Remember I told you before that if you're running this in a different IDE, you might get a different result. This is the line you need if you want to see the graph on this page. And then we do diabetes, and we're going to look at just the age, and .hist bins equals 20. What the heck is that? Well, it turns out that because this is, remember it's a pandas, there's our PD, pandas as PD. Because this is a pandas, panda automatically knows to look for the matplot library. And a hist just means it's going to be a histogram. And we're going to separate it into 20 bins. And that's what this graph is here. So when I take the diabetes and I do a histogram of it, it produces this really nice graph. We can see that at 22, most of the participants in this, probably around 174 of the people that were recorded, were of this age bracket. They're right here in this first column here. And as they get further and further down, they have less and less and less until when you're at 80, you can actually see down here there's almost none in a couple of these categories. And this is important to note because when you're doing census, the older the group is, the more the people have passed away. So you're going to have this in any of your censuses you take. You're always going to have a much larger group in the younger crowd, and then it gets lower and lower as they get older. And I mentioned the word buckets. Here we go. We're going to create an age bucket. We're going to put people in buckets. Can you imagine people sitting in buckets? Kind of a funny way of looking at it. This just makes it easier for us to separate it. When I go to the doctor's office, I don't want to be told, well, you're age 22. This is you'll get a decent one at 22. Here we are back to my cup of coffee. I told you coffee was an underlying theme. These next couple steps are very specific to TensorFlow. Up until now, we had some TensorFlow as we set the categories up, but you'd have to set that up with any model you use to make sure they're set correctly. They'd be set up a little differently. But we run input functions. And in TensorFlow, this allows for some really cool things to happen. And this is why TensorFlow is so predominant in a lot of areas. So let's take a look at these next couple lines of code here. We're going to create the input function, and we're going to go ahead and create the model. And let me go ahead and put these codes in here. I went ahead and split it up so it has different lines, so we can talk a little bit about that. And then the actual model. And let me go ahead and run this so we can see what that looks like. And in my particular environment, it just prints out a little bit of information about the model. Not too worried about looking at that, but we do want to take a closer look at what we did here. So we've created an input function. And again, this is very specific to TensorFlow. With the input function, we have our train. We have our x equals x train and our y equals y train, because we want to train it with a particular information. But we have these other settings in here, these two settings. And the number of epochs is how many times it's going to go over our training model. Epoch means large, so it means all the data. So we're going to go over it 1,000 times. That's actually a huge overkill for this amount of data. Usually it only needs probably about 200, but when we're putting it together and you're trying things out, you just kind of throw the numbers in there and then you go back and fine tune it sometimes. The batch size is really important. This is where TensorFlow though, does some really cool things. If you're processing this over a huge amount of data and you try to batch everything at once, you end up with a problem. This means we're only going to read 10 lines at a time through our data. So each one of those rows of testing they've done, we're only going to look at 10 of them at a time and put that through our model and train it. And then shuffle is self-explanatory. We're just randomly selecting which data and what order we go in. That way, if there's like 5 in a row that are kind of weighted one way and vice versa, it mixes them up. And then finally we create our model. So the model goes in there and goes, okay, I have a tf.estimator.linear classifier. We're going to put in the feature columns equals feature columns. We defined all our columns up above. And then we have in classes equal 2. And that just means we have our out result is 0 or 1. You have diabetes or you don't have diabetes, or in this case we actually call it high risk of diabetes. And then I put one more line of code in there, which I forgot. We've set up our model. We set up our feature columns. Now we need to actually train it. Model.train. You'll see this so common in so many different neural network models. This is like a standard. What's different though is we have to feed it the function. Remember we created this function with all this information on it. And then we have steps. And steps similar to number of batches and batch size. It's more like individual lines we step through. 1,000 is a lot more common for steps than epochs. But steps is used. You could probably leave this out in this particular example. And let's go ahead and run this all together, because it has a slight, when we start training it, we get a different output. So here we go. I've run it. It's given me the information from when I created the model. And now it just starts going through and we get this information. Tensor loss equals global step. All kinds of stuff going on here. And if you're following this, it's just going through the steps and training it. It gives you information. You could dig deep into here, but for this particular setup, we're not going to go too deep on what's going on. Just know that we've trained our model. This model now has the information we need in it to start running predictions. So as we sip our next, take our next sip of coffee, or maybe it's tea, or if you're one of those strange late night workers, maybe it's a sip of wine. We go into the next step and we actually want to run some predictions on here, but we don't want to run the training. We want to run the test on there. We want to take our test data and see what it did. And so that's what we're going to do next, is we're going to run the test through and actually get some answers. So if you were actually deploying it, you would pull the answers out of the data it's bringing back. Let's take a look at that in our Jupyter notebook. So here we go. Let's paste it in there. I'm going to go ahead and run it. And you'll see that as it goes, it's actually putting the answers out. If you remember correctly, well, we'll walk through this here in just a second, but it goes through and it runs each line and it gives you a prediction for each line one at a time and prints them out. So let's take a look and see what that actually looks like. Let's start with this first part. We've created another function. This is just like the other function, except for x equals x test. And there's no y. Why is there no y? Because we don't know what the answer is on this yet. We don't want to tell it the answer. We want it to guess what the answer is. So we can evaluate that and see how good it did on that 33% of the data. So this is our X test. Batch size is 10 again. So if we were watching this roll down here, we would see that it actually processes it 10 lines at a time. It's only going to go through once. It goes through all the X test data one time. We don't need to have it predict multiple times. And shuffle equals false. Very important we set the shuffle to false, because if we were tracking this and actually giving people answers, we'd want to make sure it connects to the right person so they get the right results. But of course, we're just doing this to evaluate it. So let's take a look down here what it put out. And as I scroll down to my Jupyter notebook, we have some information as far as the TensorFlow running and then the actual output. And if we look at the output, we know by this first bracket in Python it's an array. We know by this squiggly bracket that this is a dictionary, so that this is a label. The dictionary has logistic, probabilities, class IDs, classes, and so this whole first part, let me redo that. This whole first part is one output, and we know that because there is the bracket there, and there is this bracket here for the dictionary. And it's a dictionary of terms. So if I pulled this out and I looked at object 0 in here, I would go down to, and let me just find it, here it is, classes. Remember how we define classes? We define classes as our answer. And so it's guessing, our TensorFlow says, based on all the information you gave me, I'm guessing this first entry of our first test data is high risk diabetes. Uh-oh, go get tested. Change your diet. Watch what you're eating. You know, high risk, 1. And if we go down far enough, we can see down here is another one where classes equals 0. I skipped a couple because they're all 1s up here. The B, this particular output, B, in front of the 1, means it's a binary output. It only comes out as 0 or 1. And there's a lot of other information in here. You can dig deep into TensorFlow and explain these different numbers. That's way beyond the scope of what we're working on today. So the basics of it, though, is you get an output. And we have an output of whether the person has diabetes or not. Well, in this case, it's high risk of diabetes or not. So now that we've run our predictions, take a sip of coffee, a short break, and we say, well, what do we need to do? Well, we need to know how good was our predictions. We need to evaluate our model. So if you're going to publish this to a company or something like that, they want to know how good you did. Let's take a look at what that looks like in the code. So let's paste that in here, and just real quick, go back over this. By now, this function should look very, we're going to call it eval input function. It should be pretty straightforward here. We have our TF estimator inputs, pandas input function, and then we have our X test, our Y test. This time we want to give it the answers so it has something to see how good it did on. Batches 10, processing 10 at a time. We're only going to go with once through the data. We're not shuffling it, although it doesn't really matter with this. And then we're going to do results equals model.evaluate. And we put our evaluation function in there. This should all look familiar because we're repeating the same thing. It's very similar with a couple different changes as far as what we're feeding it and the fact that we're doing an evaluation. Let's see what that looks like when we run it. And we go up here to our run model. You'll see warnings on some of these because I didn't install this on its own install. So a lot of it is temporary files because I'm using the Jupyter Notebook instead of setting it up on a regular machine. And we get our output, and we'll go ahead and just look at this output real quick, and then we'll flip over. And from here you'll see that it generates an accuracy, a baseline, average loss, the mean, gives you precision, prediction. It gives you all kinds of information on here. So let's flip over and see what's important, and we'll look at the slide. Here we are in this slide, and this should be exciting because we just about wrapped up our whole TensorFlow, and TensorFlow is one of the more complicated models out there. So give yourself a pat on the back for getting all the way through this. When we look at this output, we have an accuracy of 0.7165. That's really what we want to look at. That means that we have an accuracy, if you're just truncating it, of 71%. That's quite good for our model. You know, given a small amount of data, we came up with a 71% of letting people know they're high risk or not with diabetes. So we created a model that can predict if a person has diabetes based on some previous records of people who were diagnosed with diabetes. And we managed to have an accuracy of 71%, which is quite good. The model was implemented on Python using TensorFlow. Again, pat yourself on the back because TensorFlow is one of the more complicated scripts out there, but it's also one of the more diverse and useful ones. Let's look at another example of machine learning. Based on the amount of rainfall, how much would be the crop yield? So here we have our crops, we have our rainfall, and we want to know how much we're going to get from our crops this year. So we're going to introduce two variables, independent and dependent. The independent variable is a variable whose value does not change by the effect of other variables and is used to manipulate the dependent variable. It is often denoted as x. In our example, rainfall is the independent variable. This is a wonderful example because you can easily see that we can't control the rain, but the rain does control the crop. So when we talk about the independent variable controlling the dependent variable, let's define dependent variable as a variable whose value change when there is any manipulation in the values of the independent variables. It is often denoted as y. And you can see here our crop yield is dependent variable, and it is dependent on the amount of rainfall received. Now that we've taken a look at a real-life example, let's go a little bit into the theory and some definitions on machine learning and see how that fits together with linear regression. Numerical and categorical values. Let's take our data coming in, and this is kind of random data from any kind of project. We want to divide it up into numerical and categorical. So numerical is numbers, age, salary, height, where categorical would be a description, the color, a dog's breed, gender. Categorical is limited to very specific items, where numerical is a range of information. Now that you've seen the difference between numerical and categorical data, let's take a look at some different machine learning definitions. When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers, and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there like how much food do we give our crops? When do we harvest them? Those would be additional information add into our model. And that's why it'd be multiple linear regression. And finally we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is the statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle. A good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to x times y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below, and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from. It's called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your c coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1, plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values, based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic. Multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that. And we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumberPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplotlibary and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplotlibary inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row, that's what the first colon is, comma, except for the last column. That's what the second part is, where we have a colon -1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it, since it is a comma-separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any 2 of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in 2 steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the 3rd row. And in there we're going to take the label coder and we're going to fit and transform the X, also the 3rd row. So we're going to take that 3rd row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have X equals X colon comma 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit, because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn.linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom when we were doing all this summization? And then we also looked at setting it up with the different lines, and then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do xtrain and ytrain because we're using the training data, x being the data in and y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy x equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a yPredict variable, and we're going to put in the xTest. And let's see what that looks like. Scroll up a little bit, paste that in here, predicting the test set results. So here we have yPredict equals regressor.predict, xTest going in, and this gives us yPredict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print yPredict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print yPredict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m to the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103,009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works and understand how good it works. So, calculating the R-squared value. That's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R-squared value. And we're looking at the error. So, in the R2 score, we take our Y test versus our Y predict. Y test is the actual values we're testing. That was the one that was given to us that we know are true. The Y predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct, but you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R squared value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression. What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree, important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or our calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as a condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need is something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here. We have to make a couple changes as we go through this first part of the import. The first thing we bring in is numpy as np. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the NumPy come in for your numbers. It's called NumPython. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 1, 2, 3, 4, 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balanced data from the Panda read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or open Office Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in X equals the balance of the data dot values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for Y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in where we're going to train it, and we have to know the answer to train it with. And then we have X test where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So it'll have at least 3 splits, it'll have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what's it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created, and then you'll see .predict, and it's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case we're going to put our X test data in here. Now if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict in to print it. I could just as easily have put the print and put brackets around yPredict in to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y test, that's the one we ran the predict on, and then we put in our yPredict in, that's the answers we got, and we're just going to multiply that by 100, because this is just going to give us an answer as a decimal, and we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We might not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. So why random forest? It's always important to understand why we use this tool over the other ones. What are the benefits here? And so with the random forest, the first one is there's no overfitting. If you use of multiple trees, reduce the risk of overfitting. Training time is less. Overfitting means that we have fit the data so close to what we have as our sample that we pick up on all the weird parts. And instead of predicting the overall data, you're predicting the weird stuff, which you don't want. High accuracy. Runs efficiently on large database. For large data, it produces highly accurate predictions. In today's world of big data, this is really important. And this is probably where it really shines. This is where why random forest really comes in. It estimates missing data. Data in today's world is very messy. So when you have a random forest, it can maintain the accuracy when a large proportion of the data is missing. What that means is if you have data that comes in from 5 or 6 different areas, and maybe they took one set of statistics in one area and they took a slightly different set of statistics in the other, so they have some of the same shared data, but one is missing like the number of children in the house if you're doing something over demographics, and the other one is missing the size of the house. It will look at both of those separately and build 2 different trees, and then it can do a very good job of guessing which one fits better even though it's missing that data. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And let's we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2, where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision tree gets another image, and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. We have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. And if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes a decision is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree. But let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, and we're going to create a data set 1 and a data set 2. We just split it in two. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set, which has a very high entropy, to two lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second two, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has two or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out, how does a decision tree work? So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple of different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, they're very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle, and it's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. So we've looked at kind of a basic tree in our forest, but what we really want to know is how does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. And we build a second tree very similar, but it's split differently. Instead of the first one being split by a diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier, and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python. And let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook. which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there, and let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower, and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble import random forest classifier. And then we want to bring in two more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. So we're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Pandas is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter Notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet we have set the columns. So up on the top you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column header set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data which tells us the answer for all these different pieces, and then we've added a column with the answer. That way when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the three that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into two different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25% we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into two different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create two variables. We're going to create two new data frames. One's called train. One's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next two steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans, and let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a Panda thing, the DF columns, and we know the first four of them, 0, 1, 2, 3, that'd be the first four, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first four. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, PD. Factorize. What is factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this automatically treats this just like when we were up here and I typed in Y and it printed out Y instead of print Y. This does the same thing. It treats this as a variable and prints it out. But if you were actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see injobs equals 2. You can see the random state equals 0. Those are the 2 that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to have we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today though, all we need to do is fit or train our features and our target Y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the Setosa, the Virginica, and the Versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, Setosa, Virginica, and Versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result. And we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba, for probability. It generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for Setosa. It predicts a 0 for Virginica, and it predicts a 0 for Versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, Virginica gets 0.5 votes, Versicolor gets 0.5 votes, but let's just go with the Virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, Virginica, Versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predict test features. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually do, let's do the first 25 just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the Versicolor and the Virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head, and you'll see it says Setosa, 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 and they match. So the first one is what our forest is doing, and the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter notebook, I can do a control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes 2 sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species. So across the top, you'll see the Setosa, Versicolor, Virginica, and the actual species, Setosa, Versicolor, Virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have Versicolor where they meet, and you have Virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case, it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says Virginica, but it was supposed to be Versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names. And we're going to run the prediction, and we ran it on test features. But, we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this. And this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets, and I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in, and we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. Let's take a detour and see if we can connect this to the human experience and find out why support vector machine. So in this example, last week my son and I visited a fruit shop. Dad, is that an apple or a strawberry? So the question comes up, what fruit did I just pick up from the fruit stand? After a couple of seconds, you could figure out that it was a strawberry. So let's take this model a step further, and let's, why not build a model which can predict an unknown data? And in this, we're going to be looking at some sweet strawberries or crispy apples. We want it to be able to label those two and decide what the fruit is. And we do that by having data already put in. So we already have a bunch of strawberries, we know are strawberries, and they're already labeled as such. We already have a bunch of apples, we know are apples and are labeled as such. Then once we train our model, that model then can be given the new data, and the new data is this image. In this case, you can see a question mark on it, and it comes through and goes, it's a strawberry. In this case, we're using the support vector machine model. SVM is a supervised learning method that looks at data and sorts it into one of 2 categories. And in this case, we're sorting the strawberry into the strawberry side. At this point, you should be asking the question, how does the prediction work? Before we dig into an example with numbers, let's apply this to our fruit scenario. We have our support vector machine. We've taken it and we've taken a labeled sample of data, strawberries and apples, and we draw on a line down the middle between the 2 groups. This split now allows us to take new data, in this case an apple and a strawberry, and place them in the appropriate group based on which side of the line they fall in. And that way we can predict the unknown. As colorful and tasty as the fruit example is, let's take a look at another example with some numbers involved, and we can take a closer look at how the math works. In this example, we're going to be classifying men and women, and we're going to start with a set of people with a different height and a different weight. And to make this work, we'll have to have a sample data set of female, where you have their height and weight, 174, 65, 174, 88, and so on. And we'll need a sample data set of the male. They have a height 179, 90, 180 to 80, and so on. Let's go ahead and put this on a graph so we have a nice visual. So you can see here we have 2 groups based on the height versus the weight. And on the left side, we're going to have the women. On the right side, we're going to have the men. Now, if we're going to create a classifier, let's add a new data point and figure out if it's male or female. So before we can do that, we need to split our data first. We can split our data by choosing any of these lines. In this case, we draw in 2 lines through the data in the middle that separates the men from the women. But to predict the gender of a new data point, we should split the data in the best possible way. And we say the best possible way because this line has a maximum space that separates the 2 classes. Here you can see there's a clear split between the 2 different classes, and in this one there's not so much a clear split. This doesn't have the maximum space that separates the 2. That is why this line best splits the data. We don't want to just do this by eyeballing it. And before we go further, we need to add some technical terms to this. We can also say that the distance between the points in the line should be as far as possible. In technical terms, we can say the distance between the support vector and the hyperplane should be as far as possible. And this is where the support vectors are the extreme points in the data set. And if you look at this data set, they have circled 2 points, which seem to be right on the outskirts of the women and one on the outskirts of the men. And hyperplane has a maximum distance to the support vectors of any class. Now you'll see the line down the middle, and we call this the hyperplane because when you're dealing with multiple dimensions, it's really not just a line but a plane of intersections. And you can see here where the support vectors have been drawn in dashed lines. The math behind this is very simple. We take d plus, the shortest distance to the closest positive point, which would be on the men's side, and d minus is the shortest distance to the closest negative point, which is on the women's side. The sum of d plus and d minus is called the distance margin, or the distance between the two support vectors that are shown in the dashed lines. And then, by finding the largest distance margin, we can get the optimal hyperplane. Once we've created an optimal hyperplane, we can easily see which side the new data fits in. And based on the hyperplane, we can say the new data point belongs to the male gender. Hopefully that's clear how that works on a visual level. As a data scientist, you should also be asking what happens if the hyperplane is not optimal. If we select a hyperplane having low margin, then there is a high chance of misclassification. This particular SVM model, the one we discussed so far, is also called or referred to as the LSVM. So far so clear, but a question should be coming up. We have our sample data set, but instead of looking like this, what if it looked like this, where we have 2 sets of data, but one of them occurs in the middle of another set? You can see here where we have the blue and the yellow, and then blue again on the other side of our data line. In this data set, we can't use a hyperplane. So when you see data like this, it's necessary to move away from a 1D view of the data to a 2-dimensional view of the data. And for the transformation, we use what's called a kernel function. The kernel function will take the 1D input and transfer it to a 2-dimensional output. As you can see in this picture here, the 1D when transferred to a 2-dimensional makes it very easy to draw a line between the 2 data sets. What if we make it even more complicated? How do we perform an SVM for this type of data set? Here you can see we have a 2-dimensional data set where the data is in the middle surrounded by the green data on the outside. In this case, we're going to segregate the 2 classes. We have our sample data set, and if you draw a line through, it's obviously not an optimal hyperplane in there. So to do that, we need to transfer the 2D to a 3D array. And when you translate it into a 3-dimensional array using the kernel, you can see where you can place a hyperplane right through it and easily split the data. Before we start looking at a programming example and dive into the script, let's look at the advantage of the support vector machine. We'll start with high dimensional input space, or sometimes referred to as the curse of dimensionality. We looked at earlier 1 dimension, 2 dimension, 3 dimension. When you get to 1,000 dimensions, a lot of problems start occurring with most algorithms that have to be adjusted for. The SVM automatically does that in high dimensional space. One high dimensional space that we work on is sparse document vectors. This is where we tokenize the words in documents so we can run our machine learning algorithms over them. I've seen ones get as high as 2.4 million different tokens. That's a lot of vectors to look at. And finally, we have regularization parameter. The regularization parameter, or lambda, is a parameter that helps figure out whether we're going to have a bias or overfitting of the data. Whether it's going to be overfitted to a very specific instance or it's going to be biased to a high or low value. With the SVM, it naturally avoids the overfitting and bias problems that we see in many other algorithms. These 3 advantages of the support vector machine make it a very powerful tool to add to your repertoire of machine learning tools. Now, we did promise you a use case study where we're actually going to dive into some Python programming. And so we're going to go into a problem statement and start off with the zoo. So in the zoo example, we have family members going to the zoo and we have the young child going, "Dad, is that a group of crocodiles or alligators?" Well, that's hard to differentiate. And zoos are a great place to start looking at science and understanding how things work, especially as a young child. And so we can see the parents sitting here thinking, well, what is the difference between a crocodile and an alligator? Well, one, crocodiles are larger in size, alligators are smaller in size. Snout width, the crocodiles have a narrow snout and alligators have a wider snout. And of course, in the modern day and age, the father's sitting here thinking, how can I turn this into a lesson for my son? And he goes, let a support vector machine segregate the 2 groups. I don't know if my dad ever told me that, but that would be funny. Now, in this example, we're not going to use actual measurements and data. We're just using that for imagery. And that's very common in a lot of machine learning algorithms and setting them up. But let's roll up our sleeves, and we'll talk about that more in just a moment as we break into our Python script. So here we arrive in our actual coding. And I'm going to move this into a Python editor in just a moment. But let's talk a little bit about what we're going to cover. First, we're going to cover in the code the setup, how to actually create our SVM. And you're going to find that there's only 2 lines of code that actually create it, and the rest of it is done so quick and fast that it's all here on the first page. And we'll show you what that looks like as far as our data, because we're going to create some data. I talked about creating data just a minute ago. And so we'll get into the creating data here, and you'll see this nice correction of our 2 blobs, and we'll go through that in just a second. And then the second part is we're going to take this and we're going to bump it up a notch. We're going to show you what it looks like behind the scenes. But let's start with actually creating our setup. I like to use the Anaconda Jupyter Notebook because it's very easy to use, but you can use any of your favorite Python editors or setups and go in there. But let's go ahead and switch over there and see what that looks like. So here we are in the Anaconda Python Notebook, or Anaconda Jupyter Notebook with Python. We're using Python 3. I believe this is in any of your 3x versions. And you'd have to look at the sklearn and make sure if you're using a 2x version or an earlier version. Now let's go ahead and put our code in there. And one of the things I like about the Jupyter Notebook is I can go up to View, and I'm going to go ahead and toggle the line numbers on to make it a little bit easier to talk about. And we can even increase the size because this is edited in this case I'm using Google Chrome Explorer, and that's how it opens up for the editor. Although like I said, any editor will work. Now the first step is going to be our imports. And we're going to import 4 different parts. The first 2 I want you to look at are line 1 and line 2 are numpy as np and matplotlib and matplotlib.pyplot as plt. Now these are very standardized imports when you're doing work. The first one is the numbers Python. We need that because part of the platform we're using uses that for the numpy array. And I'll talk about that in a minute so you can understand why we want to use a numpy array versus the standard Python array. And normally it's pretty standard setup to use np for numpy. The matplot library is how we're going to view our data. So this has, you do need the np for the sklearn module, but the matplot library is purely for our use for visualization. And so you really don't need that for the SVM, but we're going to put it there so you have a nice visual aid and we can show you what it looks like. That's really important at the end when you finish everything, so you have a nice display for everybody to look at. And then finally, I'm going to jump one ahead to line number 4. That's the sklearn.datasets.samples generator import make blobs. And I told you that we were going to make up data. And this is a tool that's in the sklearn to make up data. I personally don't want to go to the zoo, get in trouble for jumping over the fence, and probably get eaten by the crocodiles or alligators as I work on measuring their snouts and width and length. Instead, we're just going to make up some data. And that's what that make blobs is. It's a wonderful tool if you're ready to test your setup and you're not sure about what data you're going to put in there. You can create this blob and it makes it real easy to use. And finally, we have our actual SVM, the sklearn import SVM on line 3. So that covers all our imports. We're going to create, remember I used the make blobs to create data. And we're going to create a capital X and a lowercase y equals make blobs in samples equals 40. So we're going to make 40 lines of data. It's going to have 2 centers with a random state equals 20. So each group's going to have 20 different pieces of data in it. And the way that looks is that we'll have under X an XY plane. So I'll have 2 numbers under X, and Y will be 0 or 1. That's the 2 different centers. So we have yes or no, in this case alligator or crocodile. That's what that represents. And then I told you that the actual sklearn or the SVM is in 2 lines of code. And we see it right here with CLF equals svm.svc kernel equals linear, and I set C equal to 1. Although in this example, since we are not regularizing the data, because we want it to be very clear and easy to see, I went ahead, you can set it to 1,000 a lot of times when you're not doing that. But for this thing, linear, because it's a very simple linear example, we only have the 2 dimensions, and it'll be a nice linear hyperplane. It'll be a nice linear line instead of a full plane. So we're not dealing with a huge amount of data. And then all we have to do is do clf.fit x, y. And that's it. CLF has been created, and then we're going to go ahead and display it. And I'm going to talk about this display here in just a second, but let me go ahead and run this code. And this is what we've done is we've created two blobs. You'll see the blue on the side and then kind of an orangish on the other side. That's our two sets of data. One represents crocodiles and one represents alligators. And then we have our measurements. In this case, we have like the width and length of the snout. And I did say I was going to come up here and talk just a little bit about our plot. And you'll see PLT, that's what we imported. We're going to do a scatter plot. That means we're just putting dots on there. And then look at this notation. I have the capital X, and then in brackets I have a colon, comma, 0. That's from NumPy. If you did that in a regular array, you'll get an error in a Python array. You have to have that in a NumPy array. It turns out that our makeBlobs returns a NumPy array. And this notation is great because what it means is the first part is the colon. It means we're going to do all the rows. That's all the data in our blob we created under capital X. And then the second part has a comma 0. We're only going to take the first value. And then if you notice, we do the same thing, but we're going to take the second value. Remember, we always start with 0 and then 1. So we have column 0 and column 1. And you can look at this as our XY plots. The first one is the X plot and the second one is the Y plot. So the first one is on the bottom, 0, 2, 4, 6, 8, and 10. And then the second one, X of the 1, is the 4, 5, 6, 7, 8, 9, 10 going up the left-hand side. S equals 30 is just the size of the dot, so we can see them instead of real tiny dots. And then CMap equals plt.cm.paired. And you'll also see the C equals Y. That's the color. We're using two colors, 0, 1, and that's why we get the nice blue and the two different colors for the alligator and the crocodile. Now you can see here that we did this, the actual fit was done in 2 lines of code. A lot of times there'll be a third line where we regularize the data. We set it between like -1 and 1, and we reshape it. But for this, it's not necessary, and it's also kind of nice because you can actually see what's going on. And then if we wanted to actually run a prediction. Let's take a look and see what that looks like. And to predict some new data, and we'll show this again as we get towards the end of digging in deep, you can simply assign your new data. In this case, I am giving it a width and length 3, 4 and a width and length 5, 6. And note that I put the data as a set of brackets and then I have the brackets inside. And the reason I do that is because when we're looking at data, it's designed to process a large amount of data coming in. We don't want to just process one line at a time. And so in this case, I'm processing 2 lines. And then I'm just going to print, and you'll see clf.predict new data. So the clf and the .predict part is going to give us an answer, and let's see what that looks like. And you'll see 0, 1. So predicted the first one, the 3, 4, is going to be on the one side, and the 5, 6 is going to be on the other side. So one came out as an alligator, and one came out as a crocodile. Now that's a pretty short explanation for the setup, but really we want to dig in and see what's going on behind the scenes. And let's see what that looks like. So the next step is to dig in deep and find out what's going on behind the scenes. And also put that in a nice pretty graph. We're going to spend more work on this than we did actually generating the original model. And you'll see here that we go through a few steps, and I'll move this over to our editor in just a second. We come in, we create our original data. It's exactly identical to the first part, and I'll explain why we redid that and show you how not to redo that. And then we're going to go in there and add in those lines. We're going to see what those lines look like and how to set those up. And finally, we're going to plot all that on here and show it. And you'll get a nice graph with what we saw earlier when we were going through the theory behind this, where it shows the support vectors and the hyperplane. And those are done where you can see the support vectors as the dashed lines and the solid line, which is the hyperplane. Let's get that into our Jupyter notebook. Before I scroll down to a new line, I want you to notice line 13. It has plot show. And we're going to talk about that here in just a second, but let's scroll down to a new line down here, and I'm going to paste that code in. And you'll see that the plot show has moved down below. Let's scroll up a little bit. And if you look at the top here of our new section, 1, 2, 3, and 4 is the same code we had before. And let's go back up here and take a look at that. We're going to fit the values on our SVM, and then we're going to plot scatter it, and then we're going to do a plot show. So you should be asking, why are we redoing the same code? Well, when you do the plot show, that blanks out what's in the plot. So once I've done this plot show, I have to reload that data. Now we could do this simply by removing it up here, rerunning it, and then coming down here, and then we wouldn't have to rerun these first 4 lines of code. Now in this, it doesn't matter too much, and you'll see the plot show is down here and then removed right there on line 5. I'll go ahead and just delete that out of there because we don't want to blank out our screen. We want to move on to the next setup. So we can go ahead and just skip the first 4 lines because we did that before. And let's take a look at the AX equals plt.gca. Now right now we're actually spending a lot of time just graphing. That's all we're doing here. Okay, so this is how we display a nice graph with our results and our data. AX is very standard used variable when you talk about PLT, and it's just setting it to that axis, the last axis in the PLT. It can get very confusing if you're working with many different layers of data on the same graph, and this makes it very easy to reference the AX. So this reference is looking at the PLT that we created and we already mapped out our 2 blobs on. And then we want to know the limits. So we want to know how big the graph is. We can find out the x limit and the y limit simply with the get x limit and get y limit commands, which is part of our matplot library. And then we're going to create a grid. And you'll see down here we've set the variable xx equal to np.linespace, x limit 0, x limit 1, 30. And we've done the same thing for the y space. And then we're going to go in here and we create a mesh grid. And this is a numpy command. So we're back to our numbers Python. Let's go through what these numpy commands mean with the line space and the mesh grid. We've taken xx, small s xx equals np line space, and we have our x limit 0 and our x limit 1, and we're going to create 30 points on it. And we're going to do the same thing for the y-axis. Now, this has nothing to do with our evaluation. It's all we're doing is we're creating a grid of data. And so we're creating a set of points between 0 and the x limit. We're creating 30 points, and the same thing with the y. And then the mesh grid loops those all together, so it forms a nice grid. So if we were going to do this, say, between the limit 0 and 10 and do 10 points, we would have a 0, 0, 1, 1, 0, 1, 0, 2, 0, 3, 0, 4 to 10, and so on. You can just imagine a point at each corner of one of those boxes. And the mesh grid combines them all, so we take the YY and the XX we created and creates the full grid. And we've set that grid into the YY coordinates and the XX coordinates. Now remember, when we're working with NumPy and Python, we like to separate those. We like to have, instead of it being x comma 1, x comma y, and then x2 comma y2, and in the next set of data it would be a column of x's and a column of y's. And that's what we have here, is we have a column of y's, and we put it as a capital YY, and a column of x's, capital XX, with all those different points being listed. And finally we get down to the NumPy VStack. Just as we created those in the mesh grid, we're now going to put them all into one array, XY array. Now that we've created the stack of data points, we're going to do something interesting here. We're going to create a value z, and the z equals the CLF. That's our support vector machine we created, and we've already trained. And we have a dot decision function, and we're going to put the xy in there. So here we have all this data. We're going to put that xy in there, that data, and we're going to reshape it. And you'll see that we have the xx.shape in here. This literally takes the xx, resets it up connected to the y, and the z value lets us know whether it is the left-hand side. It's going to generate 3 different values, the z value does. And it'll tell us whether that data is a support vector to the left, the hyperplane in the middle, or the support vector to the right. So it generates 3 different values for each of those points. And those points have been reshaped so that they're right on a line, on those 3 different lines. So we've set all of our data up. We've labeled it to 3 different areas, and we've reshaped it, and we've just taken 30 points in each direction. If you do the math, you have 30 times 30, so that's 900 points of data, and we separated it between the 3 lines and reshaped it to fit those 3 lines. We can then go back to our matplot library, where we've created the AX, and we're going to create a contour. And you'll see here where we have contour, capital XX, capital YY. These have been reshaped to fit those lines. Z is the labels. So now we have the 3 different points with the labels in there, and we can set the colors equals K. And I told you we had 3 different labels, but we have 3 levels of data. The alpha just makes it kind of see-through, so it's only 0.5 of the value in there. So when we graph it, the data will show up from behind it, wherever the lines go. And finally, the line styles. This is where we set the 2 support vectors to be dash dash lines, and then a single one is just a straight line. That's what all of that setup does. And then finally, we take our ax.scatter. We're going to go ahead and plot the support vectors, but we've programmed it in there so that they look nice, like the dash dash line and the dash line on that grid. And you can see here, when we do the CLF dot support vectors, we are looking at column 0 and column 1. And then again, we have the S equals 100, so we're going to make them larger. And the line width equals 1, face colors equals none. Let's take a look and see what that looks like when we show it. And you can see when we get down to our end result, it creates a really nice graph. We have our two support vectors in dashed lines, and they have the near data. So you can see those 2 points, or in this case the 4 points, where those lines nicely cleave the data. And then you have your hyperplane down the middle, which is as far from the two different points as possible, creating the maximum distance. So you can see that we have our nice output for the size of the body and the width of the snout, and we've easily separated the two groups of crocodile and alligator. Congratulations! You've done it. We've made it. Of course, these are pretend data for our crocodiles and alligators, but this hands-on example will help you to encounter any support vector machine projects in the future. And you can see how easy they are to set up and look at in depth. KNN is really a fundamental place to start in the machine learning. It's a basis of a lot of other things, and just the logic behind it is easy to understand and incorporated in other forms of machine learning. So today, what's in it for you? Why do we need KNN? What is KNN? How do we choose the factor K? When do we use KNN? How does KNN algorithm work? And then we'll dive into my favorite part, the use case. Predict whether a person will have diabetes or not. That is a very common and popular used data set as far as testing out models and learning how to use the different models in machine learning. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those two characteristics. Now tell me if it is a cat or a dog. An odd question. Usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or it's not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of K is a process called parameter tuning and is important for better accuracy. So at k equals 3, we can classify, we have a question mark in the middle, as either as a square or not. Is it a square, or is it, in this case, a triangle? And so if we set k equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put k equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the k changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of k? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right k? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of k, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your k is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing k, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your k value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the k value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where you might get into a gig of data if it's really clean, it doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having two variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the three closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal, hence, as per KNN algorithm, the class of 57170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, you know, if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. You know, at 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import numpy as NP. Pandas is the pandas data frame, and numpy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our numpy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data just to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results, so we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the K-neighbors classifier we're going to use. And finally, the last three are 3 tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our 2 general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, you know, the dataset 1 head, dataset 2 head, it only prints out the last one. So I usually always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those, you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns, is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this, where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do a direct. There's also one that you look for your NaN. A lot of different options in here. But the NaN, numpy NaN is what that stands for, is doesn't exist. So the first thing we're doing here is we're replacing the 0 with a numpy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column .mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NaN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way, you can still use the rest of those values to do your computation, and it kind of just brings that particular value, or those missing values, out of the equation. Let's go ahead and take this, and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you want to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle, because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set, we want to look at the I location, and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember, column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far, we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there, but the actual running of our KNN, we need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our X train equals sc_x dot fit transform. So we're creating the scaler on the X train variable, and then our X test, we're also going to transform it. So we've trained and transformed the X train, and then the X test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replaced that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data. So now we have our test data and our training data. And then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using K-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be X train. Before we do this, let's go ahead and do import math and do math square root length of Y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take 1 away and we'll make it 11. Let me delete this out of here. And that's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the K-neighbors classifier. In neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2 because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean is the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score. And finally, accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the two values we're going to put in there. And let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED. Predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model.
Welcome to this session on K-means clustering. So what is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, it's 3 clusters, and so on and so forth. That's what the K stands for. And of course, there is a way of finding out what is the best or optimum value of K for a given data. We will look at that. So that is K-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data, which consists of primarily two characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with k-means clustering, we will have here, that means k is equal to 2, and we will have two clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in k-means clustering is the allocation of two centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want two clusters, which means k is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. They are random points. They are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them 1 point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined and the original randomly allocated centroid is repositioned to the actual centroid of this new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. So this is what you're going to learn from this session. We will talk about the types of clustering, What is k-means clustering? Application of k-means clustering. K-means clustering is done using distance measure. So we will talk about the common distance measures, and then we will talk about how k-means clustering works and go into the details of k-means clustering algorithm. And then we will end with a demo and a use case for k-means clustering. So let's begin. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add BC to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is the top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes: k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together. But while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point, and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with, and then as we progress we keep changing until we get the best clusters. Or there is a technique called elbow technique whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly, that to start with, randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is, for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point, and if required, the data points are reallocated to the new centroids, and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid, and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop, and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares, and the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters, and for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value. And that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS because that pretty much gets stabilized. Okay, now that we have got the value of k, and let's assume that these are our delivery points, the next step is basically to assign 2 centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated. And the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like so. You see this? So this point earlier was closer to C2 because C2 was here. But after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned the value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we picked the centroids randomly, so they are not real centroids. So now what we have to do? we have to calculate the actual centroids for each of these groups, which is like the mean position, which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed K groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to CK and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. X1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing, and that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick K cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to CK. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each X value from each C value. So the distance between x1, c1, distance between x1, c2, x1, c3, and then we find which is the lowest value, right? That's the minimum value we find, and assign x1 to that particular centroid. Then we go next to x2, find the distance of x2 from c1, x2 from c2, x2 from c3, and so on up to ck, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into K groups because we wanted to create K clusters, right? So we have K groups. Each one may be having a certain number of input values. They need not be equally distributed, by the way. Based on the distance, we will have K groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position which is the actual centroid for each of these groups. Okay? And we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have K groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids, and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of K-means clustering. We will actually see some live demos in Python Notebook using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now the issue here is if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like Matplotlib and NumPy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in Scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead, and so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see visually, also we can figure out that there are 4 distinct classes or clusters in this data set, and that is what make blobs actually provides. Now from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and we'll create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means, in k-means, k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4. And so that instance is created. we take that instance, and as with any other machine learning functionality, fit is what we use. The function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So X has these values, the data that has been created, right? So that is what we are passing here. And this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0, cluster 0, 1, 2, and 3 maybe, and then for each of the observations, it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k means. When we call predict, that is what it does. And we can take a quick look at these y underscore k means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance, and you mention how many clusters you want by specifying this parameter n underscore clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through. I will walk you through the code at each step, what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering. And there is a function or a library calculates for a given 2 pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we call here, we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest. And accordingly, we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid. And then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare. And if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop, it only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but the change will be very minor. So in that case, also that is actually convergence, right? So for example, the change is 0.0001, we can consider that as convergence. Otherwise, what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically, we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So these colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically, what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically, we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1, and the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code, and this is the shape. So we now have also, what we have done is we changed using reshape, we converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China, the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this. And so this is how the original, the color, the pixel distribution is. These are two plots. One is red against green and another is red against blue. And this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now, what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are these. This is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very, very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the summer palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also 3-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python notebook. Alright, so let's apply the same technique for another picture, which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger, so we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors. And this is basically how it would look, 16 million colors. And now we can create the clusters out of this. The 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors. And then we go ahead and apply this and visualize how it is looking for with the new just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering, and we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering, and we use some sample data using blob to just execute the k-means clustering.
Ever wondered how Google translates an entire web page to a different language in a matter of seconds? Or your phone gallery groups images based on their location? All of this is a product of deep learning. But what exactly is deep learning? Deep learning is a subset of machine learning, which in turn is a subset of artificial intelligence. Artificial intelligence is a technique that enables a machine to mimic human behavior. Machine learning is a technique to achieve AI through algorithms trained with data. And finally, deep learning is a type of machine learning inspired by the structure of the human brain. In terms of deep learning, this structure is called an artificial neural network. Let's understand deep learning better and how it's different from machine learning. Say we create a machine that could differentiate between tomatoes and cherries. If done using machine learning, we'd have to tell the machine the features based on which the two can be differentiated. These features could be the size and the type of stem on them. With deep learning, on the other hand, the features are picked out by the neural network without human intervention. Of course, that kind of independence comes at the cost of having a much higher volume of data to train our machine. Now, let's dive into the working of neural networks. Here, we have 3 students. Each of them write down the digit 9 on a piece of paper. Notably, they don't all write it identically. The human brain can easily recognize the digits. But what if a computer had to recognize them? That's where deep learning comes in. Here's a neural network trained to identify handwritten digits. Each number is present as an image of 28 × 28 pixels. Now, that amounts to a total of 784 pixels. Neurons, the core entity of a neural network, is where the information processing takes place. Each of the 784 pixels is fed to a neuron in the first layer of our neural network. This forms the input layer. On the other end, we have the output layer, with each neuron representing a digit with the hidden layers existing between them. The information is transferred from one layer to another over connecting channels. Each of these has a value attached to it, and hence is called a weighted channel. All neurons have a unique number associated with it called bias. This bias is added to the weighted sum of inputs reaching the neuron. which is then applied to a function known as the activation function. The result of the activation function determines if the neuron gets activated. Every activated neuron passes on information to the following layers. This continues up till the second last layer. The one neuron activated in the output layer corresponds to the input digit. The weights and bias are continuously adjusted to produce a well-trained network. So, where is deep learning applied? In customer support. When most people converse with customer support agents, the conversation seems so real, they don't even realize that it's actually a bot on the other side. In medical care, neural networks detect cancer cells and analyze MRI images to give detailed results. Self-driving cars. What seemed like science fiction is now a reality. Apple, Tesla, and Nissan are only a few of the companies working on self-driving cars. So, deep learning has a vast scope, but it too faces some limitations. The first, as we discussed earlier, is data. While deep learning is the most efficient way to deal with unstructured data, a neural network requires a massive volume of data to train. Let's assume we always have access to the necessary amount of data. Processing this is not within the capability of every machine. And that brings us to our second limitation: computational power. Training a neural network requires graphical processing units, which have thousands of cores as compared to CPUs. And GPUs are, of course, more expensive. And finally, we come down to training time. Deep neural networks take hours or even months to train. The time increases with the amount of data and number of layers in the network. So, here's a short quiz for you. Arrange the following statements in order to describe the working of a neural network. A. The bias is added. B. The weighted sum of the inputs is calculated. C. Specific neuron is activated. D. The result is fed to an activation function. Leave your answers in the comments section below. Some of the popular deep learning frameworks include TensorFlow, PyTorch, Keras, Deep Learning 4J, Caffe, and Microsoft Cognitive Toolkit. Considering the future predictions for deep learning and AI, we seem to have only scratched the surface. In fact, Horus Technology is working on a device for the blind that uses deep learning with computer vision to describe the world to the users. Replicating the human mind at the entirety may be not just an episode of science fiction for too long. The future is indeed full of surprises. And that is deep learning for you in short.
Welcome to this tutorial on deep learning. Now, there are several applications of deep learning, really very interesting and innovative applications, and one of them is identifying the geographic location based on a picture. And how does this work? The way it works is pretty much we train an artificial neural network with millions of images which are tagged, their geolocation is tagged, and then when we feed a new picture, it will be able to identify the geolocation of this new image. For example, you have all these images, especially with maybe some significant monuments or significant locations, and you train with millions of such images, and then when you feed another image, it need not be exactly one of those that you have trained. It can be completely different. That is the whole idea of training. It will be able to recognize, for example, that this is a picture from Paris because it is able to recognize the Eiffel Tower. So the way it works internally, if we have to look a little bit under the hood, is these images are nothing but this is digital information in the form of pixels. So each image could be a certain size. It can be 256 by 256 pixel kind of a resolution, and then each pixel is either having a certain grade of color, and all that is fed into the neural network, and it then gets trained in, and it's able to, based on these pixel information, it is able to get trained and able to recognize the features and extract the features, and thereby it is able to identify these images and the location of these images. And then when you feed a new image, it kind of based on the training, it will be able to figure out where this image is from. So that's the way, a little bit under the hood, how it works. So what are we going to do in this tutorial? We will see what is deep learning and what do we need for deep learning. And one of the main components of deep learning is neural networks. So we will see what is neural network, what is a perceptron, and how to implement logic gates like AND, OR, NOR, and so on using perceptrons, the different types of neural networks, and then applications of deep learning. And we will also see how neural networks works. So how do we do the training of neural networks? And at the end, we will end up with a small demo code which will take you through in TensorFlow. Now, in order to implement deep learning code, there are multiple libraries or development environments that are available, and TensorFlow is one of them. So the focus at the end of this would be on how to use TensorFlow to write a piece of code using Python as a programming language. And we will take up an example which is a very common one, which is like the hello world of deep learning, the handwriting number recognition, which is a MNIST, commonly known as MNIST database. So we will take a look at MNIST database and how we can train a neural network to recognize handwritten numbers. So that's what you will see in this particular video. So let's get started. What is deep learning? Deep learning is like a subset of what is known as a high-level concept called artificial intelligence. You must be already familiar, must have heard about this term, artificial intelligence. So artificial intelligence is like the high-level concept, if you will. And in order to implement artificial intelligence applications, we use what is known as machine learning. And within machine learning, a subset of machine learning is deep learning. Machine learning is a little bit more generic concept, and deep learning is one type of machine learning, if you will. And we will see a little later in maybe the following slides a little bit more in detail how deep learning is different from traditional machine learning. But to start with, we can mention here that deep learning uses one of the differentiators between deep learning and traditional machine learning is that deep learning uses neural networks. And we will talk about what are neural networks and how we can implement neural networks and so on and so forth as a part of this tutorial. So a little deeper into deep learning. Deep learning primarily involves working with complicated unstructured data compared to traditional machine learning, where we normally use structured data. In deep learning, the data would be primarily images or voice or maybe text file. And it is a large amount of data as well. And deep learning can handle complex operations. It involves complex operations. And the other difference between traditional machine learning and deep learning is that the feature extraction happens pretty much automatically. In traditional machine learning, feature engineering is done manually. The data scientists, we data scientists have to do feature engineering, feature extraction. But in deep learning, that happens automatically. And of course, deep learning, for large amounts of data, complicated unstructured data, deep learning gives very good performance. Now, as I mentioned, one of the secret sources of deep learning is neural networks. Let's see what neural networks is. Neural networks is based on our biological neurons. The whole concept of deep learning and artificial intelligence is based on human brain, and human brain consists of billions of tiny stuff called neurons. And this is how a biological neuron looks, and this is how an artificial neuron looks. So neural networks is like a simulation of our human brain. Human brain has billions of biological neurons, and we are trying to simulate the human brain using artificial neurons. This is how a biological neuron looks. It has dendrites, and the corresponding component with an artificial neural network is, or an artificial neuron, are the inputs. They receive the inputs through dendrites. weights. And then there is the cell nucleus, which is basically the processing unit in a way. So in artificial neuron also there is a piece which is an equivalent of this cell nucleus, and based on the weights and biases, we will see what exactly weights and biases are as we move. The input gets processed and that results in an output. In a biological neuron, the output is sent through a synapse, and in an artificial neuron there is an equivalent of that in the form of an output. And biological neurons are also interconnected. So there are billions of neurons which are interconnected. In the same way, artificial neurons are also interconnected. So this output of this neuron will be fed as an input to another neuron and so on. Now, in neural network, one of the very basic units is a perceptron. So what is a perceptron? A perceptron can be considered as one of the fundamental units of neural networks. It can consist at least of one neuron, but sometimes it can be more than one neuron. But you can create a perceptron with a single neuron, and it can be used to perform certain functions. It can be used as a basic binary classifier. It can be trained to do some basic binary classification, and this is how a basic perceptron looks like. And this is nothing but a neuron. You have inputs x1, x2, to xn, and there is a summation function, and then there is what is known as an activation function. And based on this input, what is known as the weighted sum, the activation function either gives an output like a 0 or a 1. So we say the neuron is either activated or not. So that's the way it works. So you get the inputs. These inputs are, each of the inputs are multiplied by a weight, and there is a bias that gets added, and that whole thing is fed to an activation function, and then that results in an output. And if the output is correct, it is accepted. If it is wrong, if there is an error, then that error is fed back, and the neuron then adjusts the weights and biases to give a new output, and so on and so forth. So that's what is known as the training process of a neuron or a neural network. There's a concept called perceptron learning. So perceptron learning is again one of the very basic learning processes. The way it works is somewhat like this. So you have all these inputs like x1 to xn, and each of these inputs is multiplied by a weight, and then that sum, this is the formula, the equation. So that sum, wi xi sigma of that, which is the sum of all these product of x and w, is added up, and then a bias is added to that. The bias is not dependent on the input or the input values, but the bias is common for one neuron. However, the bias value keeps changing during the training process. Once the training is completed, the values of these weights, W1, W2, and so on, and the value of the bias gets fixed. So that is basically the whole training process, and that is what is known as the perceptron training. So the weights and biases keep changing till you get the accurate output, and the summation is of course passed through the activation function. As you see here, this wixi summation plus b is passed through activation function, and then the neuron gets either fired or not, and based on that there will be an output. That output is compared with the actual or expected value, which is also known as labeled information. So this is the process of supervised learning. So the output is already known, and that is compared, and thereby we know if there is an error or not. And if there is an error, the error is fed back, and the weights and biases are updated accordingly till the error is reduced to the minimum. So this iterative process is known as perceptron learning or perceptron learning rule, and this error needs to be minimized. So till the error is minimized, this iteratively the weights and biases keep changing, and that is what is the training process. So the whole idea is to update the weights and the bias of the perceptron till the error is minimized. The error need not be 0. The error may not ever reach 0, but the idea is to keep changing these weights and bias so that the error is minimum, the minimum possible that it can have. So this whole process is an iterative process, and the iteration continues till either the error is 0, which is unlikely situation, or it is the minimum possible within these given conditions. Now, in 1943, two scientists, Warren McCulloch and Walter Pitts, came up with an experiment where they were able to implement the logical functions like AND, OR, and NOR using neurons. And that was a significant breakthrough in a sense. So they were able to come up with the most common logical gates. They were able to implement some of the most common logical gates, which could take two inputs like A and B and then give a corresponding result. So for example, in case of an AND gate, A and B, and then the output is AB. In case of an OR gate, it is A plus B, and so on and so forth. And they were able to do this using a single layer perceptron. Now, most of these gates, it was possible to use single layer perceptron except for XOR, and we will see why that is in a little bit. So this is how an AND gate works. The inputs A and B, the output should be fired, or the neuron should be fired only when both the inputs are 1. So if you have 0, 0, the output should be 0. For 0, 1, it is again 0, 1, 0 again 0, and 1, 1, the output should be 1. So how do we implement this with a neuron? So it was found that by changing the values of weights, it is possible to achieve this logic. So for example, if we have equal weights like 0.7, 0.7, and then if we take the sum of the weighted product, so for example 0.7 into 0, and then 0.7 into 0 will give you 0, and so on and so forth. And in the last case, when both the inputs are 1, you get a value which is greater than 1, which is the threshold. So only in this case the neuron gets activated, and the output is, there is an output. In all the other cases, there is no output because the threshold value is 1. So this is implementation of an AND gate using a single perceptron or a single neuron. Similarly, an OR gate. In order to implement an OR gate, in case of an OR gate, the output will be 1 if either of these inputs is 1. So for example, 0, 1 will result in 1, or rather, in all the cases it is 1 except for 0, 0. So how do we implement this using a perceptron? Once again, if you have a perceptron with weights, for example 1.2, now if you see here, if in the first case when both are 0, the output is 0. In the second case, when it is 0 and 1, 1.2 into 0 is 0, and then 1.2 into 1 is 1. And in the second case, similarly, the output is 1.2. In the last case, when both the inputs are 1, the output is 2.4. So during the training process, these weights will keep changing, and then at one point where the weights are equal to W1 is equal to 1.2 and W2 is equal to 1.2, the system learns that it gives the correct output. So that is implementation of OR gate using a single neuron or a single layer perceptron. Now, XOR gate. This was one of the challenging ones. They tried to implement an XOR gate with a single level perceptron, but it was not possible. And therefore, in order to implement an XOR, so this was like a roadblock in the progress of neural network. However, subsequently they realized that this can be implemented, an XOR gate can be implemented using a multi-level perceptron or MLP. So in this case, there are two layers instead of a single layer, and this is how you can implement an XOR gate. So you will see that X1 and X2 are the inputs, and there is a hidden layer, and that's why it is denoted as H3 and H4, and then you take the output of that and feed it to the output at O5 and provide a threshold here. So we will see here that this is the numerical calculation. So the weights are, in this case for X1 it is 20 and minus 20, and once again 20 and minus 20. So these inputs are fed into H3 and H4. So you will see here for H3 the input is 0, 1, 1, 1, and for H4 it is 1, 0, 1, 1. And if you now look at the output, final output, where the threshold is taken as 1. If we use a sigmoid with the threshold 1, you will see that in these two cases it is 0, and in the last two cases it is 1. So this is the implementation of XOR. In case of XOR, only when one of the inputs is 1, you will get an output. So that is what we are seeing here. If we have either both the inputs are 1 or both the inputs are 0, then the output should be 0. So that is what is an exclusive OR gate. So it is exclusive because only one of the inputs should be 1, and then only you will get an output of 1, which is satisfied by this condition. So this is a special implementation. XOR gate is a special implementation of perceptron. Now that we got a good idea about perceptron, let's take a look at what is a neural network. So we have seen what is a perceptron, we have seen what is a neuron, so we will see what exactly is a neural network. So neural network is nothing but a network of these neurons, and they are different types of neural networks. There are about 5 of them. These are artificial neural network, convolutional neural network, then recursive neural network or recurrent neural network, deep neural network, and deep belief network. So, and each of these types of neural networks have a special, they can solve a special kind of problems. For example, convolutional neural networks are very good at performing image processing and image recognition and so on, whereas RNN are very good for speech recognition and also text analysis and so on. So each type has some special characteristics, and they are good at performing certain special kind of tasks. What are some of the applications of deep learning? Deep learning is today used extensively in gaming. You must have heard about AlphaGo, which is a game created by a startup called DeepMind, which got acquired by Google. And AlphaGo is an AI which defeated the human world champion Lee Sedol in this game of Go. So gaming is an area where deep learning is being extensively used, and a lot of research happens in the area of gaming as well. In addition to that, nowadays there are neural networks or special type called generative adversarial networks, which can be used for synthesizing either images or music or text and so on, and they can be used to compose music. So the neural network can be trained to compose a certain kind of music. And autonomous cars, you must be familiar with Google's self-driving car, and today a lot of automotive companies are investing in this space, and deep learning is a core component of this autonomous cars. The cars are trained to recognize, for example, the road, the lane markings on the road, signals, any objects that are in front, any obstruction, and so on and so forth. So all this involves deep learning. So that's another major application. And robots, we have seen several robots, including Sophia. You may be familiar with Sophia, who was given a citizenship by Saudi Arabia. And there are several such robots which are very human-like, and the underlying technology in many of these robots is deep learning. Medical diagnostics and healthcare is another major area where deep learning is being used. And within healthcare diagnostics, again, there are multiple areas where deep learning and image recognition, image processing can be used. For example, for cancer detection, as you may be aware, if cancer is detected early on, it can be cured. And one of the challenges is in the availability of specialists who can diagnose cancer using these diagnostic images and various scans and so on and so forth. So the idea is to train neural network to perform some of these activities so that the load on the cancer specialist doctors or oncologists comes down. And there is a lot of research happening here, and there are already quite a few applications that are claimed to be performing better than human beings in this space. It can be lung cancer, it can be breast cancer, and so on and so forth. So healthcare is a major area where deep learning is being applied. Let's take a look at the inner working of a neural network. So how does an artificial neural network, let's say, can we train a neural network to identify the shapes like squares and circles and triangles? When these images are fed. So this is how it works. Any image is nothing but it is a digital information of the pixels. So in this particular case, let's say this is an image of 28 by 28 pixel and this is an image of a square. There is a certain way in which the pixels are lit up, and so these pixels have a certain value, maybe from 0 to 256, and 0 indicates that it is black or it is dark, and 256 indicates it is white or lit up. So that is like an indication or a measure of how the pixels are lit up. And so this is an image is, let's say, consisting of information of 784 pixels. So all the information what is inside this image can be kind of compressed into these 784 pixels. The way each of these pixels is lit up provides information about what exactly is the image. So we can train neural networks to use that information and identify the images. So let's take a look how this works. So each neuron, the value, if it is close to 1, that means it is white, whereas if it is close to 0, that means it is black. Now this is an animation of how this whole thing works. So these pixels, one of the ways of doing it is we can flatten this image and take this complete 784 pixels and feed that as input to our neural network. The neural network can consist of probably several layers. There can be a few hidden layers, and then there is an input layer and an output layer. Now the input layer takes the 784 pixels as input, the values of each of these pixels, and then you get an output which can be of 3 types or 3 classes. One can be a square, a circle, or a triangle. Now during the training process, there will be initially, obviously you feed this image and it will probably say it's a circle or it will say it's a triangle. So as a part of the training process, we then send that error back, and the weights and the biases of these neurons are adjusted till it correctly identifies that this is a square. That is the whole training mechanism that happens out here. Now let's take a look at a circle. Same way. So you feed these 784 pixels. There is a certain pattern in which the pixels are lit up, and the neural network is trained to identify that pattern. And during the training process, once again, it would probably initially identify it incorrectly, saying this is a square or a triangle, and then that error is fed back and the weights and biases are adjusted finally till it finally gets the image correct. So that is the training process. So now we will take a look at same way a triangle. So now if you feed another image which is consisting of triangles, so this is the training process. Now we have trained our neural network to classify these images into a triangle or a circle and a square. So now this neural network can identify these 3 types of objects. Now if you feed another image, and it will be able to identify whether it's a square or a triangle or a circle. Now what is important to be observed is that when you feed a new image, it is not necessary that the image or the triangle is exactly in this position. Now the neural network actually identifies the patterns. So even if the triangle is, let's say, positioned here, not exactly in the middle but maybe at the corner or in the side, it would still identify that it is a triangle. And that is the whole idea behind pattern recognition. So how does this training process work? This is a quick view of how the training process works. So we have seen that a neuron consists of inputs. It receives inputs, and then there is a weighted sum, which is nothing but this xi, wi summation of that plus the bias, and this is then fed to the activation function, and that in turn gives us a output. Now during the training process, initially obviously when you feed these images, when you send maybe a square, it will identify it as a triangle, and when you maybe feed a triangle, it will identify as a square, and so on. So that error information is fed back, and initially these weights can be random. Maybe all of them have 0 values, and then it will slowly keep changing. So as a part of the training process, the values of these weights W1, W2 up to Wn keep changing in such a way that towards the end of the training process it should be able to identify these images correctly. So till then the weights are adjusted, and that is known as the training process. And these weights are numeric values. It could be 0.5, 0.25, 0.35 and so on. It could be positive or it could be negative, and the value that is coming here is the pixel value. As we have seen, it can be anything between 0 to 1. You can scale it between 0 to 1 or 0 to 256, whichever way. 0 being black and 256 being white, and then all the other colors in between. So that is the input. So these are numerical values. This multiplication or the product WIXI is a numerical value, and the bias is also a numerical value. We need to keep in mind that the bias is fixed for a neuron. It doesn't change with the inputs, whereas the weights are 1 per input. So that is one important point to be noted. But the bias also keeps changing. Initially it will again have a random value, but as a part of the training process, the values of the weights W1, W2, Wn and the value of B will change, and ultimately once the training process is complete, these values are fixed for this particular neuron. W1, W2 up to Wn, and plus the value of the B is also fixed for this particular neuron. And in this way there will be multiple neurons, and there may be multiple levels of neurons here, and that's the way the training process works. So this is another example of multi-layer. So there are 2 hidden layers in between, and then you have the input layer, values coming from the input layer, then it goes through multiple layers, hidden layers, and then there is an output layer. And as you can see, there are weights and biases for each of these neurons in each layer, and all of them keeps changing during the training process, and at the end of the training process all these weights have a certain value, and that is a trained model, and those values will be fixed once the training is completed. Alright, then there is something known as activation function. Neural networks consists of one of the components in neural networks is activation function, and every neuron has an activation function, and there are different types of activation functions that are used. It could be a ReLU, it could be sigmoid, and so on and so forth. And the activation function is what decides whether a neuron should be fired or not. So whether the output should be 0 or 1 is decided by the activation function. And the activation function in turn takes the input, which is the weighted sum. Remember we talked about WIXI plus B. That weighted sum is fed as an input to the activation function, and then the output can be either a 0 or a 1. And there are different types of activation functions which are covered in an earlier video you might want to watch. Alright, so as a part of the training process, we feed the inputs, the labeled data or the training data, and then it gives an output, which is the predicted output by the network, which we indicate as Y hat. And then there is a labeled data, because for supervised learning, we already know what should be the output. So that is the actual output. And in the initial process, before the training is complete, obviously there will be error. So that is measured by what is known as a cost function. So the difference between the predicted output and the actual output is the error. And the cost function can be defined in different ways. There are different types of cost functions. So in this case, it is like the average of the squares of the error. So, and then all the errors are added, which can sometimes be called as sum of square errors, or SSE, and that is then fed as a feedback in what is known as backward propagation or backpropagation, and that helps in the network adjusting the weights and biases. And so the weights and biases get updated till this value, the error value or the cost function, is minimum. Now there is a optimization technique which is used here called gradient descent optimization, and this algorithm works in a way that the error, which is the cost function, needs to be minimized. So there's a lot of mathematics that goes behind this. For example, they find the local minima and the global minima using the differentiation and so on and so forth. But the idea is this: So as a training process, as the part of training, the whole idea is to bring down the error, which is like, let's say this is the function, the cost function. At certain levels it is very high, the cost value of the cost function, the output of the cost function is very high. So the weights have to be adjusted in such a way, and also the bias of course, that the cost function is minimized. So there is this optimization technique called gradient descent that is used, and this is known as the learning rate. Now gradient descent, you need to specify what should be the learning rate, and the learning rate should be optimal, because if you have a very high learning rate, then the optimization will not converge, because at some point it will cross over to the side. On the other hand, if you have very low learning rate, then it might take forever to convert. So you need to come up with the optimum value of the learning rate, and once that is done, using the gradient descent optimization, the error function is reduced, and that's like the end of the training process. Alright, so this is another view of gradient descent. So this is how it looks. This is your cost function, the output of the cost function, and that has to be minimized using gradient descent algorithm. And these are like the parameters, and weight could be one of them. So initially we start with certain random values, so cost will be high, and then the weights keep changing, and in such a way that the cost function needs to come down, and at some point it may reach the minimum value, and then it may increase. So that is where the gradient descent algorithm decides that, okay, it has reached a minimum value and it will kind of try to stay here. This is known as the global minima. Now sometimes these curves may not be, just for explanation purpose, this has been drawn in a nice way, but sometimes these curves can be pretty erratic. There can be some local minima here, and then there is a peak, and so on. So the whole idea of gradient descent optimization is to identify the global minima and to find the weights and the bias at that particular point. So that's what is gradient descent. And then this is another example. So you can have these multiple local minima. So as you can see, at this point when it is coming down, it may appear like this is a minimum value, but then it is not. This is actually the global minimum value, and the gradient descent algorithm will make an effort to reach this level and not get stuck at this point. So the algorithm is already there, and it knows how to identify this global minimum, and that's what it does during the training process. Now, in order to implement deep learning, there are multiple platforms and languages that are available, but the most common platform nowadays is TensorFlow, and so that's the reason we have this tutorial. We have created this tutorial for TensorFlow. So we will take you through a quick demo of how to write a TensorFlow code using Python. And TensorFlow is an open source platform created by Google. So let's just take a look at the details of TensorFlow. And so this is a library, a Python library. So you can use Python or any other languages. It's also supported in other languages like Java and R and so on. But Python is the most common language that is used. So it is a library for developing deep learning applications, especially using neural networks. And it consists of primarily two parts, if you will. So one is the tensors, and then the other is the graphs or the flow. That's the way the name, that's the reason for this kind of a name called TensorFlow. So what are tensors? Tensors are like multi-dimensional arrays, if you will. That's one way of looking at it. So usually you have a one-dimensional array. So first of all, you can have what is known as a scalar, which means a number. And then you have a one-dimensional array, something like this, which means this is like a set of numbers. So that is a one-dimensional array. Then you can have a two-dimensional array, which is like a matrix. And beyond that, sometimes it gets difficult. So this is a three-dimensional array, but TensorFlow can handle many more dimensions. So it can have multi-dimensional arrays. That is the strength of TensorFlow, and which makes computation, deep learning computation, much faster. And that's the reason why TensorFlow is used for developing deep learning applications. So TensorFlow is a deep learning tool, and this is the way it works. So the data basically flows in the form of tensors, and the way the programming works as well is that you first create a graph of how to execute it, and then you actually execute that particular graph in the form of what is known as a session. We will see this in the TensorFlow code as we move forward. So all the data is managed or manipulated in tensors, and then the processing happens using these graphs. There are certain terms called, like for example, ranks of a tensor. The rank of a tensor is like a dimensionality in a way. So for example, if it is scalar, so there is just a number, just one number, the rank is supposed to be 0, and then it can be a one-dimensional vector, in which case the rank is supposed to be 1, and then you can have a two-dimensional vector, typically like a matrix. Then in that case we say the rank is 2, and then if it is a three-dimensional array, then rank is 3, and so on. So it can have more than 3 as well. So it is possible that you can store multi-dimensional arrays in the form of tensors. So what are some of the properties of TensorFlow? I think today it is one of the most popular platform. TensorFlow is the most popular deep learning platform or library. It is open source. It's developed by Google, developed and maintained by Google, but it is open source. One of the most important things about TensorFlow is that it can run on CPUs as well as GPUs. GPU is a graphical processing unit, just like CPU is central processing unit. Now, in earlier days, GPU was used primarily for graphics, and that's how the name has come. And one of the reasons is that it cannot perform generic activities very efficiently like CPU, but it can perform iterative actions or computations extremely fast and much faster than a CPU. So they are really good for computational activities, and in deep learning there is a lot of iterative computation that happens, so in the form of matrix multiplication and so on. So GPUs are very well suited for this kind of computation, and TensorFlow supports both GPU as well as CPU. And there's a certain way of writing code in TensorFlow. We will see as we go into the code. And of course, TensorFlow can be used for traditional machine learning as well, but then that would be an overkill. But just for understanding, it may be a good idea to start writing code for a normal machine learning use case, so that you get a hang of how TensorFlow code works, and then you can move into neural networks. So that is just a suggestion, but if you're already familiar with how TensorFlow works, then probably you can go straight into the neural networks part. So in this tutorial, we will take the use case of recognizing handwritten digits. This is like a hello world of deep learning, and this is a nice little MNIST database is a nice little database that has images of handwritten digits nicely formatted, because very often in deep learning and neural networks, we end up spending a lot of time in preparing the data for training. And with MNIST database, we can avoid that. You already have the data in the right format, which can be directly used for training. And MNIST also offers a bunch of built-in utility functions that we can straight away use and call those functions without worrying about writing our own functions. And that's one of the reasons why MNIST database is very popular for training purposes. Initially, when people want to learn about deep learning and TensorFlow, this is the database that is used. And it has a collection of 70,000 handwritten digits, and a large part of them are for training. Then you have test, just like in any machine learning process, and then you have validation, and all of them are labeled. So you have the images and their label, and these images, they look somewhat like this. So they are handwritten images collected from a lot of individuals. People have, these are samples written by human beings. They have handwritten these numbers going from 0 to 9. So people have written these numbers, and then the images of those have been taken and formatted in such a way that it is very easy to handle. So that is MNIST database, and the way we are going to implement this in our TensorFlow is we will feed this data, especially the training data, along with the label information. And the data is basically, these images are stored in the form of the pixel information, as we have seen in one of the previous slides. All the images are nothing but these are pixels. So an image is nothing but an arrangement of pixels, and the value of the pixel, either it is lit up or it is not, or in somewhere in between. That's how the images are stored, and that is how they are fed into the neural network and for training. Once the network is trained, when you provide a new image, it will be able to identify within a certain error, of course. And for this, we will use one of the simpler neural network configurations called softmax. And for simplicity, what we will do is we will flatten these pixels. So instead of taking them in a two-dimensional arrangement, we just flatten them out. So for example, it starts from here. It is a 28 by 28, so there are 784 pixels. So pixel number 1 starts here, it goes all the way up to 28, then 29 starts here and goes up to 56 and so on. And the pixel number 784 is here. So we take all these pixels, flatten them out, and feed them like one single line into our neural network. And this is what is known as a softmax layer. What it does is, once it is trained, it will be able to identify what digit this is. So there are, in this output layer, there are 10 neurons, each signifying a digit. And at any given point of time, when you feed an image, only one of these 10 neurons gets activated. So for example, if this is trained properly, and if you feed a number 9 like this, then this particular neuron gets activated. So you get an output from this neuron. Let me just use a pen or a laser to show you here. Okay, so you're feeding a number 9. Let's say this has been trained, and now if you're feeding a number 9, this will get activated. Now let's say you feed 1 to the trained network, then this neuron will get activated. If you feed 2, this neuron will get activated, and so on. I hope you get the idea. So this is one type of a neural network or an activation function known as softmax layer. So that's what we will be using here. This is one of the simpler ones for quick and easy understanding. So this is how the code would look. We will go into our lab environment in the cloud, and we will show you there directly. But very quickly, this is how the code looks. And let me run you through briefly here, and then we will go into the Jupyter notebook where the actual code is, and we will run that as well. So as a first step, first of all, we are using Python here, and that's why the syntax of the language is Python. And the first step is to import the TensorFlow library. So, and we do this by using this line of code saying import TensorFlow as TF. TF is just for convenience, so you can give any name. And once you do this, TensorFlow is available as an object in the name of TF, and then you can run its methods and accesses its attributes and so on and so forth. And MNIST database is actually an integral part of TensorFlow, and that's again another reason why we, as a first step, we always use this example, MNIST database example. So you just simply import MNIST database as well using this line of code, and you slightly modify this so that the labels are in this format, what is known as one hot true, which means that the label information is stored like an array. And let me just use a pen to show what exactly it is. So when you do this one hot true, what happens is each label is stored in the form of an array of 10 digits, and let's say the number is 8. Okay, so in this case, all the remaining values, there will be a bunch of zeros. So this is like array at position 0, this is at position 1, position 2, and so on and so forth. Let's say this is position 7, then this is position 8. That will be 1 because our input is 8. And again, position 9 will be 0. Okay, so one hot encoding, this one hot encoding true will kind of load the data in such a way that the labels are in such a way that only one of the digits has a value of 1, and that indicates, so based on which digit is 1, we know what is the label. So in this case, the 8th position is 1, therefore we know this sample data, the value is 8. Similarly, if you have a 2 here, let's say, then the labeled information will be somewhat like this. So you have your labels. So you have this as 0, the 0th position. The first position is also 0. The second position is 1 because this indicates number 2. And then you have third as 0 and so on. Okay, so that is the significance of this one hot true. All right, and then we can check how the data is looking by displaying the data. And as I mentioned earlier, this is pretty much in the form of digital form, like numbers. So all these are like pixel values, so you will not really see an image in this format, but there is a way to visualize that image. I will show you in a bit. And this tells you how many images are there in each set. So the training, there are 55,000 images in training, and in the test set there are 10,000, and then validation there are 5,000. So altogether there are 70,000 images. All right, so let's move on, and we can view the actual image by using the matplotlib library, and this is how you can view. This is the code for viewing the images, and you can view them in color or you can view them in grayscale. So the CMap is what tells in what way we want to view it, and what are the maximum values and the minimum values of the pixel values. So these are the max and minimum values, so of the pixel values. So maximum is 1 because this is a scaled value. So 1 means it is white, and 0 means it is black, and in between is, it can be anywhere in between black and white. And the way to train the model, there is a certain way in which you write your TensorFlow code, and the first step is to create some placeholders, and then you create a model. In this case we will use the softmax model, one of the simplest ones, and placeholders are primarily to get the data from outside into the neural network. So this is a very common mechanism that is used. And then of course you will have variables, which are your, you remember, these are your weights and biases. So for, in our case, there are 10 neurons, and each neuron actually has 784 because each neuron takes all the inputs. If we go back to our slide here, actually every neuron takes all the 784 inputs. Right? This is the first neuron. It receives all the 784. This is the second neuron. This also receives all the 780. So each of these inputs needs to be multiplied with a weight, and that's what we are talking about here. So this is a matrix of 784 values for each of the neurons, and so it is like a 10 by 784 matrix because there are 10 neurons. And similarly, there are biases. Now remember, I mentioned biases only 1 per neuron, so it is not 1 per input, unlike the weights. So therefore there are only 10 biases because there are only 10 neurons in this case. So that is what we are creating a variable for biases. So this is something little new in TensorFlow. You will see, unlike our regular programming languages where everything is a variable, here the variables can be of 3 different types. You have placeholders, which are primarily used for feeding data. You have variables, which can change during the course of computation. And then a third type, which is not shown here, are constants. So these are like fixed numbers. All right. So in a regular programming language, you may have everything as variables, or at the most variables and constants. But in TensorFlow, you have 3 different types: placeholders, variables, and constants. And then you create what is known as a graph. So TensorFlow programming consists of graphs and tensors, as I mentioned earlier. So this can be considered ultimately as a tensor. And then the graph tells how to execute the whole implementation, so that the execution is stored in the form of a graph. And in this case, what we are doing is we are doing a multiplication. TF, you remember this TF was created as a TensorFlow object here. One more level, one more. So TF is available here. Now TensorFlow has what is known as a matrix multiplication, or matmul function. So that is what is being used here. in this case. So we are using the matrix multiplication of TensorFlow so that you multiply your input values x with w, right? This is what we were doing, xw plus b. You're just adding b, and this is in very similar to one of the earlier slides where we saw sigma xi wi. So that's what we are doing here. Matrix multiplication is multiplying all the input values with the corresponding weights and then adding the bias. So that is the graph we created. And then we need to define what is our loss function and what is our optimizer. So in this case, we again use the TensorFlow's APIs. So tf.nn softmax cross entropy with logits is the API that we will use, and reduce mean is what is like the mechanism whereby which says that you reduce the error. And optimizer for doing reduction of the error, what optimizer are we using? So we are using gradient descent optimizer. We discussed about this in a couple of slides earlier. And for that, you need to specify the learning rate. You remember we saw that there was a slide somewhat like this, and then you define what should be the learning rate, how fast you need to come down. That is the learning rate. And this again needs to be tested and tried, and to find out the optimum level of this learning rate. It shouldn't be very high, in which case it will not converge, or shouldn't be very low, because it will, in that case, it will take very long. So you define the optimizer and then you call the method minimize for that optimizer, and that will kickstart the training process. And so far we've been creating the graph, and in order to actually execute that graph, we create what is known as a session, and then we run that session. And once the training is completed, we specify how many times, how many iterations we want it to run. So for example, in this case, we are saying 1000 steps. So that is a exit strategy in a way. So you specify the exit condition. So a training will run for 1000 iterations. And once that is done, we can then evaluate the model using some of the techniques shown here. So let us get into the code quickly and see how it works. So this is our cloud environment. Now you can install TensorFlow on your local machine as well. I'm showing this demo on our existing cloud, but you can also install TensorFlow on your local machine, and there is a separate video on how to set up your TensorFlow environment. You can watch that if you want to install your local environment. Or you can go for any cloud service, like for example Google Cloud, Amazon, or Cloud Labs. Any of these you can use and run and try the code. Okay, so it has got started. We will log in. Alright, so this is our deep learning tutorial code, and this is our TensorFlow environment. And so let's get started. The first, we have seen a little bit of a code walkthrough in the slides as well. Now you will see the actual code in action. So the first thing we need to do is import TensorFlow, and then we will import the data, and we need to adjust the data in such a way that the one hot encoding is set to true, one hot encoding, right? As I explained earlier. So in this case, the label values will be shown appropriately. And if we just check what is the type of the data, so you can see that this is a data sets, Python data sets. And if we check the number of images, the way it looks, so this is how it looks. It is an array of type float 32. Similarly, the number, if you want to see what is the number of training images, there are 55,000, then there are test images 10,000, and then validation images 5,000. Now let's take a quick look at the data itself, visualization. So we will use matplotlib for this. And if we take a look at the shape, now shape gives us like the dimension of the tensors or the arrays, if you will. So in this case, the training data set, if we see the size of the training data set using the method shape, it says there are 55,000 and 55,000 by 784. So remember, the 784 is nothing but the 28 by 28 28 into 28. So that is equal to 784. So that's what it is showing. Now we can take just one image and just see what is the first image and see what is the shape. So again, size, obviously it is only 784. Similarly, you can look at the image itself, the data of the first image itself. So this is how it shows. So large part of it will probably be zeros, because as you can imagine, in the image only certain areas are written, rest is blank. So that's why you will mostly see zeros, either it is black or white. But then there are these values are, so the values are actually, they are scaled, so their values are between 0 and 1. Okay, so this is what you're seeing. So certain locations there are some values, and then other locations there are zeros. So that is how the data is stored and loaded. If we want to actually see what is the value of the handwritten image, if you want to view it, this is how you view it. So you create, like, do this reshape, and Matplotlib has this feature to show you these images. So we will actually use the function called imshow, and then if you pass this parameters appropriately, you will be able to see the different images. Now I can change the values in this position, so which image we are looking at, right? So we can say, if I want to see what is there in maybe 5000, right? So 5000 has 3. Similarly, you can just say 5. What is in 5? 5 has 8. What is in 50? Again 8. So basically, by the way, if you're wondering how I'm executing this code, Shift Enter, in case you're not familiar with Jupyter Notebooks, Shift Enter is how you execute each cell, individual cell. And if you want to execute the entire program, you can go here and say run all. So that is how this code gets executed. And here again, we can check what is the maximum value and what is the minimum value of these pixel values. As I mentioned, it is scaled, so therefore it is between, the values lie between 1 and 0. Now this is where we create our model. The first thing is to create the required placeholders and variables, and that's what we are doing here, as we have seen in the slides. So we create one placeholder and we create 2 variables, which is for the weights and biases. These 2 variables are actually matrices, so each variable has 784 by 10 actual values. Okay, so one for this 10 is for each neuron, there are 10 neurons, and 784 is for the pixel values inputs that are given, which is 28 into 28. And the biases, as I mentioned, one for each neuron, so there will be 10 biases. They are stored in a variable by the name B. And this is the graph, which is basically the multiplication of these matrix multiplication of X into W, and then the bias is added for each of the neurons. And the whole idea is to minimize the error. So let me just execute. I think this code is executed. Then we define what is the Y value is basically the label value. So this is another placeholder. We had X as one placeholder and Y underscore true as a second placeholder, and this will have values in the form of 10 digit arrays. And since we said one hot encoded, the position which has a 1 value indicates what is the label for that particular number. All right, then we have cross entropy, which is nothing but the loss function, and we have the optimizer. We have chosen gradient descent as our optimizer. Then the training process itself. So the training process is nothing but to minimize the cross entropy, which is again nothing but the loss function. So we define all of this in the form of a graph. So up to here, remember what we have done is we have not exactly executed any TensorFlow code till now. We are just preparing the graph, the execution plan. That's how the TensorFlow code works. So the whole structure and format of this code will be completely different from how we normally do programming. So even with people with programming experience may find this a little difficult to understand it, and it needs quite a bit of practice. So you may want to view this video also maybe a couple of times to understand this flow, because the way TensorFlow programming is done is slightly different from the normal programming. Some of you who, let's say, have done maybe Spark programming to some extent will be able to easily understand this, but even in Spark, the programming, the code itself is pretty straightforward. Behind the scenes, the execution happens slightly differently. But in TensorFlow, even the code has to be written in a completely different way. So the code doesn't get executed in the same way as you have written. So that's something you need to understand, and a little bit of practice is needed for this. So far what we have done up to here is creating the variables and feeding the variables, and or rather not feeding, but setting up the variables and the graph. That's all. Defining maybe the what kind of a network you want to use. For example, we want to use softmax and so on. So you have created the variables, how to load the data, loaded the data, viewed the data, and prepared everything, but you have not yet executed anything in TensorFlow. Now the next step is the execution in TensorFlow. So the first step for doing any execution in TensorFlow is to initialize the variables. So anytime you have any variables defined in your code, you have to run this piece of code always. So you need to basically create what is known as a node for initializing. So this is a node. You still are not yet executing anything here. You just created a node for the initialization. So let us go ahead and create that. And here onwards is where you will actually execute your code in TensorFlow. And in order to execute the code, what you will need is a session, TensorFlow session. So tf.session will give you a session, and there are a couple of different ways in which you can do this, but one of the most common methods of doing this is with what is known as a with loop. So you have a with tf.session as ses and with a colon here, and this is like a block, starting of the block, and these indentations tell how far this block goes, and this session is valid till this block gets executed. So that is the purpose of creating this with block. This is known as a with block. So with tf.session as ses, you say ses.run init. Now ses.run will execute a node that is specified here. So for example, here we are saying ses.run. Ses is basically an instance of the session, right? So here we are saying tf.session. So an instance of the session gets created and we are calling that ses. And then we run a node within that, one of the nodes in the graph. So one of the nodes here is init. So we say run that particular node, and that is when the initialization of the variables happens. Now what this does is, if you have any variables in your code, in our case we have w is a variable and b is a variable. So any variables that we created, you have to run this code, you have to run the initialization of these variables, otherwise you will get an error. Okay, so that's what this is doing. Then we, within this with block, we specify a for loop, and we are saying we want the system to iterate for 1000 steps and perform the training. That's what this for loop does. Run training for 1000 iterations. And what it is doing basically is it is fetching the data or these images. Remember, there are about 50,000 images, but it cannot get all the images in one shot because it will take up a lot of memory and performance issues will be there. So this is a very common way of performing deep learning training. You always do in batches. So we have maybe 50,000 images, but you always do it in batches of 100 or maybe 500 depending on the size of your system and so on and so forth. So in this case we are saying, okay, get me 100 images at a time and get me only the training images. Remember, we use only the training data for training purpose, and then we use test data for test purpose. You must be familiar with machine learning, so you must be aware of this. But in case you are not, in machine learning also, this is not specific to deep learning, but in machine learning in general, you have what is known as training data set and test data set. Your available data, typically you will be splitting into two parts and using the training data set for training purpose. And then to see how well the model has been trained, you use the test data set to check or test the validity or the accuracy of the model. So that's what we are doing here. And you observe here that we are actually calling an mnest function here. So we are saying mnest train.next batch. Right? So this is the advantage of using MNIST database, because they have provided some very nice helper functions which are readily available. Otherwise, this activity itself, we would have had to write a piece of code to fetch this data in batches. That itself is a lengthy exercise. So we can avoid all that if we are using MNIST database, and that's why we use this for the initial learning phase. Okay, so when we say fetch, what it will do is it will fetch the images into X and the labels into Y, and then you use this batch of 100 images and you run the training. So ses.run, basically what we are doing here is we are running the training mechanism, which is nothing but it passes this through the neural network, passes the images through the neural network, finds out what is the output, and if the output, obviously initially it will be wrong, so all that feedback is given back to the neural network, and thereby all the W's and B's get updated till it reaches 1000 iterations. In this case, the exit criteria is 1000, but you can also specify probably accuracy rate or something like that for as an exit criteria. So here it just says that, okay, this particular image was wrongly predicted, so you need to update your weights and biases. That's the feedback given to each neuron, and that is run for 1000 iterations. And typically by the end of this 1000 iterations, the model would have learned to recognize these handwritten images. Obviously it will not be 100% accurate. Okay, so once that is done, so this happens for 1000 iterations. Once that is done, you then test the accuracy of these models by using the test data set. Right? So this is what we are trying to do here. The code may appear a little complicated because if you're seeing this for the first time, you need to understand the various methods of TensorFlow and so on. But it is basically comparing the output with what is actually there. That's all it is doing. So you have your test data, and you're trying to find out what is the actual value and what is the predicted value, and seeing whether they are equal or not, tf.equal, right? And how many of them are correct, and so on and so forth. And based on that, the accuracy is calculated as well. So this is the accuracy, and that is what we are trying to see, how accurate the model is in predicting these numbers or these digits. Okay, so let us run this. This entire thing is in one cell, so we will have to just run it in one shot. It may take a little while. Let us see. And not bad. So it has finished the 1000 iterations, and what we see here as an output is the accuracy. So we see that the accuracy of this model is around 91%. Okay, now which is pretty good for such a short exercise. Within such a short time we got 90% accuracy. However, in real life this is probably not sufficient, so there are other ways to increase the accuracy. We will see probably in some of the later tutorials how to improve this accuracy, how to change maybe the hyperparameters like number of neurons or number of layers and so on and so forth, and so that this accuracy can be increased beyond 90%.
Let's look at the different types of artificial neural networks. And this is like the biggest area growing, is how these all come together. Let's see the different types of neural network. And again, we're comparing this to human learning. So here's a human brain. I feel sorry for that poor guy. So we have a feed-forward neural network. Simplest form of they call it an ANN, a neural network, data travels only in one direction, input to output. This is what we just looked at. So as the data comes in, all the weights are added, it goes to the hidden layer, all the weights are added, it goes to the next hidden layer, all the weights are added, and it goes to the output. The only time you use the reverse propagation is to train it. So when you actually use it, it's very fast. When you're training it, it takes a while because it has to iterate through all your training data. And you start getting into big data because you can train these with a huge amount of data. The more data you put in, the better trained they get. The applications, vision and speech recognition, actually they're pretty much everything we talked about. Almost all of them use this form of neural network at some level. Radial basis function neural network. This model classifies the data point based on its distance from a center point. What that means is that you might not have training data, so you want to group things together and you create central points, and it looks for all the things, some of these things are just like the other. If you've ever watched the Sesame Street as a kid, that dates me. So it brings things together, and this is a great way. If you don't have the right training model, you can start finding things that are connected you might not have noticed before. Applications, power restoration systems. They try to figure out what's connected, and then based on that, they can fix the problem if you have a huge power system. Cohen's self-organizing neural network. Vectors of random dimensions are input to discrete map comprised of neurons. So they basically find a way to draw, and they say dimensions, or vectors, or planes, because they actually chop the data in 1 dimension, 2 dimension, 3 dimension, 4, 5, 6. They keep adding dimensions and finding ways to separate the data and connect different data pieces together. Applications used to recognize patterns in data, like in medical analysis. The hidden layer saves its output to be used for future prediction. Recurrent neural networks. So the hidden layers remember its output from last time, and that becomes part of its new input. You might use that especially in robotics or flying a drone. You want to know what your last change was and how fast it was going to help predict what your next change you need to make is to get to where the drone wants to go. Applications, text-to-speech, conversation model. So, I talked about drones, but, just identifying on Lexus or Google Assistant or any of these, they're starting to add in, I'd like to play a song on my Pandora, and I'd like it to be at volume 90%. So you now can add different things in there and it connects them together. The input features are taken in batches like a filter. This allows a network to remember an image in parts. Convolution neural network. Today's world in photo identification and taking apart photos and trying to, have you ever seen that on Google where you have 5 people together? This is the kind of thing separates all those people so then it can do a face recognition on each person. Applications used in signal and image processing. In this case, I use facial images or Google picture images as one of the options. Modular neural network. It has a collection of different neural networks working together to get the output. So, wow, we just went through all these different types of neural networks, and the final one is to put multiple neural networks together. And I mentioned that a little bit when we separated people in a larger photo, individuals in the photo, and then do the facial recognition on each person. So one network is used to separate them, and the next network is then used to figure out who they are and do the facial recognition. Applications still undergoing research. This is the cutting edge. You hear the term pipeline, and there's actual in Python code and in almost all the different neural network setups out there, they now have a pipeline feature usually. And it just means you take the data from one neural network and maybe another neural network, or you put it into the next neural network, and then you take 3 or 4 other neural networks and feed them into another one. So how we connect the neural networks is really just cutting edge, and it's so experimental. I mean, it's almost creative in its nature. There's not really a science to it because each specific domain has different things it's looking at. So if you're in the banking domain, it's going to be different than the medical domain, than the automatic car domain. And suddenly figuring out how those all fit together is just a lot of fun and really cool. So we have our types of artificial neural network. We have our feed-forward neural network. We have our radial basis function neural network. We have our Cohen self-organizing neural network, recurrent neural network, convolution neural network, and modular neural network, where it brings them all together. And the colors on the brain do not match what your brain actually does, but they do bring it out that most of these were developed by understanding how humans learn. And as we understand more and more of how humans learn, we can build something in the computer industry to mimic that, to reflect that. And that's how these were developed. So, exciting part, use case, problem statement. So this is where we jump in. This is my favorite part. Let's use the system to identify between a cat and a dog. If you remember correctly, I said we're going to do some Python code, and you can see over here my hair is kind of sticking up over the computer, a cup of coffee on one side, and then a little bit of old school, a pencil and a pen on the other side. Yeah, most people now take notes. I love the stickies on the computer. That's great. That is my computer. I have sticky notes on my computer in different colors. So not too far from today's programmer. So the problem is we want to classify photos of cats and dogs using a neural network. And you can see over here we have quite a variety of dogs in the pictures and cats, and just sorting out it is a cat is pretty amazing. And why would anybody want to even know the difference between a cat and a dog? Okay, why? Well, I have a cat door. It'd be kind of fun that instead of having like a little collar with a magnet on it, which is what my cat has, the door would be able to see, oh, that's the cat. That's our cat coming in. Oh, that's the dog. We have a dog too. That's the dog I want to let in. Maybe I don't want to let this other animal in because it's a raccoon. So you can see where you could take this one step further and actually apply this. You could actually start a little startup company idea, a self-identifying door. So this use case will be implemented on Python. I am actually in Python 3.6. It's always nice to tell people the version of Python because that does affect sometimes which modules you load and everything. And we're going to start by importing the required packages. I told you we're going to do this in Keras. So we're going to import from Keras models, a sequential from the Keras layers, conversion 2D or CONV 2D, max pooling 2D, flatten, and dense. And we'll talk about what each one of these do in just a second. But before we do that, let's talk a little bit about the environment we're going to work in. And in fact, let me go ahead and open the website, Keras's website, so we can learn a little bit more about Keras. So here we are on the Keras website, and it's keras.io. That's the official website for Keras. And the first thing you'll notice is that Keras runs on top of either TensorFlow, CNTK, and I think it's pronounced Thano or Theano. What's important on here is that TensorFlow, and the same is true for all these, but TensorFlow is probably one of the most widely used currently packages out there with the Keras. And of course, tomorrow this is all going to change. It's all going to disappear and they'll have something new out there. So make sure when you're learning this code that you understand what's going on and also know the code. I mean, when you look at the code, it's not as complicated once you understand what's going on. The code itself is pretty straightforward. And the reason we like Keras, and the reason that people are jumping on it right now and it's such a big deal is if we come down here, let me just scroll down a little bit, they talk about user friendliness, modularity, easy extensibility, work with Python. Python's a big one because a lot of people in data science now use Python, although you can actually access Keras other ways. If we continue down here is layers. And this is where it gets really cool. When we're working with Keras, you just add layers on. Remember those hidden layers we were talking about? And we talked about the ReLU activation. You can see right here. Let me just up that a little bit in size. There we go. That's big. I can add in an ReLU layer, and then I can add in a softmax layer in the next instance. We didn't talk about softmax. So you can do each layer separate. Now, if I'm working in some of the other kits I use, I take that and I have one setup, and then I feed the output into the next one. This one I can just add hidden layer after hidden layer with the different information in it, which makes it very powerful and very fast to spin up and try different setups and see how they work with the data you're working on. And we'll dig a little bit deeper in here. And a lot of this is very much the same, so when we get to that part I'll point that out to you also. Now, just a quick side note, I'm using Anaconda with Python in it, and I went ahead and created my own package, and I called it the Keras Python 3.6 because I'm in Python 3.6. Anaconda is cool that way. You can create different environments real easily. If you're doing a lot of different experimenting with these different packages, you probably want to create your own environment in there. And the first thing is you can see right here, there's a lot of dependencies. A lot of these you should recognize by now if you've done any of these videos. If not, kudos for you for jumping in today. Pip install numpy, scipy, the scikit-learn, pillow, and h5py are both needed for the TensorFlow and then putting the Keras on there. And then you'll see here, and pip is just a standard installer. that you use with Python. You'll see here that we did pip install TensorFlow, since we're going to do Keras on top of TensorFlow. And then pip install, and I went ahead and used the GitHub. So git plus git, and you'll see here github.com. This is one of their releases, one of the most current release on there that goes on top of TensorFlow. And you can look up these instructions pretty much anywhere. This is for doing it on Anaconda. Certainly you'd want to install these if you're doing it in Ubuntu server setup. You'd want to get, I don't think you need the H5PY in Ubuntu, but you do need the rest in there because there are dependencies in there, and it's pretty straightforward. And that's actually in some of the instructions they have on their website. So you don't have to necessarily go through this. Just remember their website on there. And then when I'm under my Anaconda Navigator, which I like, you'll see where I have environments, and on the bottom I created a new environment and I called it Keras Python 36, just to separate everything. You can say I have Python 30.5 and Python 3.6. I used to have a bunch of other ones, but I kind of cleaned house recently. And of course, once I go in here, I can launch my Jupyter Notebook, making sure I'm using the right environment that I just set up. This, of course, opens up my, in this case I'm using Google Chrome, and in here I could go and just create a new document in here. And this is all in your browser window when you use the Anaconda. Do you have to use Anaconda in Jupyter Notebook? No. You can use any kind of Python editor, whatever setup you're comfortable with and whatever you're doing in there. So let's go ahead and go in here and paste the code in. And we're importing a number of different settings in here. We have import sequential. That's under the models, because that's the model we're going to use as far as our neural network. And then we have layers, and we have conversion 2D, max pooling 2D, flatten, dense. And you can actually just kind of guess at what these do. We're working in a 2D photograph. And if you remember correctly, I talked about how the actual input layer is a single array. It's not in 2 dimensions, it's 1 dimension. All these do is these are tools to help flatten the image. So it takes a 2-dimensional image and then it creates its own proper setup. You don't have to worry about any of that. You don't have to do anything special with the photograph. You let the Keras do it. And we're going to run this, and you'll see right here they have some stuff that is going to be depreciated and changed, because that's what it does. Everything's being changed as we go. You don't have to worry about that too much. If you have warnings, if you run it a second time, the warning will disappear. And this has just imported these packages for us to use. And Jupyter's nice about this, that you can do each thing step by step. And I'll go ahead and also zoom in there. A little Control Plus. That's one of the nice things about being in a browser environment. So here we are back. Another sip of coffee. If you're familiar with my other videos, you notice I'm always sipping coffee. I always have in my case, latte next to me, an espresso. So the next step is to go ahead and initialize, we're going to call it the CNN, or classifier neural network. And the reason we call it a classifier is because it's going to classify it between 2 things. It's going to be cat or dog. So when you're doing classification, you're picking specific objects. You're specific, it's a true or false, yes, no, it is something or it's not. So first thing, we're going to create our classifier, and it's going to equal sequential. So their sequential setup is the classifier. That's the actual model we're using. That's the neural network. So we call it a classifier. And the next step is to add in our convolution. And let me just do let me shrink that down in size so you can see the whole line. And let's talk a little bit about what's going on here. I have my classifier and I add something. What am I adding? Well, I'm adding my first layer. This first layer we're adding in is probably the one that takes the most work to make sure you have it set correct. And the reason I say that is this is your actual input. And we're going to jump here to the part that says input shape equals 64 by 64 by 3. What does that mean? Well, that means that our picture's coming in, and there's these pictures. Remember we had like the picture of the car was 128 by 128 pixels? Well, this one is 64 by 64 pixels. And each pixel has 3 values. That's where these numbers come from. And it is so important that this matches. I mentioned a little bit that if you have like a larger picture, you have to reformat it to fit this shape. If it comes in as something larger, there's no input nodes. There's no input neural network there that will handle that extra space. So you have to reshape your data to fit in here. Now, the first layer is the most important, because after that, Keras knows what your shape is coming in here, and it knows what's coming out. And so that really sets the stage. Most important thing is that input shape matches your data coming in. And you'll get a lot of errors if it doesn't. You'll go through there and picture number 55 doesn't match it correctly. And guess what it does? It usually gives you an error. And then the activation, if you remember, we talked about the different activations on here. We're using the RELU model. Like I said, that is the most commonly used now because, one, it's fast. It doesn't have the added calculations in it. It just says, here's the value coming out based on the weights and the value going in. And from there, you know, it's if it's over 1, then it's good. Or over 0, it's good. If it's under 0, then it's considered not active. And then we have this conversion 2D. What the heck is conversion 2D? I'm not going to go into too much detail in this because this has a couple of things it's doing in here. A little bit more in depth than we're ready to cover in this tutorial. But this is used to convert from the photo, because we have 64 by 64 by 3, and we're just converting it to two-dimensional kind of setup. So it's very aware that this is a photograph and that different pieces are next to each other. And then we're going to add in a second convolutional layer. That's what the CONV stands for, 2D. So these are hidden layers. So we have our input layer and our two hidden layers, and they are two-dimensional because we're doing with a two-dimensional photograph. And you'll see down here that on the last one we add a max pooling 2D, and we put a pool size equals 2, 2. And so what this is that as you get to the end of these layers, one of the things you always want to think of is what they call mapping and then reducing. Wonderful terminology from the big data. We're mapping this data through all these layers, and now we want to reduce it to only 2 sets. In this case, it's already in 2 sets because it's a 2D photograph. But we had, 2 dimensions we actually have 64 by 64 by 3. So now we're just getting it down to a 2 by 2, just the two-dimensional instead of having the third dimension of colors. And we'll go ahead and run these. We're not really seeing anything on our run script because we're just setting up. This is all set up. And this is where you start playing, because maybe you'll add a different layer in here to do something else to see how it works and see what your output is. That's what makes Keras so nice, is I can, with just a couple flips of code, put in a whole new layer that does a whole new processing and see whether that improves my run or makes it worse. And finally, we're going to do the final setup, which is to flatten. Classifier add a flatten setup, and then we're going to also add a dense layer, and then we're going to add in another dense layer, and then we're going to build it. We're going to compile this whole thing together. So let's flip over and see what that looks like. And we've even numbered them for you. So we're going to do the flattening. And flatten is exactly what it sounds like. We've been working in a two-dimensional array of picture, which actually is in 3 dimensions because of the pixels. The pixels have a whole other dimension to it of 3 different values. And we've kind of resized those down to 2 by 2. But now we're just going to flatten it. I don't want to have multiple dimensions being worked on by Tensor and by Keras. I want just a single array, so it's flattened out. And then step 4, full connection. So we add in our final 2 layers, and you could actually do all kinds of things with this. You could actually leave out this some of these layers and play with them. You do need to flatten it. That's very important. Then we want to use the dense. Again, we're taking this and we're taking whatever came into it. So once we take all those the 2 dimensions or 3 dimensions as they are, and we flatten it to 1 dimension, we want to take that and we're going to pool it into units of 128. They got that. You can say, where did they get 128 from? You could actually play with that number and get all kinds of weird results. But in this case, we took the 64 plus 64 is 128. You could probably even do this with 64 or 32. Usually you want to keep it in the same multiple, whatever the data shape you're already using is in. And we're using the activation, the RELU, just like we did before. And then we finally filter all that into a single output. And it has how many units? 1. Why? Because we want to know whether true or false. It's either a dog or a cat. You could say 1 is dog, 0 is cat. Or maybe you're a cat lover and it's 1 is cat and 0 is dog. And if you love both dogs and cats, you're going to have to choose. And then we use the sigmoid activation. If you remember from before, we had the RELU and there's also the sigmoid. The sigmoid just makes it clear it's yes or no. We don't want any kind of in-between number coming out. And we'll go ahead and run this, and you'll see it's still all in setup. And then finally we want to go ahead and compile. And let's put the compiling our classifier neural network. And we're going to use the optimizer Atom. And I hinted at this just a little bit before. Where does Atom come in? Where does an optimizer come in? Well, the optimizer is the reverse propagation. When we're training it, it goes all the way through and says error, and then how does it readjust those weights? There are a number of them. Atom is the most commonly used, and it works best on large data. Most people stick with the atom because when they're testing on smaller data, see if their model is going to go through and get all their errors out before they run it on larger data sets. They're going to run it on atom anyway, so they just leave it on atom, most commonly used. But there are some other ones out there. You should be aware of that you might try them if you're stuck in a bind, or you might explore that in the future. But usually atom is just fine on there. And then you have two more settings. You have loss and metrics. We're not going to dig too much into loss or metrics. These are things you really have to explore Keras because there are so many choices. This is how it computes the error. There's so many different ways on your back propagation and your training. So we're using the atom model, but you can compute the error by standard deviation squared. They use binary cross entropy. I'd have to look that up to even know what that is. There's so many of these. A lot of times you just start with the ones that look correct, that are most commonly used, and then you have to go read the Keras site and actually see what these different losses and metrics and what different options they have. So we're not going to get too much into them other than to reference you over to the Keras website to explore them deeper. But we are going to go ahead and run them. And now we've set up our classifier. So we have an object classifier, and if you go back up here, you'll see that we've added in step 1, we added in our layer for the input. We added a layer that comes in there and uses the RELU for activation, and then it pulls the data. So this is, even though these are two layers, the actual neural network layer is up here, and then it uses this to pull the data into a 2x2. So into a 2-dimensional array from a 3-dimensional array with the colors. Then we flatten it. So there's our adder flatten. And then we add another dense, what they call dense layer. This dense layer goes in there and it downsizes it to 128. It reduces it. So you can look at this as we're mapping all this data down the 2-dimensional setup, and then we flatten it. So we map it to a flattened map, and then we take it and reduce it down to 128. And we use the RELU again. And then finally we reduce that down to just a single output, and we use the sigmoid to do that, to figure out whether it's yes, no, true, false, in this case cat or dog. And then finally, once we put all these layers together, we compile them. That's what we've done here. And we've compiled them as far as how it trains to use these settings for the training, back propagation. So if you remember, we talked about training our setup. And when we go into this, you'll see that we have two data sets. We have one called the training set and the testing set. And that's very standard in any data processing, is you need to have, that's pretty common in any data processing, is you need to have a certain amount of data to train it, and then you got to know whether it works or not. Is it any good? And that's why you have a separate set of data for testing it, where you already know the answer, but you don't want to use that as part of the training set. So in here we jump into part 2, fitting the classifier neural network to the images. And then from Keras, and let me just zoom in there. I always love that about working with Jupyter Notebooks, you can really see. We're going to come in here, we do the cross pre-processing an image, and we import image data generator. It's so nice of Keras. It's such a high-end product right now going out, and since images are so common, they already have all this stuff to help us process the data, which is great. And so we come in here, we do train data gen, and we're going to create our object for helping us train it, for reshaping the data so that it's going to work with our setup. And we use an image data generator, and we're going to rescale it. And you'll see here we have 1 point, which tells it it's a float value on the rescale over 255. Where does 255 come from? Well, that's the scale in the colors of the pictures we're using. They're value from 0 to 255. So we want to divide it by 255, and it'll generate a number between 0 and 1. They have shear range and zoom range. Horizontal flip equals true. And this, of course, has to do with if the photos are different shapes and sizes. Like I said, it's a wonderful package. You really need to dig in deep to see all the different options you have for setting up your images. For right now, though, we're going to just stick with some basic stuff here. And let me go ahead and run this code. And again, it doesn't really do anything because we're still setting up the pre-processing. Let's take a look at this next set of code. And this one is just huge. We're creating the training set. So the training set is going to go in here and it's going to use our train data gen we just created, .flow from directory. It's going to access, in this case, the path, data set, training set. That's a folder. So it's going to pull all the images out of that folder. Now, I'm actually running this in the folder that the data set's in. So if you're doing the same setup and you load your data in there and you're doing this, make sure wherever your Jupyter Notebook is saving things to that you create this path, or you can do the complete path if you need to, C:// etc. And the target size, the batch size, and class mode is binary. So the classes, we're switching everything to a binary value. Batch size, what the heck is batch size? Well, that's how many pictures we're going to batch through the training each time. And the target size, 64 by 64. A little confusing, but you can see right here that this is just a general training, and you can go in there and look at all the different settings for your training set. And of course, with different data, we're doing pictures. There's all kinds of different settings depending on what you're working with. Let's go ahead and run that and see what happens. And you'll see that it found 800 images belonging to one classes. So we have 800 images in the training set. And if we're going to do this with the training set, we also have to format the pictures in the test set. Now, we're not actually doing any predictions. We're not actually programming the model yet. All we're doing is preparing the data. So we're going to prepare a training set and the test set. So any changes we make to the training set at this point also have to be made to the test set. So we've done this thing, we've done a train data generator, we've done our training set, and then we also have, remember, our test set of data. So I'm going to do the same thing with that. I'm going to create a test data gen, and we're going to do this image data generator. We're going to rescale 1/255. We don't need the other settings, just the single setting for the test data gen. And we're going to create our test set. We're going to do the same thing we did with the test set, except that we're pulling it from the test set folder. And we'll run that, and you'll see in our test set we found 2,000 images. That's about right. We're using 20% of the images as test and 80% to train it. And then finally, we've set up all our data. We've set up all our layers, which is where all the work is cleaning up that data and making sure it's going in there correctly. And we're actually going to fit it. We're going to train our data set. And let's see what that looks like. And here we go. Let's put the information in here. And let's just take a quick look at what we're looking at with our fit generator. We have our classifier.fit generator. That's our back propagation. So the information goes through forward with a picture, and it says, oh, you're either right or you're wrong, and then the error goes backward and reprograms all those weights. So we're training our neural network. And of course, we're using the training set. Remember, we created the training set up here. And then we're going steps per epoch. So it's 8,000 steps. Epoch means that's how many times we go through all the pictures. So we're going to rerun each of the pictures, and we're going to go through the whole data set 25 times. But we're going to look at each picture during each epoch 8,000 times. So we're really programming the heck out of this and going back over it. And then they have validation data equals test set. So we have our training set, and then we're going to have our test set to validate it. So we're going to do this all in one shot. And we're going to look at that, and they're going to do 200 steps for each validation. And we'll see what that looks like in just a minute. Let's go ahead and run our training here. And we're going to fit our data. And as it goes, it says epoch 1 of 25. You start realizing that this is going to take a while. On my older computer, it takes about 45 minutes. I have a dual processor. We're processing 10,000 photos. That's not a small amount of photographs to process. So if you're on your laptop, which I am, it's going to take a while. So let's go ahead and go get our cup of coffee and a sip and come back and see what this looks like. So I'm back. You didn't know I was gone. That was actually a lengthy pause there. I made a couple changes, and let's discuss those changes real quick and why I made them. So the first thing I'm going to do is I'm going to go up here and insert a cell above, and let's paste the original code back in there. And you'll see that the original thing was steps per epoch 8,000, 25 epochs, and validation steps 2,000. And I changed these to 4,000 epochs, or 4,000 steps per epoch, 10 epochs, and just 10 validation steps. And this will cause problems if you're doing this as a commercial release. But for demo purposes, this should work. And if you remember, our steps per epoch, that's how many photos we're going to process. In fact, let me go ahead and get my drawing pen out. And let's just highlight that right here. Well, we have 8,000 pictures we're going through. So for each epoch, I'm going to change this to 4,000. I'm going to cut that in half. So it's going to randomly pick 4,000 pictures each time it goes through an epoch. And the epoch is how many processes. So this is 25, and I'm just going to cut that to 10. So instead of doing 25 runs through 8,000 photos each, which you can do the math of 25 times 8,000, I'm only going to do 10 through 4,000. So I'm going to run this 40,000 times through the processes. And the next thing I noted you'll want to notice is that I also changed the validation step. And this would cause some major problems in releasing because I dropped it all the way down to 10. What the validation step does is it says we have 2,000 photos in our trainings or in our testing set. And we're going to use that for validation. Well, I'm only going to use a random 10 of those to validate. So not really the best settings, but let me show you why we did that. Let's scroll down here just a little bit. And let's look at the output here and see what's going on there. So I've got my drawing tool back on, and you'll see here it lists a run. So each time it goes through an epic, it's going to do 4,000 steps. And this is where the 4,000 comes in. So that's where we have epic 1 of 10, 4,000 steps. So it's randomly picking half the pictures in the file and going through them. And then we're going to look at this number right here. That is for the whole epic, and that's 2,411 seconds. And if you remember correctly, you divide that by 60, you get minutes. If you divide that by 60, you get hours. Or you can just divide the whole thing by 60 times 60, which is 3,600. If 3,600 is an hour, this is roughly 45 minutes right here. And that's 45 minutes to process half the pictures. So if I was doing all the pictures, we're talking an hour and a half per epic times 36. Or no, 25. They had 25 up above. 25. So that's roughly a couple days. A couple days of processing. Well, for this demo, we don't want to do that. I don't want to come back the next day. Plus, my computer did a reboot in the middle of the night. So we look at this and we say, okay, we're just testing this out. My computer that I'm running this on is a dual core processor. Runs 0.9 gigahertz per second. For a laptop, it was good about 4 years ago, but for running something like this, it's probably a little slow. So we cut the times down, and the last one was validation. We're only validating it on a random 10 photos. And this comes into effect because you're going to see down here where we have accuracy, value loss, value accuracy, and loss. Those are very important numbers to look at. So the 10 means I'm only validating across 10 pictures. That is where, here we have value, this is ACC is for accuracy. Value loss, we're not going to worry about that too much, and accuracy. Now accuracy is while it's running, it's putting these two numbers together. That's what accuracy is. And value accuracy is at the end of the epic. What's our accuracy at the end of the epic? What is it looking at? In this tutorial, we're not going to go so deep, but these numbers are really important when you start talking about these two numbers reflect bias. That is really important. I'll just put that up there. And bias is a little bit beyond this tutorial, but the short of it is if this accuracy, which is being our validation per step, is going down, and the value accuracy continues to go up, that means there's a bias. That means I'm memorizing the photos I'm looking at. I'm not actually looking for what makes a dog, what makes a cat. I'm just memorizing them. And so the more this discrepancy grows, the bigger the bias is. And that is really the beauty of the Keras neural network. It has a lot of built-in features like this that make that really easy to track. So let's go ahead and take a look at the next set of code. So here we are into part 3. We're going to make a new prediction. And so we're going to bring in a couple tools for that, and then we have to process the image coming in and find out whether it's an actual dog or cat, if we can actually use this to identify it. And of course the final step of part 3 is to print prediction. We'll go ahead and combine these, and of course you can see me there adding more sticky notes to my computer screen, hidden behind the screen, and last one was don't forget to feed the cat and the dog. So let's go ahead and take a look at that and see what that looks like in code and put that in our Jupyter notebook. All right, and let's paste that in here. And we'll start by importing NumPy as NP. NumPy is a very common package. I pretty much import it on any Python project I'm working on. Another one I use regularly is pandas. They're just ways of organizing the data. And then NP is usually the standard in most machine learning tools as a return for the data array. Although, you can use a standard data array from Python. And we have Keras pre-processing, import image. This should all look familiar because we're going to take a test image and we're going to set that equal to, in this case, cat or dog 1, as you can see over here. And let me get my drawing tool back on. So let's take a look at this. We have our test image we're loading, and in here we have test image 1, and this one data hasn't seen this one at all, so this is all new. Oh, let me shrink the screen down. Let me start that over. So here we have my test image, and we went ahead and the Keras processing has this nice image setup. So we're going to load the image and we're going to alter it to a 64 by 64 print. So right off the bat, Keras is nice that way. It automatically sets it up for us so we don't have to redo all our images and find a way to reset those. And then we use all those to set the image to an array. So again, we're all in pre-processing the data, just like we pre-processed before with our test information and our training data. And then we use the NumPy. Here's our NumPy. That's from our right up here, import numpy as np. Expand the dimensions, test image, axes equals 0. So it puts it into a single array. And then finally, all that work, all that pre-processing, and all we do is we run the result. We click on here and we go result equals classifier predict test image, and then we find out, well, what is the test image? And let's just take a quick look and just see what that is. And you can see when I ran it, it comes up dog, and if we look at those images, there it is, cat or dog, image number 1. That looks like a nice floppy-eared lab. Friendly with his tongue hanging out. It's either that or a very floppy-eared cat. I'm not sure which. But according to our software, it says it's a dog. And we have a second picture over here. Let's just see what happens when we run the second picture. We can go up here and change this from dog image 1 to 2. We'll run that, and it comes down here and says cat. You can see me highlighting it down there as cat. So our process works. We are able to label a dog and a cat just from the pictures. There we go, cleared my drawing tool. And the last thing I want you to notice, when we come back up here to when I ran it, you'll see it has an accuracy of 1 and the value accuracy of 1. Well, the value accuracy is the important one, because the value accuracy is what it actually runs on the test data. Remember, I'm only validating it on a random 10 photos. And those 10 photos just happen to come up 1. Now, when they ran this on the server, it actually came up about 86%. This is why cutting these numbers down so far for a commercial release is bad. So you want to make sure you're a little careful of that when you're testing your stuff, that you change these numbers back when you run it on a more enterprise computer other than your old laptop that you're just practicing on or messing with. And we come down here and again, we had the validation of cat. And so we have successfully built a neural network that could distinguish between photos of a cat and a dog. Imagine all the other things you could distinguish. Imagine all the different industries you could dive into with that, just being able to understand those two different pictures. What about mosquitoes? Could you find the mosquitoes that bite versus the mosquitoes that are friendly? It turns out the mosquitoes that bite us are only 4% of the mosquito population, if even that, maybe 2%. There's all kinds of industries that use this, and there's so many industries that are just now realizing how powerful these tools are. Just in the photos alone, there is a myriad of industries sprouting up. And I said it before, I'll say it again, what an exciting time to live in with these tools that we get to play with.
Welcome to TensorFlow 2.0 tutorial. What's in it for you? We're going to cover today deep learning frameworks, what is TensorFlow, features of TensorFlow, TensorFlow applications, how TensorFlow works, TensorFlow 1.0 versus 2.0, TensorFlow 2.0 architecture, and then we'll go over a TensorFlow demo where we roll up our sleeves and dive right into the code. So let's start with deep learning frameworks. To start with, this chart doesn't even do the filled justice because it's just exploded. These are just some of the major frameworks out there. There's Keras, which happens to sit on TensorFlow, so they're very integrated. There's TensorFlow, PyTorch is out there, Caffe, Theano, DL4J, and Chainer. These are just a few of the deep learning frameworks. We're talking about neural networks. If you're just starting out and never seen a neural network, you can go into Python in the scikit and do the neural network in there, which is probably the most simplest version I know. But the most robust version out there, the most top of the ladder as far as the technology right now, is TensorFlow. And that, of course, is changing from day to day. And some of these are better for different purposes. So let's dive into TensorFlow. Let's see, what is TensorFlow? What is TensorFlow? TensorFlow is a popular open source library released in 2015 by Google Brain Team for building machine learning and deep learning models. It is based on Python programming language and performs numerical computations using data flow graphs to build models. So let's take a look at some of the features of TensorFlow. It works efficiently with multi-dimensional arrays. If you've ever played with any of the simpler packages of neural networks, you're going to find that you have to pretty much flatten them and make sure your stuff is set in a flat model. TensorFlow works really good. So we're talking pictures here, where you have X and Y coordinates where the picture is, and then each pixel has 3 or 4 different channels. That's a very complicated array, a very multidimensional array. It provides scalability of computation across machines and large data sets. This is so new right now. And you might think that's a minor thing, but when Python is operating on one computer and it has a float value and it truncates it differently on each computer, you don't get the same results. And so your training model might work on one machine and then on another it doesn't. This is one of the things that TensorFlow addresses and does a very good job on. It supports fast debugging and model building. This is why I love TensorFlow. I can go in there and I can build a model with different layers. Each layer might have different properties. They have like the convolutional neural network, which you can then sit on top of a regular neural network with reverse propagation. There's a lot of tools in here and a lot of options. And each layer that it goes through can utilize those different options and stack differently. And it has a large community and provides TensorBoard to visualize the model. TensorBoard's pretty recent, but it's a really nice tool to have so when you're working with other people or showing your clients or the shareholders in the company, you can give them a nice visual model so they know what's going on. What are they paying for? And let's take a glance at some of the different uses or applications for TensorFlow. When we talk about TensorFlow applications, clearly this is data analytics. We're getting into the data science. I like to use data science as probably a better term because this is the programming side. And it's really the sky is the limit. We can look at face detection, language translation, fraud detection, video detection. There are so many different things out there that TensorFlow can be used for. When you think of neural networks, because TensorFlow is a neural network, think of complicated chaotic data. This is very different than if you have a set numbers like you're looking at the stock market. You can use this on the stock market, but if you're doing something where the numbers are very clear and not so chaotic as you have in a picture, then you're talking more about linear regression models and different regression models when you're looking at that. When you're talking about these really complicated data patterns, then you're talking neural networks and TensorFlow. And if we're going to talk about TensorFlow, we should talk about what tensors are. After all, that is what that's what this is named after. So when we talk about tensors in TensorFlow, TensorFlow is derived from its core component known as a tensor. A tensor is a vector or a matrix of n dimensions that represent all types of data. And you can see here we have the scalar, which is just a single number. You have your vector, which is two numbers. Might be a number in a direction. You have a simple matrix, and then we get into the tensor. I mentioned how a picture is a very complicated tensor because it has your XY coordinates, and then each one of those pixels has 3 to 4 channels for your different colors. And so each image coming in would be its own tensor. And in TensorFlow, tensors are defined by a unit of dimensionality called as rank. And you can see here we have our scalar, which is a single number that has a rank of 0 because it has no real dimensions to it other than it's just a single point. And then you have your vector, which would be a single list of numbers. So that's a rank 1. Matrix would have rank 2. And then as you can see right here as we get into the full tensor, it has a rank 3. And so the next step is to understand how a TensorFlow works. And if you haven't looked at the basics of a neural network and reverse propagation, that is the basics of TensorFlow, and then it goes through a lot of different options and properties that you can build into your different tensors. So a TensorFlow performs computations with the help of data flow graphs. It has nodes that represent the operations in your model. And if you look at this, you should see a neural network going on here. We have our inputs, B, C, and D, and you might have x equals b plus c, y equals d minus 4, a equals x times y, and then you have an output. And so even though this isn't a neural network here, it's just a simple set of computations going across, you can see how the more complicated it gets, the more it can actually, one of the tensors is a neural network with reverse propagation, but it's not limited to that. There's so much more you can do with it. And this here is just a basic flow of computations of the data going across. And you can see we can plug in the numbers, b equals 4, c equals 3, d equals 6, and you get x equals 4 plus 3, so x equals 7, y equals 6 minus 4, so y equals 2, and finally a equals 7 times 2, or a equals 14. Like I said, this is a very simplified version of how TensorFlow works. Each one of these layers can get very complicated. But TensorFlow does such a nice job that you can spin different setups up very easily and test them out. So you can test out these different models to see how they work. Now, TensorFlow has gone through two major stages. We had the original TensorFlow release of 1.0, and then they came out with the 2.0 version. And the 2.0 addressed so many things out there that the 1.0 really needed. So when we start talking about TensorFlow 1.0 versus 2.0, I guess you would need to know this for a legacy programming job if you're pulling apart somebody else's code. The first thing is that TensorFlow 2.0 supports eager execution by default. It allows you to build your models and run them instantly. And you can see here from TensorFlow 1 to TensorFlow 2, we have almost double the code to do the same thing. So if I want to do with tf.session or TensorFlow session as a session, the session run, you have your variables, your session run, you have your tables initializer, and then you do your model fit. X train, Y train, and then your validation data, your X value, Y value, and your epochs and your batch size. All that goes into the fit. And you can see here where that was all just compressed to make it run easier. You can just create a model and do a fit on it, and you only have like that last set of code on there, so it's automatic. That's what they mean by the eager. So if you see the first part and you're like, what the heck is all this session thing going on? That's TensorFlow 1.0. And then when you get into 2.0, it's just nice and clean. If you remember from the beginning, I said Keras on our list up there. And Keras is the high-level API in TensorFlow 2.0. Keras is the official high-level API of TensorFlow 2.0. It has incorporated Keras as tf.keras. Keras provides a number of model building APIs such as sequential, functional, and subclassing, so you can choose the right level of abstraction for your project. And we'll hopefully touch base a little bit more on this, sequential being the most common form. That is, your layers are going from one side to the other. So everything's going in a sequential order. Functional is where you can split the layers. So you might have your input coming on one side, it splits into two completely different models, and then they come back together. And one of them might be doing classification, the other one might be doing just linear regression kind of stuff, or a basic reverse propagation neural network, and then those all come together into another layer, which is your neural network reverse propagation setup. Subclassing is the most complicated as you're building your own models, and you can subclass your own models into Keras. So very powerful tools here. This is all the stuff that's been coming out currently in the TensorFlow Keras setup. A third big change we're going to look at is that in TensorFlow 1.0, in order to use TF layers as variables, you would have to write TF variable block. So you'd have to predefine that. In TensorFlow 2, you just add your layers in under the sequential, and it automatically defines them as long as they're flat layers. Of course, this changes a little bit as the more complicated tensor you have coming in, but all of it's very easy to do, and that's what 2.0 does a really good job of. And here we have a little bit more on the scope of this, and you can see how TensorFlow 1 asks you to do these different layers and values. If you look at the scope and the default name, you start looking at all the different code in there to create the variable scope. That's not even necessary in Tensor 2.0. So you'd have to do one before you do what you see the code in 2.0. In 2.0, you just create your model. It's a sequential model, and then you can add all your layers in. You don't have to pre-create the variable scope. So if you ever see the variable scope, you know that came from an older version. And then we have the last two, which is our API cleanup and the autograph. In the API cleanup, TensorFlow 1, you could build models using TF-GANs, TF-app, TF-contrib, TF-flags, etc. In TensorFlow 2, a lot of APIs have been removed. And this is they just cleaned them up because people weren't using them, and they've simplified them. And that's your TF-app, your TF-flags, and your TF-logging are all gone. So those are three legacy features that are not in 2.0. And then we have our TF function and autograph feature. In the old version, TensorFlow 1.0, the Python functions were limited and could not be compiled or exported, re-imported. So you were continually having to redo your code, and you couldn't very easily just put a pointer to it and say, hey, let's reuse this. In TensorFlow 2, you can write a Python function using the TF function to mark it for the JIT compilation, for the Python JIT. so that TensorFlow runs it as a single graph. Autograph feature of TF function helps to write graph code using natural Python syntax. Now we just threw in a new word in you, graph. Graph is not a picture of a person. You'll hear graph X and some other things. Graph is what are all those lines that are connecting different objects. So if you remember from before, where we had the different layers going through sequentially, each one of those white lined arrows would be a graph X. That's where that computation is taken care of, and that's what they're talking about. And so if you had your own special code or Python way that you're sending that information forward, you can now put your own function in there instead of using whatever function they're using. In neural networks, this would be your activation function, although it could be almost anything out there depending on what you're doing. Next, let's go for hierarchy and architecture, and then we'll cover 3 basic tools in TensorFlow before we roll up our sleeves and dive into the example. So let's just take a quick look at TensorFlow toolkits and their hierarchy. At the high level, we have our object-oriented API. So this is what you're working with. You have your TF Keras, you have your estimators. This sits on top of your TF layers, TF losses, TF metrics. So you have your reusable libraries for model building. This is really where TensorFlow shines, is between the Keras, running your estimators, and then being able to swap in different layers. Your losses, your metrics, all of that is so built into TensorFlow. It makes it really easy to use. And then you can get down to your low-level TF API. You have extensive control over this. You can put your own formulas in there, your own procedures or models in there. You could have it split. We talked about that earlier. So with the 2.0, you can now have it split one direction where you do a linear regression model, and then go to the other where it does a neural network. And maybe each neural network has a different activation set on it. And then it comes together into another layer, which is another neural network. So you can build these really complicated models, and at the low level you can put in your own APIs, you can move that stuff around. And most recently we have the TF code can run on multiple platforms. And so you have your CPU, which is basically like on the computer I'm running on, I have 8 cores and 16 dedicated threads. I hear they now have one out there that has over 100 cores. So you have your CPU running, and then you have your GPU, which is your graphics card. And most recently, they also include the TPU setup, which is specifically for TensorFlow models, neural network kind of setup. So now you can export the TF code, and it can run on all kinds of different platforms for the most diverse setup out there. And moving on from the hierarchy to the architecture, in the TensorFlow 2.0 architecture, we have, you can see on the left, this is usually where you start out with, and 80% of your time in data science is spent pre-processing data, making sure it's loaded correctly and everything looks right. So the first level in TensorFlow is going to be your read and pre-processed data, your TF data feature columns. This is going to feed into your TF Keras or your pre-made estimators, and kind of you have your TensorFlow hub that sits on top of there so you can see what's going on. Once you have all that set up, you have your distribution strategy. Where are you going to run it? Are you going to be running it on just your regular CPU? Are you going to be running it with the GPU added in? Like I have a pretty high-end graphics card, so it actually grabs that GPU processor and uses it. Or do you have a specialized TPU set up in there that you paid extra money for? It could be if you're later on, when you're distributing the package, you might need to run this on some really high processors because you're processing it at a server level for let's say you might be processing this at you're distributing it, not the distribution strategy, but you're distributing it into a server where that server might be analyzing thousands and thousands of purchases done every minute. And so you need that higher speed to give them a recommendation or a suggestion so they can buy more stuff off your website. Or maybe you're looking for data fraud analysis working with the banks. You want to be able to run this at a high speed so that when you have hundreds of people sending their transactions in, it says, hey, this doesn't look right. Someone's scamming this person and probably has their credit card. So when we're talking about all those fun things, we're talking about saved model. We were talking about that earlier, where it used to be when you did one of these models, it wouldn't truncate the float numbers the same. And so a model going from one, you build the model on your machine in the office, and then you need to distribute it. And so we have our TensorFlow serving cloud on premium. That's what I was talking about if you're like a banking or something like that. Now they have TensorFlow Lite, so you can actually run a TensorFlow on an Android or an iOS or Raspberry Pi, a little breakout board there. In fact, they just came out with a new one that has a built-in, it's just a little mini TPU with the camera on it, so it can pre-process a video. So you can load your TensorFlow model onto that. Talking about an affordable way to beta test a new product. You have the TensorFlow JS, which is for browser and node server. So you can get that out on the browser for some simple computations that don't require a lot of heavy lifting, but you want to distribute to a lot of endpoints. And now they also have other language bindings. So you can now create your TensorFlow backend, save it, and have it accessed from C, Java, Go, C#, Rust, R, or from whatever package you're working on. So we kind of have an overview of the architecture and what's going on behind the scenes, and in this case, what's going on as far as distributing it. Let's go ahead and take a look at 3 specific pieces of TensorFlow. And those are going to be constants, variables, and sessions. So very basic things you need to know and understand when you're working with the TensorFlow setup. So constants in TensorFlow. In TensorFlow, constants are created using the function constant. In other words, they're going to stay static the whole time, whatever you're working with. The syntax for constant value, dtype 9, shape equals none, name constant, verify shape equals false. That's kind of the syntax you're looking at. And we'll explore this with our hands on a little more in depth. And you can see here we do z equals tf.constant, 5.2, name equals x, dtype is a float. That means that we're never going to change that 5.2. It's going to be a constant value. And then we have our variables in TensorFlow. Variables in TensorFlow are in memory buffers that store tensors. And so we can declare a 2x3 tensor populated by ones. You could also do constants this way, by the way. So you can create an array of ones for your constants. I'm not sure why you do that, but you might need that for some reason. In here we have v equals tf.variables, and then in TensorFlow you have tf.ones, and you have the shape, which is 2, 3, which is then going to create a nice 2x3 array that's filled with ones. And then of course you can go in there and they're variables, so you can change them. It's a tensor, so you have full control over that. And then you of course have sessions in TensorFlow. A session in TensorFlow is used to run a computational graph to evaluate the nodes. And remember, when we're talking about graph or graph X, we're talking about all that information then goes through all those arrows and whatever computations they have that take it to the next node. And you can see down here where we have import TensorFlow as TF. If we do x equals a TF.constant of 10, we do y equals a TF constant of 2.0 or 20.0, and then you can do z equals TF.variable, and it's a TF.add x comma y. And then once you have that set up in there, you go ahead and init your TF global variables initializer with TF session as session. You can do a session run init, and then you print the session run y. And so when you run this, you're going to end up with, of course, the 10 plus 20 is 30. And we'll be looking at this a lot more closely as we actually roll up our sleeves and put some code together. So let's go ahead and take a look at that. And for my coding today, I'm going to go ahead and go through Anaconda, and then I'll use specifically the Jupyter Notebook on there. And of course, this code is going to work whatever platform you choose, whether you're in a notebook, the Jupyter Lab, which is just the Jupyter Notebook but with tabs for larger projects. We're going to stick with Jupyter Notebook. PyCharm, whatever it is you're going to use in here. You have your Spider and your Qt console for different programming environments. The thing to note, it's kind of hard to see, but I have my main Pi 3.6. Right now, when I was writing this, TensorFlow works in Python version 3.6. If you have Python version 3.7 or 3.8, you're probably going to get some errors in there. Might be that they've already updated it and I don't know it and I have an older version. But you want to make sure you're in a Python version 3.6 in your environment. And of course, in Anaconda, I can easily set that environment up. Make sure you go ahead and pip in your TensorFlow, or if you're in Anaconda, you can do Anaconda install TensorFlow to make sure it's in your package. So let's just go ahead and dive in and bring that up. This will open up a nice browser window. I just love the fact I can zoom in and zoom out depending on what I'm working on, making it really easy to adjust demo for the right size. Go under New, and let's go ahead and create a new Python. And once we're in our new Python window, this is going to leave it untitled. Let's go ahead and import. Import TensorFlow as TF. At this point, we'll go ahead and just run it real quick. No errors. Yay! No errors. I do that whenever I do my imports because I invariably will have opened up a new environment and forgotten to install TensorFlow into that environment or something along those lines. So it's always good to double check. And if we're going to double check that, it's also good to know what version we're working with. And we can do that simply by using the version command in TensorFlow, which you should know is probably intuitively the TF dot underscore underscore version underscore underscore. And you know, it always confuses me because sometimes you do TF dot version for one thing, you do TF dot underscore version underscore for another thing. This is a double underscore in TensorFlow for pulling your version out. And it's good to know what you're working with. We're going to be working in TensorFlow version 2.1.0. And I did tell you we were going to dig a little deeper into our constants, and you can do an array of constants. And we'll just create this nice array, a equals tf.constant, and we're just going to put the array right in there, 4361. We can run this, and now that is what a is equal to. And if we want to just double check that, remember we're in Jupyter Notebook, where you can just put the letter A, and it knows that that's going to be print. Otherwise, you'd surround it in print. And you can see it's a TF tensor. It has the shape, the type, and the array on here. It's a 2x2 array. And just like we can create a constant, we can go ahead and create a variable. And this is also going to be a 2x2 array. And if we go ahead and print the v out, we'll run that. And sure enough, there's our TF variable in here. Then we can also, let's just go back up here and add this in here. I could create another tensor, and we'll make it a constant this time. And we'll go ahead and put that in over here. We'll have b TF constant. And if we go ahead and print out v and b, we go ahead and run that. And this is an interesting thing that happens in here. You'll see right here when I print them both out, what happens is it only prints the last one unless you use print commands. So important to remember that in Jupyter Notebooks. But we can easily fix that by go ahead and print and surround v with brackets. And now we can see with the two different variables we have the 3152, which is a variable, and this is just a flat constant, so it comes up as a TF tensor shape 2 kind of 2. And that's interesting to note that this label is a TF.tensor and this is a TF variable. So that's how it's looking in the back end when you're talking about the difference between a variable and a constant. The other thing I want you to notice is that in variable we capitalize the V, and with the constant we have a lowercase c. Little things like that can lose you when you're programming and you're trying to find out, hey, why doesn't this work? So those are a couple little things to note in here. And just like any other array in math, we can do like a concatenate the different values here. And you can see we can take AB concatenated. You just do a tf.concat values, and there's our AB axes on 1. Hopefully you're familiar with axes and how that works when you're dealing with matrices. And if we go ahead and print this out, you'll see right here we end up with a tensor. So let's put it in as a constant, not as a variable. And you have your array 4378 and 6145. It's concatenated the two together. And again, I want to highlight a couple things on this. Our axes equals 1. This means we're doing the columns. So if you had a longer array, like right now we have an array that is like, has a shape 1, whatever it is, 2, 2. Axes 0 is going to be your first one, and axes 1 is going to be your second one. And it translates as columns and rows. If we had a shape, let me just put the word shape here. So you know what I'm talking about, and it's very clear. And this is, I'll tell you what, I spend a lot of time looking at these shapes and trying to figure out which direction I'm going in and whether to flip it or whatever. So you can get lost in which way your matrix is going and which is column, which is rows. Are you dealing with the third axis or the second axis? Axis 1, 0, 1, 2, that's going to be our columns. And if you can do columns, then we also can do rows, and that is simply just changing the concatenate. We'll just grab this one here and copy it. We'll do the whole thing over. Control copy, Control V, and change this from axis 1 to axis 0. And if we run that, you'll see that now we concatenate by row as opposed to column. And you have 4, 3, 6, 1, 7, 8, 4, 7. So it just brings it right down and turns it into rows versus columns. You can see the difference there, your output. This really, you want to look at the output sometimes just to make sure your eyes are looking at it correctly and it's in the format. I find visually looking at it is almost more important than understanding what's going on, because conceptually your mind just too many dimensions sometimes. The second thing I want you to notice is this says a NumPy array. So TensorFlow is utilizing NumPy as part of their format as far as Python's concerned. And so you can treat this output like a NumPy array because it is just that. It's going to be a NumPy array. Another thing that comes up more than you would think is filling one of these with zeros or ones. And so you can see here we just create a tensor tf.zeros, and we give it a shape. We tell it what kind of data type it is. In this case we're doing an integer. And then if we print out our tensor, again we're in Jupyter, so I can just type out tensor, and I run this, you can see I have a nice array of with shape 3, 4 of zeros. One of the things I want to highlight here is integer 32. If I go to the TensorFlow data types, I want you to notice how we have float 16, float 32, float 64, complex. If we scroll down, you'll see the integer down here, 32. The reason for this is that we want to control how many bits are used in the precision. This is for exporting it to another platform. So what would happen is I might run it on this computer where Python does a float to indefinite, however long it wants to. And then we can take it, but we want to actually say, hey, we don't want that high precision. We want to be able to run this on any computer. And so we need to control whether it's a TF float 16. In this case, we did an integer 32. We could also do this as a float. So if I run this as a float 32, that means this has a 32-bit precision. You'll see 0 point whatever. And then to go with zeros, we have ones. If we're going from the opposite side, and so we can easily just create a TensorFlow with ones. And you might ask yourself, why would I want zeros and ones? And your first thought might be to initiate a new tensor. Usually we initiate a lot of this stuff with random numbers because it does a better job solving it. If you start with a uniform set of ones or zeros, you're dealing with a lot of bias. So be very careful about starting a neural network for one of your rows or something like that with ones and zeros. On the other hand, I use this for masking. You can do a lot of work with masking. You can also have, it might be that one tensor row is masked, 0 is false, 1 is true, or whatever you want to do it. And so in that case, you do want to use the zeros and ones. And there are cases where you do want to initialize it with all zeros or all ones, and then swap in different numbers as the tensor learns. So it's another form of control. But in general, you see zeros and ones, you usually are talking about a mask over another array. And just like in NumPy, you can also do reshapes. So if we take our, remember this is shaped 3, 4, maybe we want to swap that to 4, 3. And if we print this out, you will see, let me just go and do that, Control V, let me run that, and you'll see that the order of these is now switched. Instead of 4 across, now we have 3 across and 4 down. And just for fun, let's go back up here where we did the ones, and I'm going to change the ones to tf.randomUniform, and we'll go ahead and just take off, well, we'll go ahead and leave that. We'll go ahead and run this. And you'll see now we have 0.0441, and this way you can actually see how the reshape looks a lot different. 0.041, 0.15, 0.71, and then instead of having this one, it rolls down here to the 0.14. And this is what I was talking about. Sometimes a lot of times you fill these with random numbers. And so this is the random.uniform is one of the ways to do that. Now, I just talked a little bit about this float 32. And all these data types. One of the things that comes up, of course, is recasting your data. So if we have a D-type float 32, we might want to convert these to integers because of the project we're working on. I know one of the projects I've worked on ended up wanting to do a lot of round off so that it would take a dollar amount or a float value and then have to round it off to a dollar amount. So we only wanted 2 decimal points. And in which case you have a lot of different options. You can multiply by 100 and then round it off or whatever you want to do. There's a lot of, or then convert it to an integer was one way to round it off. Kind of a cheap and dirty trick. So we can take this and we can take the same tensor and we'll go ahead and create a as an integer. And so we're going to take this tensor, we're going to tf.cast it, and if we print tensor, and then we're going to go ahead and print our tensor. Let me just do a quick copy and paste. And when I'm actually programming, I usually type out a lot of my stuff just to double check it. In doing a demo, copy and paste works fine, but sometimes be aware that copy and paste can copy the wrong code over. Personal choice, depends on what I'm working on. And you can see here we took a float 32, 4.6, 4.2, and so on, and it just converts it right down to a integer value. So our integer 32 setup. And you remember we talked about a little bit about reshape as far as flipping it, and I just did 4, 3 on the reshape up here, and we talked about axis 0, axis 1. One of the things that is important to be able to do is to take one of these variables. We'll just take this last one, tensor as integer, and I want to go ahead and transpose it, and so I can do we'll do a equals tf.transpose, and we'll do our tensor integer in there, and then if I print the a out and we run this, you'll see that's the same array, but we've flipped it so that our columns and rows are flipped. This is the same as reshaping. So when you transpose, you're just doing a reshape. What's nice about this is that if you look at the numbers, the columns, when we went up here and we did the reshape, they kind of roll down to the next row. So you're not maintaining the structure of your matrix. So when we do a reshape up here, they're similar, but they're not quite the same. And you can actually go in here and there's settings in the reshape that would allow you to turn it into a transform. So when we come down here, it's all done for you. And so there are so many times you have to transpose your digits that this is important to know that you can just do that. You can flip your rows and columns rather quickly here. And just like NumPy, you can also do your different math functions. We'll look at multiplication. And so we're going to take matrix multiplication of tensors. We'll go ahead and create A as a constant, 5839. And we'll put in a vector V, 4, 2. And we could have done this where they matched, where this was a 2 by 2 array. But instead, we're going to do just a 2 by 1 array. And the code for that is your tf.matmul, so matrix multiplier. And we have A times V, and if we go ahead and run this, let's make sure we print out our AV on there. And if we go ahead and run this, you'll see that we end up with 36 by 30. And if it's been a while since you've seen the matrix math, this is 5 times 4 plus 8 times 2. 3 times 4 plus 9 times 2. And that's where we get the 36 and 30. Now, I know we're covering a lot really quickly as far as the basic functionality. So the matrix, or your matrix multiplier, is a very commonly used back-end tool as far as computing different models or linear regression, stuff like that. One of the things is to note is that just like in NumPy, you have all of your different math. So we have our TF math, and if we go in here, we have functions, we have our cosines, absolute, angle, all of that's in here. So all of these are available for you to use in the TensorFlow model. And if we go back to our example, and let's go ahead and pull, let's do some multiplication. That's always good. We'll stick with our AV, our constant A and our vector V. And we'll go ahead and do some bitwise multiplication, and we'll create an AV, which is A times V. Let's go and print that out. And you can see coming across here, we have the 4, 2 and the 5, 8, 3, 9, and it produces 20, 32, 6, 18. And that's pretty straightforward. If you look at it, you have 4 times 5 is 20, 4 times 8 is 32. That's where those numbers come from. We can also quickly create an identity matrix, which is basically your main values on the diagonal being 1s and 0s across the other side. Let's go ahead and take a look and see what that looks like. And we can do, let's do this. So we're going to get the shape. This is a simple way, very similar to your NumPy. You can do a.shape, and it's going to return a tuple, in this case our rows and columns. And so we can do a quick print. We'll do rows. Oops. And we'll do columns. And if we run this, you can see we have 3 rows, 2 columns. And then if we go ahead and create an identity matrix, the script for that, got a wrong button there. The script for that looks like this, where we have the number of rows equals rows, the number of columns equals columns, and D type is a 32. And then if we go ahead and just print out our identity, you can see we have a nice identity column with our ones going across here. Now, clearly we're not going to go through every math module available, but we do want to start looking at this as a prediction model and seeing how it functions. So we're going to move on to a more of a direct setup where you can actually see the full TensorFlow in use. For that, let's go back and create a new setup. And we'll go in here, new Python 3 module. There we go. Bring this out so it takes up the whole window, because I like to do that. Hopefully you made it through that first part and you have a basic understanding of TensorFlow as far as being a series of NumPy arrays. You got your math equations and different things that go into them. We're going to start building a full setup as far as the NumPy, so you can see how Keras sits on top of it and the different aspects of how it works. The first thing we want to do is we're going to go ahead and do a lot of imports. Date times, warnings, SciPy. SciPy is your math, so the back-end scientific math. Warnings, because whenever we do a lot of this, you have older versions, newer versions, and so sometimes when you get warnings, you want to go ahead and just suppress them. We'll talk about that if it comes up on this particular setup. And of course, date time. Pandas, again, is your data frame. Think rows and columns. We import it as PD. NumPy is your numbers array, which of course TensorFlow is integrated heavily with. Seaborn for our graphics, and the Seaborn as SNS is going to be set on top of our Matplot library, which we import as MPL. And then of course we're going to import our Matplot library PyPlot as PLT. And right off the bat, we're going to set some graphic colors. Patch force edge color equals true. The style, we're going to use the 538 style. You can look this all up. When you get into Matplot library, into Seaborn, there are so many options in here. It's just kind of nice to make it look pretty when we start up. That way we don't have to think about it later on. And then we're going to take, we have our MPLRC. We're going to put a patch edge color, dim gray line width. Again, this is all part of our graphics here in our setup. We'll go ahead and do an interactive shell. Node interactivity equals last expression. Here we are, PD for pandas. Options display max columns, so we don't want to display more than 50. And then our Matplot library is going to be inline. This is a Jupyter notebook thing, the Matplot library inline. Then warnings, we're going to filter our warnings, and we're just going to ignore warnings. That way when they come up, we don't have to worry about them. Not really what you want to do when you're working on a major project. You want to make sure you know those warnings and then filter them out and ignore them later on. And if we run this, it's just going to be loading all that into the background. So that's a little back-end kind of stuff. Then what we want to go ahead and do is we want to go ahead and import our specific packages that we're going to be working with, which is under Keras. Now remember, Keras kind of sits on TensorFlow. So when we're importing Keras and the sequential model, we are in effect importing TensorFlow underneath of it. We just brought in the math, probably should have put that up above. And then we have our Keras models. We're going to import sequential. Now if you remember from our slide, there was 3 different options. Let me just flip back over there so we can have a quick recall on that. And so in Keras, we have sequential, functional, and subclassing. So remember those 3 different setups in here we talked about earlier. And if you remember from here, we have sequential, where it's going one TensorFlow layer at a time. You go kind of think of it as going from left to right or top to bottom or whatever direction it's going in. But it goes in one direction all the time. Where functional can have a very complicated graph of directions. You can have the data split into 2 separate tensors, and then it comes back together into another tensor, all those kinds of things. And then subclassing is really the really complicated one, where now you're adding your own subclasses into the tensor to do external computations right in the middle of like a huge flow of data. But we're going to stick with sequential. It's not a big jump to go from sequential to functional. But we're running a sequential TensorFlow. And that's what this first import is here. We want to bring in our sequential. And then we have our layers. And let's talk a little bit about these layers. This is where Keras and TensorFlow really are happening. This is what makes them so nice to work with, is all these layers are pre-built. So from Keras, we have layers import dense. From Keras, layers import LSTM. When we talk about these layers, Keras has so many built-in layers. You can do your own layers. The dense layer is your standard neural network. By default, it uses ReLU for its activation. And then the LSTM is a long short-term memory layer. Since we're going to be looking probably at sequential data, we want to go ahead and do the LSTM. And if we go into Keras and we look at their layers, this is the Keras website, you can see as we scroll down for the Keras layers that are built in, we can get down here and we can look at, let's see, here we have our layer activation, our base layers. Activation, layer weight, so it's a lot of stuff in here. We had the ReLU, which is the basic activation that was listed up here for layer activations. You can change those. And here we have our core layers and our dense layers. So you have an input layer, a dense layer, and then we've added a more customized one with the long-term, short-term memory layer. And of course, you can even do your own custom layers in Keras. There's a whole functionality in there if you're doing your own thing. What's really nice about this is it's all built in. Even the convolutional layers, this is for processing graphics. There's a lot of cool things in here you can do. This is why Keras is so popular. It's open source, and you have all these tools right at your fingertips. So from Keras, we're just going to import a couple layers, the dense layer and the long short-term memory layer. And then, of course, from sklearn, our scikit, we want to go ahead and do our min-max scaler, standard scaler for pre-editing our data, and then metrics just so we can take a look at the errors and compute those. Let me go ahead and run this, and that just loads it up. We're not expecting anything from the output. And our file coming in is going to be airquality.csv. Let's go ahead and take a quick look at that. This is in OpenOffice. It's just a standard, you can do Excel, whatever you're using for your spreadsheet. And you can see here we have a number of columns, a number of rows. It actually goes down to like 8,000. The first thing we want to notice is that the first row is kind of just a random number put in going down. Probably not something we're going to work with. The second row is Bandung. I'm guessing that's a reference for the profile. If we scroll to the bottom, which I'm not going to do because it takes forever to get back up, they're all the same. The same thing with the status. The status is the same. We have a date, so we have a sequential order here. Here is the gem, which I'm going to guess is the timestamp on there. So we have a date and time. We have our O3, CO, NO2 reading, SO2, NO, CO2, VOC, and then some other numbers here, PM1, PM2.5, PM4, PM10. 10 without actually looking through the data. I mean, some of this I can guess is like temperature, humidity. I'm not sure what the PMs are. But we have a whole slew of data here. So we're looking at air quality as far as an area and a region and what's going on with our date timestamps on there. And so code-wise, we're going to read this into a pandas data frame. So our data frame, DF is a nice abbreviation commonly used for data frames, equals pd.read_csv, and then the path to it just happens to be on my D drive, separated by spaces. And so if we go ahead and run this, we'll print out the head of our data. And again, this looks very similar to what we were just looking at. Being in Jupyter, I can take this and go the other way. Make it real small so you can see all the columns going across and we can get a full view of it. Or we can bring it back up in size. That's pretty small on there. Overshot. But you can see it's the same data we were just looking at. We're looking at the number, we're looking at the profile, which is the Bandung, the date, we have a timestamp, our O3 count, CO, and so forth on here. And this is just your basic printing out the top 5 rows. We could easily have done 3 rows, 5 rows, 10, whatever you want to put in there. By default, that's 5 for pandas. Now, I talk about this all the time, so I know I've already said it at least once or twice during this video. Most of our work is in pre-formatting data. What are we looking at? How do we bring it together? So we want to go ahead and start with our date time. It's come in 2 columns. We have our date here, and we have our time. And we want to go ahead and combine that. And then we have, this is just a simple script in there that says combine date time. That's our formula we're building. We're going to submit our pandas data frame and the tab name. When we go ahead and do this, that's all of our information that we want to go ahead and create. And then goes for I in range DF shape 0. So we're going to go through the whole setup, and we're going to list tab append DF location I. And here is our date going in there, and then return the numpy array list tab dtypes date time 64. That's all we're doing. We're just switching this to a date timestamp. And if we go ahead and do df date time equals combine date time, and then I always like to print. We'll do df head just so we can see what that looks like. And so when we come out of this, we now have our setup on here, and of course it's edited on to the far right. Here's our date time. You can see the format's changed. So we've added in the date time column, and we've brought the date over, and we've taken this format here, and it's an actual variable with a 000 on here. Well, that doesn't look good. So we need to also include the time part of this, and we want to convert it into hourly data. So let's go ahead and do that. To do that, to finish combining our date time, let's go ahead and create a little script here to combine the time in there. Same thing we just did. We're just creating a numpy array, returning a numpy array, and forcing this into a date time format. And we can actually spend hours just going through these conversions. How do you pull it from the pandas data frame? How do you set it up? So I'm kind of skipping through it a little fast because I want to stay focused on TensorFlow and Keras. Keep in mind, this is like 80% of your coding when you're doing a lot of this stuff is going to be reformatting these things, resetting them back up so that it looks right on here. And, it just takes time to get through all that. But that is usually what the companies are paying you for. That's what the big bucks are for. And we want to go ahead and a couple things going on here is we're going to go ahead and do our date time. We're going to reorganize some of our setup in here, convert into hourly data. Let me just put a pause in there. Now remember, we can select from DF our different columns we're going to be working with, and you're going to see that we actually dropped a couple of the columns. Those ones I showed you earlier, they're just repetitive data. So there's nothing in there that exciting. And then we want to go ahead and we'll create a second data frame here. Let me just get rid of the DF head. And DF2 is we're going to group by date time, and we're looking at the mean value. And then we'll print that out so you can see what we're talking about. We have now reorganized this, so we put in date time, O3, CO. So now this is in the same order as it was before. And you'll see the date time now has our 00, same date, 1, 2, 3, and so on. So it's grouped the data together so that it's a lot more manageable and in the format we want, and in the right sequential order. And if we go back to, there we go, our air quality, you can see right here we're looking at these columns going across. We really don't need, since we're going to create our own date time column, we can get rid of those. These are the different columns of information we want, and that should reflect right here in the columns we picked coming across. So this is all the same columns on there. That's all we've done is reformatted our data, grouped it together by date, and then you can see the different data coming out set up on there. And then as a data scientist, first thing I want to do is get a description. What am I looking at? And so we can go ahead and do the df2 describe, and this gives us our describe gives us our basic data analytics information we might be looking for, like what is the mean, standard deviation, minimum amount, maximum amount. We have our first quarter, second quarter, and third quarter numbers also in there. So you can get a quick look at a glance describing the data, or descriptive analysis. And even though we have our quantile information in here, we're going to dig a little deeper into that. We're going to calculate the quantile for each variable. We're going to look at a number of things for each variable. We'll see right here, Q1, we can simply do the quantile 0.25%, which should match our 25% up here. And we're going to be looking at the min, the max, and we're just going to do this. It's basically we're breaking this down for each different variable in there. One of the things that's kind of fun to do, we're going to look at that in just a second. Let me put the next piece of code in here. We got to clean out some of our, we're going to drop a couple things, our last rows and first row, because those usually they have a lot of null values, and the first row is just our titles. So that's important. It's important to drop those rows in here. And so this right here, as we look at our different quantiles, again, it's the same, we're still looking at the 25 quantile here. We're going to do a little bit more with this. So now that we've cleared off our first and last rows, we're going to go ahead and go through all of our columns, and this way we can look at each column individually. And so we'll just create a Q1, Q3, min, max, min IQR, max IQR, and calculate the quantile of I of DF2. We're basically doing the math that they did up here, but we're splitting it apart. That's all this is. And this happens a lot because you might want to look at individual. If this was my own project, I would probably spend days and days going through what these different values mean. One of the biggest data science things we can look at that's important is use your common sense. If you're looking at this data and it doesn't make sense, and you go back in there and you're like, wait a minute, what the heck did I just do? At that point, you probably should go back and double check what you have going on. Now, we're looking at this, and you can see right here, here's our attribute for our O3. So we've broken it down. We have our Q1 5.88, Q3 10.37. If we go back up here, here's our 5.8. We've rounded it off. 10.37's in there. So we've basically done the same math, just split it up. We have our minimum and our max IQR, and that's computed, let's see, where is it? Here we go. Q1 minus 1.5 times IQR. And the IQR is your Q3 minus Q1. So that's the difference between our two different quarters. And this is all data science. As far as the hard math, we're really not, we're actually trying to focus on Keras and TensorFlow. You still got to go through all this stuff. I told you 80% of your programming is going through and understanding what the heck happened here. What's going on? What does this data mean? And so when we're looking in that, we're going to go ahead and say, hey, we've computed these numbers, and the reason we've computed these numbers is if you take the minimum value and it's less than your minimum IQR, that means something's going wrong there. And that usually, in this case, is going to show us an outlier. So we want to go ahead and find the minimum value. If it's less than the minimum IQR, it's an outlier. And if the max value is greater than the max IQR, we have an outlier. And that's all this is doing. Low outlier is found, minimum value, high outlier is found, really important, actually. Outliers are almost everything in data sometimes. Sometimes you do this project just to find the outliers because you want to know crime detection. What are we looking for? We're looking for the outliers. What doesn't fit a normal business deal? And then we'll go ahead and throw in, just threw in a lot of code. Oh my goodness. So we have, if your max is greater than IQR, print outlier is found. What we want to do is we want to start cleaning up these outliers. And so we want to convert, create a convert nan, x max IQR equals max underscore IQR, min IQR equals min IQR. So this is just saying this is the data we're going to send. That's all that is in Python. And if x is greater than the max IQR and x is less than the min IQR, x equals null. We're going to set it to null. Why? Because we want to clear these outliers out of the data. Now, again, if you're doing fraud detection, you would do the opposite. You would be cleaning everything else that's not in that series so that you can look at just the outlier. And then we're going to convert the nan hum. Again, we have x max IQR is 100%, min IQR is min IQR. If x is greater than max IQR and x is less than min IQR, again, we're going to return a null value. Otherwise, it's going to remain the same value x equals x. And you can see as we go through the code, if I equals our HUM, then we go ahead and do, that's a column specific to humidity. That's your HUM column. Then we're going to go ahead and run a map on there and convert the non-HUM. You can see here this is just cleanup. We found out that humidity probably has some weird values in it. We have our outliers. That's all this is. And so when we go ahead and finish this and we take a look at our outliers and we run this code here, we have a low outlier, 2.04. We have a high outlier, 99.06. Outliers have been interpolated. That means we've given them a new value. Chances are these days when you're looking at something like these sensors coming in, they probably have a failed sensor in there. Something went wrong. That's the kind of thing that you really don't want to do your data analysis on. So that's what we're doing, is we're pulling that out and then converting it over and setting it up method linear. So we interpolate method linear is it's going to fill that data in based on a linear regression model of similar data. Same thing with this up here with the df2i interpolate. That's what we're doing. Again, this is all data prep. We're not actually talking about TensorFlow. We're just trying to get all our data set up correctly so that when we run it, it's not going to cause problems or have a huge bias. So we've dealt with outliers specifically in humidity. And again, this is one of these things where when we start running, we ran through this, you can see down here that we have our outliers found, high-low outliers, migrated them in. We also know there's other issues going on with this data. How do we know that? Some of it's just looking at the data, playing with it until you start understanding what's going on. Let's take the temp value, and we're going to go ahead and use a logarithmic function on the temp value. And it's interesting because it's like, how do you heck do you even know to use logarithmic on the temp value? That's domain specific. We're talking about being an expert in air care. I'm not an expert in air care. It's not what I go look at. I don't look at air care data. In fact, this is probably the first air care data setup I've looked at. But the experts come in there and they come to you and say, hey, in data science, this is a exponentially variable on here, so we need to go ahead and do transform it and use a logarithmic scale on that. So at that point, that would be coming from your data. Here we go. Data science programmer overview, does a lot of stuff connecting the database and connecting in with the experts. Data analytics, a lot of times you're talking about somebody who is a data analysis, might be all the way usually a PhD level. Data science, programming level interfaces, database manager, that's going to be the person who's your admin working on it. So when we're looking at this, we're looking at something they've sent to me and they said, hey, domain, air care, this is a skew because the data just goes up exponentially and affects everything else. And we'll go ahead and take that data. Let me just go ahead and run this. Just for another quick look at it, we have our, we'll do a distribution DF. We'll create another data frame from the temp values and then from a data set from the log temp. So we can put them side by side. And we'll just go ahead and do a quick histogram. And this is kind of nice. Plot a figure size. Here's our PLT from Matplot library. And then we'll just do a distribution underscore DF. There's our data frames. This is nice because it just integrates the histogram right into pandas. Love pandas. And this is a chart you would send back to your data analyst and say, hey, is this what you wanted? This is how the data is converting on here. As a data scientist, the first thing I note is we've gone from a 10, 20, 30 scale to 2.5, 3.0, 3.5 scale. And the data itself has kind of been adjusted a little bit based on some kind of a skew on there. So let's jump into, we're getting a little closer to actually doing our Keras on here. We'll go ahead and split our data up. And this, of course, is any good data scientists. You want to have a training set and a test set. And we'll go ahead and do the train size. We're going to use 0.75% of the data. Make sure it's an integer. You don't want to take a slice as a float value. Give you a nice error. And we'll have our train size is 75%, and the test size is going to be, of course, the train size minus the length of the data set. And then we can simply do train comma test. Here's our data set, which is going to be the train size, the test size. And then if we go ahead and print this, let me just go ahead and run this. We can see how these values split. It's a nice split of 1,298 and then 433 points of value that are going to be for our setup on here. And if you remember, we're specifically looking at the data set. Where did we create that data set from? That was from up here. That's what we called the logarithmic value of the temp. That's where the data set came from. So we're looking at just that column with this train size and the test, with the train and test data set here. And let's go ahead and do convert an array of values into a data set matrix. We're going to create a little setup in here. We create our data set. Our data set's going to come in. We're going to do a look back of 1. So we're going to look back one piece of data going backward. And we have our data X and our data Y. For I in range, length of data set, look back -1. This is creating, let me just go ahead and run this. Actually, the best way to do this is to go ahead and create this data and take a look at the shape of it. Let me go ahead and just put that code in here. So we're going to do a look back 1. Here's our train X, our train Y, and it's going to be adding the data on there. And then when we come up here and we take a look at the shape, there we go. And we run this piece of code here. We look at the shape on this, and we have a new, slightly different change on here, but we have a shape of X, 1296, 1, shape of Y, train Y, test X, test Y. And so what we're looking at is that the X comes in, and we're only having a single value out. We want to predict what the next one is. That's what this little piece of code is here for. What are we looking for? Well, we want to look back 1. That's the what we're going to train the data with is yesterday's data. Yesterday says, hey, the humidity was at 97%. What should today's humidity be at? If it's 97% yesterday, is it going to go up or is it going to go down today? If 97, does it go up to 100? What's going on there? And so we're looking forward to the next piece of data, which says, hey, tomorrow's is going to, today's humidity is this. This is what tomorrow's humidity is going to be. That's all that is. All that is stacking our data so that our Y is basically X plus 1, or X could be Y minus 1. And then a couple things to note is our X data. We're only dealing with the one column, but you need to have it in a shape that has it by the columns. So you have the two different numbers. And since we're doing just a single point of data, we have, and you'll see with the train Y, we don't need to have the extra shape on here. Now, this is going to run into a problem. And the reason is that we have what they call a time step. And the time step is that long-term, short-term memory layer. So we're going to add another reshape on here. Let me just go down here and put it into the next cell. And so we want to reshape the input array in the form of sample time step features. We're only looking at one feature. And I mean, this is one of those things when you're playing with this, you're like, why am I getting an error in the numpy array? Why is this giving me something weird going on? So what we're going to do is we're going to add one more level on here. Instead of being 1299.1, we want to go one more. And when they put the code together in the back, you can see we kept the same shape, the 1299. We added the one dimension, and then we have our train X shape 1. And this could have, depends again on how far back in the long short-term memory you want to go. That is what that piece of code is for, and that reshape is. And you can see the new shape is now 1299.11 versus the 1299.1. And then the other part of the shape 432.11. Again, this is our X in, and of course our test X. And then our Y is just a single column because we're just doing one output that we're looking for. So now we've done our 80%. That's all the writing all the code, reformatting our data, bringing it in. Now we want to go ahead and do the fun part, which is we're going to go ahead and create and fit the LSTM neural network. And if we're going to do that, the first thing we need is we're going to need to go ahead and create a model. And we'll do this sequential model. And if you remember, sequential means it just goes in order. That means if you have two layers, the layers go from layer 1 to layer 2, or layer 0 to layer 1. This is different than functional. Functional allows you to split the data and run two completely separate models and then bring them back together. We're doing just sequential on here. And then we decided to do the long short-term memory. And we have our input shape, which it comes in. Again, this is what all this switching was. We could have easily made this 1, 2, 3, or 4 going back as far as the end number on there. We just stuck to going back 1. And it's always a good idea when you get to this point, where the heck is this model coming from? What kind of models do we have available? And let me go ahead and put the next model in there, because we're going to do two models. And the next model is going to go ahead and we're going to do dense. So we have model equals sequential, and then we're going to add the LSTM model, and then we're going to add a dense model. And if you remember from the very top of our code, where we did the imports, oops, there we go, our cross, this is it right here. Here's our importing a dense model, and here's our importing an LSTM. Now, just about every TensorFlow model uses dense. Your dense model is your basic forward propagation, reverse propagation error, where it does reverse propagation to program the model. So any of your neural networks that you've already looked at that looks and says, here's the error, and sends the error backwards, that's what this is. The long short-term memory is a little different. The real question that we want to look at right now is, where do you find these models? What kind of models do you have available? And so for that, let's go to the Keras website, which is the keras.io. If you go under API/layers, and I always have to do a search, just search for Keras API layers. It'll open up and you can see we have your base layers right here, class, trainable, weights, all kinds of stuff like there. Your activation, so a lot of your layers you can switch how it activates. ReLU, which is like your smaller arrays, or if you're doing convolutional neural networks, the convolution usually uses a ReLU. Your sigmoid, all the way up to softmax, softplus, all these different choices as far as how those are set up. And what we want to do is we want to go ahead, and if you scroll down here, you'll see your core layers, and here is your dense layer. So you have an input object, your dense layer, your activation layer, embedding layer. This is your kind of your one setup on there that's most common. Convolutional neural networks, or your convolutional layers, these are like for doing image categorizing, so trying to find objects in a picture, that kind of thing. We have pooling layers, so as you have the layers come together, usually you bring them down into a single layer, although you can still do like global max pooling 3D. And there is just, I mean, this list just goes on and on. There's all kinds of different things hidden in here as far as what you can do. And it changes. You go in here and you just have to do a search for what you're looking for, and figure out what's going to work best for you as far as which project you're working on. Long short-term memory is a big one, because this is when we start talking about text. What if someone says the? What comes after the? The Cat in the Hat, little kid's book there. Starts programming it, and so you really want to know not only what's going on, but it's going to be something that has a history. The history behind it tells you what the next one coming up is. Now, once we've built all our different, we built our model, we've added our different layers we want in there, play with it. Remember, if you're in functional, you can actually link these layers together and they branch out and come back together. If you do the sub setup, then you can create your own different model. You can embed a model in there that might be something linear regression. You can embed a linear regression model as part of your functional split and then have that come back together with other things. So we're going to go ahead and compile your model. This brings everything together. We're going to put in what the loss is, which we'll use the mean squared error, and we'll go ahead and use the atom optimizer. Clearly there's a lot of choices on here depending on what you're doing. And just like any of these different prediction models, if you've been doing any scikit from Python, you'll recognize that we have to then fit the model. So what are we doing in here? We're going to send in our train X, our train Y. We're going to decide how many epochs we're going to run it through. 500 is probably a lot for this. I'm guessing it'd probably be about 200 or 300, probably do just fine. Our batch size. So how many different, when you process it, this is the math behind it. If you're in data analytics, you might try to know what this number is as a data scientist, where I haven't had the PhD level math that says this is why you want to use this particular batch size. You kind of play with this number a little bit. You can dig deeper into the math, see how it affects the results depending on what you're doing. And there's a number of other settings on here. We did verbose 2. I'd have to actually look that up to tell you what verbose means. I think that's actually the default on there if I remember correctly. There's a lot of different settings when you go to fit it. The big ones are your epoch and your batch size. Those are what we're looking for. And so we're going to go ahead and run this. And this is going to take a few minutes to run because it's going through 500 times through all the data. So if you have a huge data set, this is the point where you're kind of wondering, oh my gosh, is this going to finish tomorrow? If I'm running this on a single machine and I have a terabyte of data going into it, if this is my personal computer and I'm running a terabyte of data into this, this is running rather quickly through all 500 iterations. But at a terabyte of data, we're talking something closer to days, week, even with a 3.5 gigahertz machine in 8 cores, it's still going to take a long time to go through a full terabyte of data. And then we want to start looking at putting it into some other framework like Spark or something that will be able to process on there more across multiple processors and multiple computers. And if we scroll all the way down to the bottom, you're going to see here's our square mean error of 0.0088. If we scroll way up, you'll see it kind of oscillates between 0.0888 and 0.0089. It's right around 250 where you start seeing that oscillation where it's really not going anywhere. So we really didn't need to go through a full 500 epochs. If you're retraining the stuff over and over again, it's kind of good to note where that error zone is so you don't have to do all the extra processing. Of course, if you're going to build a model, we want to go ahead and run a prediction on it. So let's go ahead and make our prediction. And remember, we have our training test set and our test set, we have the train X and the train Y for training it, or train predict, and then we have our test X and our test Y going in there. So we can test to see how good it did. And when we come in here, we have, you'll see right here, we go ahead and do our train predict equals model predict train X and test predict model predict test X. Why would we want to run the prediction on train X? Well, it's not 100% on its prediction. We know it has a certain amount of error, and we want to compare the error we have on what we programmed it with the error we get when we run it on new data that's never seen, the model's never seen before. And one of the things we can do, we go ahead and invert the predictions. This helps us level it off a little bit more. Get rid of some of our bias. We have train predict equals an NP exponential M1, the train predict, and then train y equals the exponential m1 for train y, and then we do again that with test predict and test y. Again, reformatting the data so that it all matches, and then we want to go ahead and calculate the root mean square error. So we have our train score, which is your math square root times the mean square root error, train y and train predict. And again, we're just this is just feeding the data through so we can compare it. And the same thing with the test. And let's take a look at that, because really the code makes sense if you're going through it line by line. You can see what we're doing, but the answer really helps to zoom in. So we have a train score which is 2.40 of our root mean square error, and we have a test score of 3.16 of the root mean square error. If these were reversed, if our test score is better than our training score, then we've overtrained. Something's really wrong. At that point, you got to go back and figure out what you did wrong. Because you should never have a better result on your test data than you do on your training data. And that's why we put them both through. That's why we look at the error for both the training and the testing. When you're going out and quoting your, publishing this, and you're saying, hey, how good is my model? It's the test score that you're showing people. This is what it did on my test data that the model had never seen before. This is how good my model is. And a lot of times you actually want to put together like a little formal code where we actually want to print that out. And if we print that out, you can see down here, test prediction and standard deviation of data set 3.16 is less than 4.40. I have to go back, and we're up here. If you remember, we did the square means error. This is standard deviation. That's why these numbers are different. It's saying the same thing that we just talked about. 3.16 is less than 4.40. Model is good enough. We're saying, hey, this model is valid. We have a valid model here. So we can go ahead and go with that. And along with putting a formal print out of there, we want to go ahead and plot what's going on. And this, we just want a pretty graph here so that people can see what's going on. When I walk into a meeting and I'm dealing with a number of people, they really don't want these numbers. They don't want to say, hey, standard deviation, unless you know what statistics are. You might be dealing with a number of different departments. Head of sales might not work with standard deviation or have any idea what that really means number-wise. And so at this point, we really want to put it in a graph so we have something to display. And with displaying, you got to remember that we're looking at the data today going into it and what's going to happen tomorrow. So let's take a quick look at this. We're going to go ahead and shift the train predictions for plotting. We have our train predict plot, NP empty like data set, train predict plot, set it up with null values. It's just kind of a weird thing where we're creating the data groups as we like them, and then putting the data in there is what's going on here. So we have our train predict plot, which is going to be our look back, our length, plus look back. Is going to equal train predict. So we're creating this, basically we're taking this and we're dumping the train predict into it. So now we have our nice train predict plot. And then we have the shift test predictions for the plotting. We're going to continue more of that. Oops, looks like I put it in here double. No, it's just, yeah, they put it in here double. Didn't mean to do that. We really only need to do it once. Oh, here we go. This is where the problem is because this is the test predict. So we have our training prediction, we're doing the shift on here, and then the test predict, we're going to look at that. Same thing, we're just creating those two data sets. Test predict plot, length prediction set up on there. And then we're going to go through the plotting, the original data set, and the predictions. So we have a time axis. Always nice to have your time set on there. Set that to the time array, time axis lap. All this is setting up the time variable for the bottom. And then we have a lot of stuff going on here as far as setting up our figure. Let's go ahead and run that, and then we'll break it down. We have on here our main plot. We have two different plots going on here. The ISPU going up and the data, and the ISPU here with all these different settings on it. And so when we look at this, we have our AX1. That's the main plot. Our AX. That's the main plot, and we have our AX1, which is the secondary plot over here. So we're doing a figure PLT, or plt.figure, and we're going to dump those two graphs on there. And so we take, and if you go through the code piece by piece, which we're not going to do, we're going to do the data set here, exponential, reverse exponential, so that it looks correctly. We're going to label it the original data set. We're going to plot the train predict plot. That's what we just created. We're going to make that orange, and we'll label it train prediction. Test predict plot, we're going to make that red and label it test prediction, and so forth. Set our ticks up. This actually just put ticks, time axes gets its ticks. The little marks there going along the axes, that kind of thing. And let's take a look and see what these graphs look like. And these are just kind of fun. You know, when you show up into a meeting and this is the final output and you say, hey, this is what we're looking at. Here's our original data in blue. Here's our training prediction. You can see that it trains pretty close to what the data is up there. I would also probably put a like a little timestamp and do just right before and right after, where we go from train to test prediction. And you can see with the test prediction, the data comes in red. And then you can also see what the original data set looked like behind it and how it differs. And then we can just isolate that here on the right. That's all this is just the test prediction on the right. And it's, you know, you'll see with the original data set, there's a lot of peaks we're missing and a lot of lows we're missing. But as far as the actual test prediction, it does pretty good. It's pretty right on. You can get a good idea of what to expect for your ISPU. And so from this, we would probably publish it and say, hey, this is what you expect, and this is our this is a range of error. That's the kind of thing I'd put out on a daily basis. Maybe we predict the cells are going to be this, or maybe weekly. So you kind of get you kind of flatten the data coming out, and you say, hey, this is what we're looking at. The big takeaway from this is that we're working with, let me go back up here. Whoops, oh, too far. There we go. Is this model here. This is what this is all about. We worked through all of those pieces, all the tensor flows, and that is to build this sequential model. And we're only putting in the 2 layers. This can get pretty complicated. If you get too complicated, it never verges into a usable model. So if you have like 30 different layers in here, there's a good chance you might crash it, kind of thing. So don't go too haywire on that. And that you kind of learn as you go. Again, it's domain knowledge, and also starting to understand all these different layers and what they mean. The data analytics behind those layers is something that your data analysis professional would come in and say, this is what we want to try. But I tell you, as a data scientist, a lot of these basic setups are common, and I don't know how many times working with somebody and they're like, oh my gosh, if I only did a tangent H instead of a ReLU activation, I worked for 2 weeks to figure that out. Well, as a data science, I can run it through the model in 5 minutes instead of spending 2 weeks doing the math behind it. So that's one of the advantages of data scientists, is we do it from programming side, and a data analytics is going to look for it. How does it work in math? And this is really the core right here of TensorFlow and Keras, is being able to build your data model quickly and efficiently. And of course, with any data science, putting out a pretty graph so that your shareholders, again, we want to take and reduce the information down to something people can look at and say, oh, that's what's going on. They can see what's going on as far as the dates and the change in the ISPU.
In this video, I will walk you through the TensorFlow code to perform object detection in a video. So let's get started. This part is basically you're importing all the libraries. We need a lot of these libraries, for example, NumPy, we need image IO, datetime, and pill, and so on and so forth, and of course matplotlib. So we import all these libraries, and then there are a bunch of variables which have some paths for the files and folders. So this is regular stuff. Let's keep moving. Then we import the matplotlib and make it inline, and a few more imports. Alright, and then these are some warnings. We can just ignore them. So if I run this code once again, it will go away. right? And then here onwards we do the model preparation. Now what we're going to do is we are going to use an existing neural network model. So we are not going to train a new one because that really will take a long time, and it needs a lot of computation resources and so on, and it is really not required. There are already models that have been trained, and in this case it is the SSD with MobileNet. That's the model that we are going to use, and this model is trained to detect objects, and it is readily available as open source, so we can actually use this. And if you want to use other models, there are a few more models available, so you can click on this link here, and let me just take you there. There are a few more models, but we have chosen this particular one because this is faster. It may not be very accurate, but that is one of the faster models. But on this link you will see a lot of other models that are readily available. These are trained models. Some of them would take a little longer, but they may be more accurate and so on, so you can probably play around with these other models. Okay, so we will be using that model. So this piece of code, this line, is basically importing that model, and this is also known as frozen model. The term we use is frozen model. So we import, download and import that, and then we will actually use that model in our code. Alright, so these two cells, we have downloaded and imported the model, and then once it is available locally, we will then load this into our program. Alright, so we are loading this into memory, and you need to perform a couple of additional steps, which is basically we need to map the numbers to text. As you may be aware, when we actually build the model and when we run predictions, the model will not give a text. The output of the model is usually a number. So we need to map that to a text. So for example, if the network predicts that the output is 5, we know that 5 means it is an aeroplane. Things like that. So this mapping is done in this next cell. Alright, so let's keep moving. And then we have a helper code which will basically load the data or load the images and transform into NumPy arrays. This is also used in doing object detection in images. So we are actually going to reuse, because video is nothing but it consists of frames, which in turn are images. So we are going to pretty much reuse the same code which we used for doing object detection in images. So this is where the actual detection starts. So here, this is the path for where the images are stored. So this is, here once again we are reusing the code which we wrote for detecting objects in an image. So this is the path where the images were stored, and this is the extension, and this was done for about 2 or 3 images. So we will continue to use this, and if we go down, I'll skip this section. So this is the cell where we are actually loading the video and converting it into frames, and then using frame by frame we are detecting the objects in the image. So in this code, what we are doing basically is there are a few lines of code. What they do is basically once they find an object, a box will be drawn around those each of those objects, and the input file, the name of the input video file is traffic. It is the extension is MP4, and we have this video reader. It's an excellent object which is basically part of this class called image.io, so we can read and write videos using that. And the video that we are going to use is traffic.mp4. You can use any MP4 file, but in our case I picked up video which has like car. So let me just show you. So this is in this object detection folder. I have this MP4 file. I'll just quickly play this video. It's a little slow. Yeah, okay. So here we go. This is the video. It's a short one, relatively small video, so that for this particular demo. And what it will do is, once we run our code, it will detect each of these cars and it will annotate them as cars. So in this particular video, we only have cars. We can later on see with another video. I think I have cat here, so we can also try with that. But let's first check with this traffic video. So let me go back. So we will be reading this frame by frame, and no, actually we will be reading the video file, but then we will be analyzing it frame by frame, and we will be reading them at 10 frames per second. That is the rate we are mentioning here, and analyzing it and then annotating and then writing it back. So you will see that we will have a video file named something like this, traffic_annotated, and we will see the annotated video. So let's go back and run through this piece of code, and then we will come back and see the annotated video. This might take a little while, so I will pause the video after running this particular cell and then come back to show you the results. Alright, so let's go ahead and run it. So it is running now, and it is also important that at the end you close the video writer, so that it is similar to a file pointer. When you open a file, you should also make sure you close it so that it doesn't hog the resources. So it's very similar. So at the end of it, the last piece or last line of code should be video_writer.close. Alright, so I'll pause and then I'll come back. Okay, so I will see you in a little bit. Alright, so now as you can see here, the processing is done. The hourglass has disappeared. That means the video has been processed. So let's go back and check the annotated video. We'll go back to my file manager. So this was the original traffic.mp4, and now you have here traffic_annotated mp4. So let's go and run this and see how it looks. You see here, it has got each of these cars are getting detected. Let me pause and show you. So we pause here. It says car 70%. Let us allow it to go a little further. It detects something on top. What is that? Truck. Okay, so I think because of the board on top, it somehow thinks there is a truck. Let's play some more and see if it detects anything else. So this is again a car, looks like. So let us, yeah, so this is a car, and it has confidence level of 69%. Okay, this is again a car. Alright, so basically till the end it goes and detects each and every car that is passing by. Now we can quickly repeat this process for another video. Let me just show you the other video, which is a cat. Again, there is this cat is not really moving or anything, but it is just standing there staring and moving a little slowly, and our application will, our network will detect that this is a cat, and even when the cat moves a little bit in the other direction, it will continue to detect and show that it is a cat. Okay, so yeah, so this is how the original video is. Let's go ahead and change our code to analyze this one and see if it detects, our network detects this cat. Close this, here we go, and I'll go back to my code. All we need to do is change this traffic to cat. The extension, it will automatically up because it is given here, and then it will run through. So very quickly, once again, what it is doing is this video reader, video_reader, has a neat little feature or interface whereby you can say for frame in video_reader. So it will basically provide frame by frame. So you're in a loop frame by frame, and then you take that each frame that is given to you, you take it and analyze it as if it is an image, individual image. So that's the way it works. So it is very easy to handle this. Alright, so now let's once again run just this cell. The rest of the stuff remains the same. So I will run this cell again. It will take a little while, so the hourglasses come back. I will pause and then come back in a little while. Alright, so the processing is done. Let's go and check the annotated video. Go here. So we have cat annotated.mp4. Let's play this. Alright, so you can see here it is detecting the cat, and in the beginning you also saw it detected something else here. There looks like it detected one more object. So let's just go back and see what it has detected here. Let's see. Yes. So what is it trying to show here? It's too small, not able to see, but it is trying to detect something. I think it is saying it is a car. I don't know. Alright, okay, so in this video there's pretty much only one object, which is the cat, and let's wait for some time and see if it continues to detect it when the cat turns around and moves as well. Just in a little bit. That's going to happen, and we will see. There we go. And in spite of turning the other way, I think our network is able to detect that it is a cat. So let me freeze and then show here. It is actually still continues to detect it as a cat. Alright, so that's pretty much it. I think that's the only object that it detects in this particular video. Okay, so close this. So that's pretty much it.
In this video, we will learn about an important popular deep learning neural network called generative adversarial networks. Yann LeCun, one of the pioneers in the field of machine learning and deep learning, described it as the most interesting idea in the last 10 years in machine learning. In this video, you will learn about what are generative adversarial networks and look in brief at generator and discriminator. Then, we'll understand how GANs work and the different types of GANs. Finally, we'll look at some of the applications of GANs. So let's begin. So what are generative adversarial networks? Generative adversarial networks, or GANs, introduced in 2014 by Ian J. Goodfellow and co-authors, became very popular in the field of machine learning. GAN is an unsupervised learning task in machine learning. It consists of two models that automatically discover and learn the patterns in input data. The two models, called generator and discriminator, compete with each other to analyze, capture and copy the variations within a dataset. GANs can be used to generate new examples that possibly could have been drawn from the original dataset. In the image below, you can see that there is a database that has real 100 rupee notes. The generator, which is basically a neural network, generates fake 100 rupees notes. The discriminator network will identify if the notes are real or fake. Let us now understand in brief about what is a generator. A generator in GANs is a neural network that creates fake data to be trained on the discriminator. It learns to generate plausible data. The generated instances become negative training examples for the discriminator. It takes a fixed length random vector carrying noise as input and generates a sample. Now the main aim of the generator is to make the discriminator classify its output as real. The portion of the GAN that trains the generator includes a noisy input vector, the generator network, which transforms the random input into a data instance, a discriminator network which classifies the generated data, and a generator loss, which penalizes the generator for failing to dolt the discriminator. The backpropagation method is used to adjust each weight in the right direction by calculating the weight's impact on the output. The backpropagation method is used to obtain gradients, and these gradients can help change the generator weights. Now, let us understand in brief what a discriminator is. A discriminator is a neural network model that identifies real data from the fake data generated by the generator. The discriminator's training data comes from two sources. The real data instances, such as real pictures of birds, humans, currency notes, etc., are used by the discriminator as positive samples during the training. The fake data instances created by the generator are used as negative examples during the training process. While training the discriminator, it connects with two loss functions. During discriminator training, the discriminator ignores the generator loss and just uses the discriminator loss. In the process of training the discriminator classifies both real data and fake data from the generator. The discriminator loss penalizes the discriminator for misclassifying a real data instance as fake or a fake data instance as real. Now moving ahead, let's understand how GANs work. Now GANs consists of two networks, a generator which is represented as G of x and a discriminator which is represented as D of x. They both play an adversarial game where the generator tries to fool the discriminator by generating data similar to those in the training set. The discriminator tries not to be fooled by identifying fake data from the real data. They both work simultaneously to learn and train complex data like audio, video or image files. Now you are aware that GANs consists of two networks, a generator G of x and discriminator D of x. Now the generator network takes a sample and generates a fake sample of data. The generator is trained to increase the probability of the discriminator network to make mistakes. On the other hand, the discriminator network decides whether the data is generated or taken from the real sample using a binary classification problem with the help of a sigmoid function that gives the output in the range 0 and 1. Here is an example of a generative adversarial network trying to identify if the 100 rupee notes are real or fake. So first, a noise vector or the input vector is fed to the generator network. The generator creates fake 100 rupee notes. The real images of 100 rupee notes stored in a database are passed to the discriminator along with the fake notes. The discriminator then identifies the notes and classifies them as real or fake. We train the model, calculate the loss function at the end of the discriminator network, and backpropagate the loss into both discriminator and generator. Now the mathematical equation of training a GAN can be represented as, you can see here. Now this is the equation and these are the parameters. Here G represents generator, D represents the discriminator. Now P data of X is the probability distribution of real data. P of Z is the distribution of generator. X is the sample of probability data of X. Z is the sample size from P of Z. D of X is the discriminator network and G of Z is the generator network. Now the discriminator focuses to maximize the objective function such that D of X is close to 1 and Z of Z is close to 0. It simply means that the discriminator should identify all the images from the training set as real, that is 1, and all the generated images as fake, that is 0. The generator wants to minimize the objective function such that D of Z of Z is 1. This means that the generator tries to generate images that are classified as real, that is 1, by the discriminator network. Next, let's see the steps for training a neural network. So we have to first define the problem and collect the data. Then we'll choose the architecture of GAN. Now depending on your problem, choose how your GAN should look like. Then we need to train the discriminator on real data. Now that will help us predict them as real for n number of times. Next, you need to generate fake inputs for the generator. After that, you need to train the discriminator on fake data to predict the generated data as fake. Finally, train the generator on the output of discriminator. With the discriminator predictions available, train the generator to fool the discriminator. Let us now look at the different types of GANs. So first we have vanilla GANs. Now vanilla GANs have min-max optimization formula that we saw earlier, where the discriminator is a binary classifier and is using sigmoid cross entropy loss during optimization. In vanilla GANs, the generator and the discriminator are simple multi-layer perceptrons. The algorithm tries to optimize the mathematical equation using stochastic gradient descent. Up next, we have deep convolutional GANs or DC GANs. Now DC GANs support convolutional neural networks instead of vanilla neural networks at both discriminator and generator. They are more stable and generate higher quality images. The generator is a set of convolutional layers with fractional strided convolutions or transpose convolutions, so it unsamples the input image at every convolutional layer. The discriminator is a set of convolutional layers with strided convolutions, so it downsamples the input image at every convolutional layer. Moving ahead, the third type we have is conditional GANs or CGANs. Vanilla GANs can be extended into conditional models by using an extra label information to generate better results. In CGAN, an additional parameter called Y is added to the generator for generating the corresponding data. Labels are fed as input to the discriminator to help distinguish the real data from fake data generated. Finally, we have super resolution GANs. Now SR GANs use deep neural networks along with adversarial neural network to produce higher resolution images. Super resolution GANs generate a photorealistic high resolution image when given a low resolution image. Let's look at some of the important applications of GANs. So with the help of DC GANs, you can train images of cartoon characters for generating faces of anime characters and Pokemon characters as well. Next, GANs can be used on the images of humans to generate realistic faces. The faces that you see on your screens have been generated using GANs and do not exist in reality. Third application we have is GANs can be used to build realistic images from textual descriptions of objects like birds, humans, and other animals. We input a sentence and generate multiple images fitting the description. Here is an example of a text-to-image translation using GANs for a bird with a black head, yellow body, and a short beak. The final application we have is creating 3D objects. So GANs can generate 3D models using 2D pictures of objects from multiple perspectives. GANs are very popular in the gaming industry. GANs can help automate the task of creating 3D characters and backgrounds to give them a realistic feel.
So we're going to dive right into what is Keras. We'll also go all the way through this into a couple of tutorials because that's where you really learn a lot, is when you roll up your sleeves. So when we talk about what is Keras, Keras is a high-level deep learning API written in Python for easy implementation of neural networks. It uses deep learning frameworks such as TensorFlow, PyTorch, etc. as backend to make computation faster. And this is really nice because as a programmer, there is so much stuff out there and it's evolving so fast, it can get confusing. And having some kind of high-level order in there where you can actually view it and easily program these different neural networks is really powerful. It's really powerful to have something out really quick and also be able to start testing your models and seeing where you're going. So Keras works by using complex deep learning frameworks such as TensorFlow, PyTorch, MLPlade, etc. as a backend for fast computation, while providing a user-friendly and easy-to-learn front-end. And you can see here we have the Keras API specifications, and under that you'd have like TF Keras for TensorFlow, Thano Keras, and so on. And then you have your TensorFlow workflow that this is all sitting on top of. And this is, like I said, it organizes everything. The heavy lifting is still done by TensorFlow or whatever underlying package you put in there. And this is really nice because you don't have to dig as deeply into the heavy end stuff while still having a very robust package you can get up and running rather quickly. And it doesn't distract from the processing time because all the heavy lifting is done by packages like TensorFlow. This is the organization on top of it. So the working principle of Keras. The working principle of Keras is Keras uses computational graphs to express and evaluate mathematical expressions. And you can see here we put them in blue. They have the expression expressing complex problems as a combination of simple mathematical operators, where we have like the percentage, or in this case in Python that's usually your remainder, or multiplication. You might have the operator of x to the power of 0.3. And it is useful for calculating derivatives by using back propagation. So if we're doing with neural networks, when we send the error back up to figure out how to change it, this makes it really easy to do that without really not banging your head and having to hand write everything. It's easier to implement distributed computation, and for solving complex problems, specify input and outputs and make sure all nodes are connected. And so this is really nice as you come in through, is that as your layers are going in there, you can get some very complicated different setups nowadays, which we'll look at in just a second. And this just makes it really easy to start spinning this stuff up and trying out the different models. So when we look at Keras models, Keras model, we have a sequential model. Sequential model is a linear stack of layers where the previous layer leads into the next layer. And this, if you've done anything else, even like the Simplilearn with their neural networks and propagation and any of these setups, this should look familiar. You should have your input layer, it goes into your layer 1, layer 2, and then to the output layer. And it's useful for simple classifier or decoder models. And you can see down here we have the model equals a Keras sequential, and this is the actual code. You can see how easy it is. We have a layer that's dense, your layer 1. As an activation, they're using the ReLU in this particular example. And then you have your name layer 1, layer dense ReLU, name layer 2, and so forth. And they just feed right into each other, so it's really easy just to stack them, as you can see here, and it automatically takes care of everything else for you. And then there's a functional model. And this is really where things are at. This is new. Make sure you update your Keras or you'll find yourself running this, doing the functional model. You'll run into an error code because this is a fairly new release. And it uses multi-input and multi-output model. The complex model which forks into 2 or more branches. And you can see here we have our image inputs equals your Keras input shape equals 32 by 32 by 3. You have your dense layers, dense 64 activation ReLU. This should look similar to what you already saw before, but if you look at the graph on the right, it's going to be a lot easier to see what's going on. You have 2 different inputs. And one way you could think of this is maybe one of those is a small image and one of those is a full-sized image. And that feedback goes into, you might feed both of them into one node because it's looking for one thing, and then only into one node for the other one. And so you can start to get kind of an idea that there's a lot of use for this kind of split and this kind of setup. where you have multiple information coming in, but the information's very different even though it overlaps. And you don't want it to send it through the same neural network. And they're finding that this trains faster and also has a better result depending on how you split the data up and how you fork the models coming down. And so in here we do have the two complex models coming in. We have our image inputs, which is a 32 by 32 by 3 or 3 channels, or 4 if you're having an alpha channel. You have your layers dense is 64 activation using the ReLU, very common. X equals dense inputs, X layers dense X64 activation equals ReLU, X outputs equals layers dense 10X, model equals cross, model inputs equals inputs, outputs equals outputs, name equals minced model. So we add a little name on there. And again, this is this kind of split here. This is setting us up to have the input go into different areas. So if you're already looking at cross, you probably already have this answer. What are neural networks? But it's always good to get on the same page, and for those people who don't fully understand neural networks, to dive into them a little bit or do a quick overview. Neural networks are deep learning algorithms modeled after the human brain. They use multiple neurons, which are mathematical operations, to break down and solve complex mathematical problems. And so just like the neuron, one neuron fires in and it fires out to all these other neurons, or nodes as we call them, and eventually they all come down to your output layer. And you can see here we have the really standard graph: input layer, a hidden layer, and an output layer. One of the biggest parts of any data processing is your data pre-processing. So we always have to touch base on that. With a neural network, like many of these models, they're kind of, when you first start using them, they're like a black box. You put your data in, you train it, and you test it and see how good it was. And you have to pre-process that data, because bad data in is bad outputs. So in data pre-processing, we will create our own data examples set with Keras. The data consists of a clinical trial conducted on 2,100 patients, ranging from ages 13 to 100, with the patients under 65 and the other half over 65 years of age. We want to find the possibility of a patient experiencing side effects due to their age. And you can think of this in today's world with COVID, what's going to happen on there. And we're going to go ahead and do an example of that in our live hands-on. Like I said, most of this you really need to have hands-on to understand. So let's go ahead and bring up our Anaconda, and open that up and open up a Jupyter Notebook for doing the Python code in. Now, if you're not familiar with those, you can use pretty much any of your setups. I just like those for doing demos and showing people, especially shareholders. It really helps because it's a nice visual. So let me go ahead and flip over to our Anaconda. And the Anaconda has a lot of cool tools. They just added Datalore and IBM Watson Studio Cloud into the Anaconda framework. But we'll be in the Jupyter Lab or Jupyter Notebook. I'm going to do Jupyter Notebook for this because I use the lab for like large projects with multiple pieces because it has multiple tabs, where the notebook will work fine for what we're doing. And this opens up in our browser window because that's how Jupyter Notebook is set to run. And we'll go under New, create a new Python 3, and it creates an untitled Python. We'll go ahead and give this a title, and we'll just call this Keras tutorial. And let's change that to capital. There we go. We'll go ahead and just rename that. And the first thing we want to go ahead and do is get some pre-processing tools involved. And so we need to go ahead and import some stuff for that, like our NumPy, do some random number generation. I mentioned sklearn or your scikit. If you're installing sklearn, the sklearn stuff, it's scikit you want to look up. That should be a tool of anybody who is doing data science. If you're not familiar with the sklearn toolkit, it's huge, but there's so many things in there that we always go back to. And we want to go ahead and create some train labels and train samples for training our data. And then just a note of what we're actually doing in here. Let me go ahead and change this. This is kind of a fun thing you can do. We can change the code to Markdown. And then markdown code is nice for doing examples once you've already built this. Our example data, we're going to do experimental. There we go. Experimental drug was tested on 2,100 individuals between 13 to 100 years of age. Half the participants are under 65, and 95% of participants are under 65. Experienced no side effects, while 95% of participants over 65 experienced side effects. So that's kind of where we're starting at. And this is just a real quick example, because we're going to do another one with a little bit more complicated information. And so we want to go ahead and generate our setup. So we want to do for I and range, and we want to go ahead and create, if you look here, we have random integers, train the labels, append. So we're just creating some random data. And let me go ahead and just run that. And so once we've created our random data, and you can certainly ask for a copy of the code from Simplilearn. They'll send you a copy of this, or you can zoom in on the video and see how we went ahead and did our train samples, append, and we're just using this. I do this kind of stuff all the time. I was running a thing on that had to do with errors following a bell-shaped curve on a standard distribution error. And so what do? I generate the data on a standard distribution error to see what it looks like and how my code processes it, since that was the baseline I was looking for. In this, we're just doing generating random data for our setup on here. And we could actually go in, print some of the data up. Let's just do this, print. We'll do train samples, and we'll just do the first 5 pieces of data in there to see what that looks like. And you can see the first 5 pieces of data in our train samples is 49, 85, 41, 68, 19. Just random numbers generated in there. That's all that is. And we generated significantly more than that. Let's see, 50 up here, 1,000. Yeah, so there's 1,000 here. 1,000 numbers we generated. And we could also, if we wanted to find that out, we could do a quick print the length of it. And so, or you could do a shape kind of thing, and if you're using NumPy, although the link for this is just fine. And there we go, it's actually 2,100, like we said in the demo setup in there. And then we want to go ahead and take our labels. Oh, that was our train labels. We also did samples, didn't we? So we could also print, do the same thing. Oh, labels. And let's change this to labels. And labels. And run that just to double check, and sure enough we have 2,100, and they're labeled 10, 10, 10. I guess that's if they have symptoms or not. 1 symptoms, 0 none. And so we want to go ahead and take our train labels and we'll convert it into a NumPy array, and the same thing with our samples. And let's go ahead and run that. And we also shuffle. This is just a neat feature you can do in NumPy right here. Put my drawing thing on, which I didn't have on earlier. I can take the data and I can shuffle it. So we have our, it just randomizes it. That's all that's doing. We've already randomized it, so it's kind of an overkill. It's not really necessary. But if you're doing a larger package where the data is coming in, and a lot of times it's organized somehow, and you want to randomize it just to make sure that the input doesn't follow a certain pattern that might create a bias in your model. And we go ahead and create a scalar. The scalar range, minimum max scalar, feature range 0 to 1. And then we go ahead and scale the scaled train samples. So we're going to go ahead and fit and transform the data so it's nice and scaled. And that is the age. So you can see up here we have 49, 85, 41. We're just moving that so it's going to be between 0 and 1. And so this is true with any of your neural networks. You really want to convert the data to 0 and 1, otherwise you create a bias. So if you have like 100 creates a bias versus the math behind it gets really complicated. If you actually start multiplying stuff, because there's a lot of multiplication and addition going on in there, that higher end value will eventually multiply down, and it will have a huge bias as to how the model fits it, and then it will not fit as well. And then one of the fun things we can do in Jupyter Notebook is that if you have a variable and you're not doing anything with it, and it's the last one on the line, it will automatically print. And we're just going to look at the first 5 samples on here, and so it's going to print the first 5 samples. And you can see, here we go, 0.9195, 0.791, so everything's between 0 and 1. And that just shows us that we scaled it properly and it looks good. It really helps a lot to do these kind of print-ups halfway through. You never know what's going to go on there. I don't know how many times I've gotten down and found out that the data sent to me that I thought was scaled was not. And then I have to go back and track it down and figure it out on there. So let's go ahead and create our artificial neural network. And for doing that, this is where we start diving into TensorFlow and Keras. TensorFlow, if you don't know the history of TensorFlow, it helps to jump into, we'll just use Wikipedia. Be careful, don't quote Wikipedia on these things because you get in trouble. But it's a good place to start. Back in 2011, Google Brain built Disbelief as a proprietary machine learning setup. TensorFlow became the open source for it. So TensorFlow was a Google product, and then it became open sourced, and now it's just become probably one of the de factos when it comes for neural networks as far as where we're at. So when you see the TensorFlow setup, it's got like a huge following. There are some other setups like the Scikit under the sklearn has their own little neural network, but the TensorFlow is the most robust one out there right now. And Keras sitting on top of it makes it a very powerful tool, so we can leverage both the Keras easiness in which we can build a sequential setup on top of TensorFlow. And so in here we're going to go ahead and do our input of TensorFlow, and then we have the rest of this is all Keras here from number 2 down. We're going to import from TensorFlow the Keras connection. And then you have your TensorFlow Keras models, import sequential. It's a specific kind of model. We'll look at that in just a second. If you remember from the files, that means it goes from one layer to the next layer to the next layer. There's no funky splits or anything like that. And then we have from TensorFlow Keras layers, we're going to import our activation and our dense layer. And we have our optimizer atom. This is a big thing to be aware of, how you optimize your data. When you first do it, Atom's as good as any. Atom is usually, there's a number of optimizer out there. There's a couple of main ones, but Atom is usually assigned to bigger data. It works fine. Usually the lower data does it just fine, but Atom is probably the mostly used. But there are some more out there, and depending on what you're doing with your layers, your different layers might have different activations on them. And then finally down here you'll see our setup where we want to go ahead and use the metrics, and we're going to use the TensorFlow Keras metrics for categorical cross entropy, so we can see how everything performs when we're done. That's all that is. A lot of times you'll see us go back and forth between TensorFlow, and then Scikit has a lot of really good metrics also for measuring these things. Again, it's the end of the at the end of the story, how good does your model do? And we'll go ahead and load all that. And then comes the fun part. I actually like to spend hours messing with these things. And 4 lines of code. You're like, you're going to spend hours on 4 lines of code? No, we don't spend hours on 4 lines of code. That's not what we're talking about when I say spend hours on 4 lines of code. What we have here, I'm going to explain that in just a second. We have a model. And it's a sequential model. If you remember correctly, we mentioned the sequential up here where it goes from one layer to the next. And our first layer is going to be our input. It's going to be what they call dense, which is usually it's just dense, and then you have your input and your activation. How many units are coming in? We have 16. What's the shape? What's the activation? And this is where it gets interesting. Because we have in here ReLU, on 2 of these and softmax activation on 1 of these. There are so many different options for what these mean and how they function. How does the ReLU, how does the softmax function? And they do a lot of different things. We're not going to go into the activations in here. That is what really you spend hours doing, is looking at these different activations. And just some of it is just almost like you're playing with it. Like an artist, you start getting a feel for like a inverse tangent activation, or the tan-H activation. Takes up a huge processing amount. So you don't see it a lot. Yet it comes up with a better solution, especially when you're doing when you're analyzing Word documents and you're tokenizing the words. And so you'll see this shift from one to the other because you're both trying to build a better model. And if you're working on a huge data set, it'll crash the system. It'll just take too long to process. And then you see things like softmax. Softmax generates an interesting setup where a lot of these, when you talk about ReLU, oops, let me do this. ReLU, there we go. ReLU has a setup where if it's less than 0, it's 0, and then it goes up. And then you might have what they call lazy setup, where it has a slight negative to it so that the errors can translate better. Same thing with softmax. It has a slight laziness to it so that errors translate better. All these little details make a huge difference on your model. So one of the really cool things about data science that I like is you build your what they call you build to fail. And it's an interesting design setup. Oops, I forgot the end of my code here. The concept of build to fail is you want the model as a whole to work, so you can test your model out. So that you can do, you can get to the end and you can do your, let's see, where was it? Overshot down here. You can test out the quality of your setup on there. And see, where did I do my TensorFlow? Oh, here we go. It was right above me. There we go. We start doing your cross entropy and stuff like that. Is you need a full functional set of code so that when you run it, you can then test your model out and say, hey, it's either this model works better than this model, and this is why. And then you can start swapping in these models. And so when I say I spend a huge amount of time on pre-processing data, it's probably 80% of your programming time. Well, between those two, it's like 80-20. You'll spend a lot of time on the models. Once you get the model down, once you get the whole code and the flow down set, depending on your data, your models get more and more robust as you start experimenting with different inputs, different data streams, and all kinds of things. And we can do a simple model summary here. Here's our sequential, here's our layer, our output, our parameter. This is one of the nice things about Keras is you can see right here, here's our sequential 1 model. Boom, 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 boom. Everything's set and clear and easy to read. So once we have our model built, the next thing we're going to want to do is we're going to go ahead and train that model. And so the next step is, of course, model training. And when we come in here, this a lot of times is just paired with the model because it's so straightforward. It's nice to print out the model setup so you can have a tracking. But here's our model. The keyword in Keras is compile, optimizer atom, learning rate, another term right there that we're just skipping right over that really becomes the meat of the setup is your learning rate. So whoops, I forgot that I had an arrow, but I'll just underline it. A lot of times the learning rate set to 0.01. Depending on what you're doing, this learning rate can overfit and underfit. So you'd want to look up, I know we have a number of tutorials out on overfitting and underfitting that are really worth reading once you get to that point and understanding. And we have our loss, sparse categorical cross entropy. So this is going to tell Keras how far to go until it stops. And then we're looking for metrics of accuracy. So we'll go ahead and run that. And now that we've compiled our model, we want to go ahead and run it, fit it. So here's our model fit. We have our scaled train samples, our train labels, our validation split. In this case, we're going to use 10% of the data for validation. Batch size, another number you kind of play with. Not a huge difference as far as how it works, but it does affect how long it takes to run, and it can also affect the bias a little bit. Most of the time, though, a batch size is between 10 to 100, depending on just how much data you're processing in there. We want to go ahead and shuffle it. We're going to go through 30 epochs and put a verbose of 2. Let me just go ahead and run this. And you can see right here, here's our epoch, here's our training, here's our loss. Now if you remember correctly up here, we set the loss. Let's see, where was it? Compiled our data. There we go, loss. So it's looking at the sparse categorical cross entropy. This tells us that as it goes, how much does the error go down? Is the best way to look at that. And you can see here, the lower the number, the better. It just keeps going down. And vice versa, accuracy we want, let's see, where's my accuracy? Value accuracy at the end. And you can see 0.619, 0.69, 0.74, it's going up. We want the accuracy, would be ideal if it made it all the way to 1. But we also, the loss is more important because it's a balance. You can have 100% accuracy and your model doesn't work because it's overfitted. Again, you want to look up overfitting and underfitting models. And we went ahead and went through 30 epochs. It's always fun to kind of watch your code going. To be honest, I usually the first time I run it, I'm like, oh, that's cool, I get to see what it does. And after the second time of running it, I'm like, I'd like to just not see that. And you can repress those, of course, in your code. Repress the warnings in the printing. And so the next step is going to be building a test set and predicting it now. So here we go. We want to go ahead and build our test set. And we have, just like we did our training set, a lot of times you just split your initial setup. But we'll go ahead and do a separate set on here. And this is just what we did above. There's no difference as far as the randomness that we're using to build this set on here. The only difference is that we already did our scalar up here. Well, that doesn't matter because the data is going to be across the same thing. But this should just be transform down here instead of fit transform. Because you don't want to refit your data on your testing data. There we go. And now we're just transforming it because you never want to transform the test data. Easy mistake to make, especially on an example like this where we're not doing, we're randomizing the data anyway, so it doesn't matter too much because we're not expecting something weird. And then we want to go ahead and do our predictions. The whole reason we built the model is we take our model, we predict, and we're going to do, here's our X-scale data, batch size 10, verbose, and now we have our predictions in here, and we could go ahead and do a, we'll print predictions, and then I guess I could just put down predictions in 5 so we can look at the first 5 of the predictions. And what we have here is we have our age and the prediction on this age versus what we think it's going to be, what we think is going to have symptoms or not. And the first thing we notice is that's hard to read because we really want a yes/no answer. So we'll go ahead and just round off the predictions using the argmax, the numpy argmax for predictions. So it just goes to a 0 or 1, and if you remember, this is a Jupyter Notebook, so I don't have to put the print. I can just put in rounded predictions, and we'll just do the first 5. And you can see here 0, 1, 0, 0, 0. So that's what the predictions are that we have coming out of this, is no symptoms, symptoms, no symptoms, symptoms, no symptoms. And just as we were talking about at the beginning, we want to go ahead and take a look at this. There we go. Confusion matrices for accuracy check. Most important part when you get down to the end of the story, how accurate is your model before you go and play with the model and see if you can get a better accuracy out of it. And for this, we'll go ahead and use the scikit, the sklearn metrics, scikit being where that comes from. Import confusion matrix, some iteration tools, and of course a nice matplot library. That makes a big difference, so it's always nice to have a nice graph to look at. Picture's worth a thousand words. And then we'll go ahead and call it CM for confusion matrix, y true equals test labels, y predict rounded predictions. And we'll go ahead and load in our CM. And I'm not going to spend too much time on the plotting, going over the different plotting code. You can spend, we have whole tutorials on how to do your different plotting on there. But we do have here is we're going to do a plot confusion matrix. There's our CM, our classes, normalized false, title, confusion matrix. CMAP is going to be in blues. And you can see here we have to the nearest CMAP, titles, all the different pieces, whether you put tick marks or not, the marks, the classes, the color bar. So a lot of different information on here as far as how we're doing the printing of the confusion matrix. You can also just dump the confusion matrix into a Seaborn and real quick get an output. It's worth knowing how to do all this when you're doing a presentation to the shareholders. You don't want to do this on the fly. You want to take the time to make it look really nice, like our guys in the back did. And let's go ahead and do this. Forgot to put together our CM plot labels. We'll go ahead and run that. And then we'll go ahead and call the definition for our mapping. And you can see here, plot confusion matrix. That's the little script we just wrote. And we're going to dump our data into it. So our confusion matrix, our classes, title confusion matrix, and let's just go ahead and run that. And you can see here we have our basic setup. No side effects 195, had side effects 200, no side effects that had side effects. So we predicted the 10 of them who actually had side effects, and that's pretty good. I mean, I don't know about you, but you know, that's 5% error on this, and this is because there's 200 here. That's where I get 5% is divide these both by 2 and you get 5 out of 100. You can do the same kind of math up here. Not as quick on the fly because it's 15 and 195, not an easily rounded number. But you can see here where they have 15 people who predicted to have with the no side effects but had side effects kind of setup on there. And these confusion matrix are so important at the end of the day. This is really where you show whatever you're working on comes up, and you can actually show them, hey, this is how good we are or not, how messed up it is. So this was I spent a lot of time on some of the parts, but you can see here is really simple. We did the random generation of data, but when we actually built the model coming up here, here's our model summary, and we just have the layers on here that we built with our model on this, and then we went ahead and trained it and ran the prediction. Now we can get a lot more complicated. Let me flip back on over here because we're going to do another demo. So that was our basic introduction to it. We talked about the oops, here we go. Okay, so implementing a neural network with Keras. After creating our samples and labels, we need to create our Keras neural network model. We will be working with a sequential model which has 3 layers. And this is what we did. We had our input layer, our hidden layers, and our output layers. And you can see the input layer coming in was the age factor. We had our hidden layer, and then we had the output. Are you going to have symptoms or not? So we're going to go ahead and go with something a little bit more complicated. Training our model is a 2-step process. We first compile our model, and then we train it in our training data set. So we have compiling. Compiling converts the code into a form of understandable by machine. We used the atom in the last example, a gradient descent algorithm, to optimize the model, and then we trained our model, which means it let it learn on training data. And I actually had a little backwards there, but this is what we just did. Is if you remember from our code we just had, oops, let me go back here. Here's our model that we created, summarized. We come down here and we compile it. So it tells it, hey, we're ready to build this model and use it. And then we train it. And this is the part where we go ahead and fit our model and put that information in here, and it goes through the training on there. And of course we scaled the data, which was really important to do. And then you saw we did the creating a confusion matrix with Keras. As we are performing classifications on our data, we need a confusion matrix to check the results. A confusion matrix breaks down the various misclassifications as well as correct classifications to get the accuracy. And so you can see here, this is what we did with the true positive, true negative, false negative. And that is what we went over. Let me just scroll down here. On the end, we printed it out, and you can see we have a nice printout of our confusion matrix with the true positive, false negative, true negative. And so the blue ones, we want those to be the biggest numbers because those are the better side. And then we have our false predictions on here as far as this one. So it had no side effects, but we predicted, let's see, no side effects predicting side effects and vice versa.
If getting your learning started is half the battle, what if you could do that for free? Visit Skill Up by Simplilearn. Click on the link in the description to know more.
Now, saving and loading models with Keras. We're going to dive into a more complicated demo. And you're going to say, oh, that was a lot of complication before. Well, if you broke it down, we randomized some data, we created the Keras setup, we compiled it, we trained it, we predicted, and we ran our matrix. So we're going to dive into something a little bit more fun. Is we're going to do a face mask detection with Keras. So we're going to build a Keras model to check if a person is wearing a mask or not in real time. And this might be important if you're at the front of a store. This is something today which is might be very useful as far as some of our, making sure people are safe. And so we're going to look at mask and no mask. And let's start with a little bit on the data. And so in my data I have with a mask, and you can see they just have a number of images showing the people in masks. And again, if you want some of this information, contact Simplilearn, and they can send you some of the information as far as people with and without masks, so you can try it on your own. And this is just such a wonderful example of this setup on here. So before I dive into the mask detection, talking about being in the current with COVID and seeing if people are wearing masks, this particular example I had to go ahead and update to a Python 3.8 version. It might run in a 3.7, I'm not sure. I kind of skipped 3.7 and installed 3.8. So I'll be running in a Python 3.8, and then you also want to make sure your TensorFlow is up to date, because the they call functional layers, that's where they split, if you remember correctly from back. Let's take a look at this. Remember from here, the functional model and a functional layer allows us to feed in the different layers into different nodes into different layers and split them. Very powerful tool, very popular right now in the edge of where things are with neural networks and creating a better model. So I've upgraded to Python 3.8, and let's go ahead and open that up and go through our next example, which includes multiple layers, programming it to recognize whether someone wears a mask or not, and then saving that model so we can use it in real time. So we're actually almost a full end-to-end development of a product here. Of course, this is a very simplified version, and there'd be a lot more to it. You'd also have to do like recognizing whether it's someone's face or not. All kinds of other things go into this. So let's go ahead and jump into that code, and we'll open up a new Python 3. Oops, Python 3. It's working on it. There we go. And then we want to go ahead and train our mask. We'll just call this train mask. And we want to go ahead and train mask and save it. So it's save mask, train mask detection, not to be confused with masking data. A little bit different. We're actually talking about a physical mask on your face. And then from the Keras standpoint, we got a lot of imports to do here. And I'm not going to dig too deep on the imports. We're just going to go ahead and notice a few of them. So we have in here, oops, let me go Alt-D, there we go. Have something to draw with a little bit here. We have our image processing, and the image processing right here, let me underline that, deals with how do we bring images in, because most images are like a square grid, and then each value in there has 3 values for the 3 different colors. Keras and TensorFlow do a really good job of working with that, so you don't have to do all the heavy listening and figuring out what's going to go on. We have the mobile net average pooling 2D. This again is how do we deal with the images and pulling them. Dropout's a cool thing worth looking up. If you haven't, as you get more and more into Keras and TensorFlow, it'll auto drop out certain nodes. That way you'll get a better, the nodes just kind of die. And they find that they actually create more of a bias than a help, and they also add processing time, so they remove them. And then we have our flatten. That's where you take that huge array with the 3 different colors and you find a way to flatten it so it's just a one-dimensional array instead of a 2 by 2 by 3. Dense input, we did that in the other one, so that should look a little familiar. Oops, there we go. Our input, our model, again, these are things we had on the last one. Here's our optimizer with our atom. We have some pre-processing on the input that goes along with bringing in the data in. More pre-processing with image to array, loading the image. This stuff is so nice. It looks like a lot of work, so you have to import all these different modules in here. But the truth is it does everything for you. You're not doing a lot of pre-processing. You're letting the software do the pre-processing. And we're going to be working with setting something to categorical. Again, that's just a conversion from a number to a category. 0, 1 doesn't really mean anything. It's like true, false. Label binarizer, the same thing. We're changing our labels around. And then there's our train, test, split, classification report. Our IM utilities, let me just go ahead and scroll down here a notch for these. This is something a little different going on down here. This is not part of the TensorFlow or the sklearn. This is the scikit setup in TensorFlow above. The paths, this is part of OpenCV, and we'll actually have another tutorial going out with the OpenCV. So if you want to know more about OpenCV, you'll get a glance on it in this software, especially the second piece when we reload up the data and hook it up to a video camera. We're going to do that on this round. But this is part of the OpenCV thing, and you'll see CV2 is usually how that's referenced. But the IM utilities has to do with how do you rotate pictures around and stuff like that, and resize them. And then the matplot library for plotting, because it's nice to have a graph, tells us how good we're doing, and then of course our numpy numbers array and just a straight OS access. Wow, so that was a lot of imports. Like I said, I'm not going to spend, I spent a little time going through them, but we didn't want to go too much into them. And then I'm going to create some variables that we need to go ahead and initialize. We have the learning rate, number of epochs to train for, and the batch size. And if you remember correctly, we talked about the learning rate to the negative 4.00001. A lot of times it's 0.001 or 0.001. Usually it's in that variation depending on what you're doing and how many epochs, and they kind of play with the epochs. The epochs is how many times we're going to go through all the data. Now I have it as 2. The actual setup is for 20, and 20 works great. The reason I have it for 2 is it takes a long time to process. One of the downsides of Jupyter is that Jupyter isolates it to a single kernel. So even though I'm on an 8-core processor with 16 dedicated threads, only one thread is running on this, no matter what. So it doesn't matter. So it takes a lot longer to run, even though TensorFlow really scales up nicely. And the batch size is how many pictures do we load at once and process. Again, those are numbers you have to learn to play with depending on your data and what's coming in. And the last thing we want to go ahead and do is there's a directory with a data set we're going to run. And this just has images of masks and not masks. And if we go in here, you'll see data set. And then you have pictures with masks. They're just images of people with masks on their face. And then we have the opposite. Let me go back up here. without masks. So it's pretty straightforward. They look kind of askew because they tried to format them into very similar setup on there. So they're mostly squares. You'll see some that are slightly different on here. And that's kind of an important thing to do on a lot of these data sets. Get them as close as you can to each other. And we actually will run in this processing of images up here, and the cross layers and importing and dealing with images. It does such a wonderful job of converting these that a lot of it we don't have to do a whole lot with. So you have a couple things going on there. And so we're now going to be, this is now loading the images, and let me see. And we'll go ahead and create data and labels. Here's our here's the features going in, which is going to be our pictures, and our labels going out. And then for categories in our list directory, and if you remember, I just flashed that at you. It had face mask or no face mask. Those are the two options. And we're just going to load into that. We're going to append the image itself and the labels. So we're just going to create a huge array. And you can see right now this could be an issue if you had more data. At some point, thankfully I have a 32 gig hard drive or RAM. Even that, you could do with a lot less of that. Probably under 16 or even 8 gigs would easily load all this stuff. And there's a conversion going on in here. I told you about how we are going to convert the size of the image so it resizes all the images. And that way our data is all identical the way it comes in. And you can see here with our labels, we have without mask, without mask, without mask. The other one would be with mask. Those are the two that we have going in there. And then we need to change it to the one-hot encoding. And this is going to take our, up here we had, what was it, labels and data. We want the labels to be categorical. So we're going to take labels and change it to categorical, and our labels then equal a categorical list. We'll run that. And again, if we do labels and we just do the last or the first 10, let's do the last 10 just because minus 10 to the end. There we go. Just so we can see what the other side looks like. We now have 1. That means they have a mask. 1, 0, 1, 0, so on. 1 being they have a mask, and 0 no mask. And if we did this in reverse, I just realized that this might not make sense if you've never done this before. Let me run this. 0, 1. So 0 is, do they have a mask on? 0. Do they not have a mask on? 1. So this is the same as what we saw up here without mask. 1 equals, the second value is without mask. So with mask, without mask. And that's just with any of your data processing, we can't really, if you have a 0, 1 output, it causes issues as far as training and setting it up. So we always want to use a one-hot encoder if the values are not actual linear value or regression values. They're not actual numbers if they represent a thing. And so now we need to go ahead and do our train X, test X, train Y, test Y, train split test data. And we'll go ahead and make sure it's going to be random, and we'll take 20% of it for testing and the rest for setting it up as far as training their model. This is something that's become so cool. When they're training these sets, they realize we can augment the data. What does augment mean? Well, if I rotate the data around and I zoom in, I zoom out, I rotate it, share it a little bit, flip it horizontally, fill mode, as I do all these different things to the data, it is able to, it's kind of like increasing the number of samples I have. So if I have all these perfect samples, what happens when we only have part of the face, or the face is tilted sideways, or all those little shifts cause a problem if you're doing just a standard set of data. So we're going to create an augment in our image data generator, which is going to rotate, zoom, and do all kinds of cool things. And this is worth looking up, this image data generator and all the different features it has. A lot of times, the first time through my models, I'll leave that out because I want to make sure there's a thing what we call build to fail, which is just cool to know. You build the whole process, and then you start adding these different things in so that you can better train your model. And so we go ahead and run this, and then we're going to load, and then we need to go ahead, and you probably would have gotten an error if you hadn't put this piece in right here. I haven't run it myself because the guys in the back did this. But we take our base model, and one of the things we want to do is we want to do a mobile net v2. And this is a big thing right here. Include the top equals false. A lot of data comes in with a label on the top row. So we want to make sure that that is not the case. And then the construction of the head of the model that will be placed on the top of the base model. We want to go ahead and set that up. And you'll see a warning here. I'm kind of ignoring the warning because it has to do with the size of the pictures and the weights for input shape. So it'll switch things to defaults, just saying, hey, we're going to auto shape some of this stuff for you. You should be aware that with this kind of imagery, we're already augmenting it by moving it around and flipping it and doing all kinds of things to it. So that's not a bad thing in this. But in other data, it might be if you're working in a different domain. And so we're going to go back here, and we have our base model. We're going to do our head model equals our base model output. And what we got here is we have an average pooling 2D, pool size 7.7 head model. Head model flatten, so we're flattening the data. So this is all processing and flattening the images. And the pooling has to do with some of the ways it can process some of the data. We'll look at that a little bit when we get down to the lower level and just processing it. And then we have our dense. We've already talked a little bit about a dense, just what you think about. And then the head model has a dropout of 0.5. What we can do with a dropout, the dropout says that we're going to drop out a certain amount of nodes while training. So when you actually use the model, it will use all the nodes, but this drops certain ones out, and it helps stop biases from forming. So it's really a cool feature in here. They discovered this a while back. We have another dense mode, and this time we're using softmax activation. Lots of different activation options here. Softmax is a real popular one for a lot of things, and so is the ReLU. And we could do a whole talk on activation formulas. And what their different uses are and how they work. When you first start out, you'll use mostly the ReLU and the softmax for a lot of them, just because they're some of the basic setups. It's a good place to start. And then we have our model equals model, inputs equals base model dot input, outputs equals head model. So again, we're still building our model here. We'll go ahead and run that. And then we're going to loop over all the layers in the base model and freeze them so they will not be updated during the first training process. So for layer and base model layers, layers.trainable equals false. A lot of times when you go through your data, you want to kind of jump in partway through. I'm not sure why in the back they did this for this particular example, but I do this a lot when I'm working with series and specifically in stock data. I want it to iterate through the first set of 30 data before it does anything. I would have to look deeper to see why they froze it on this particular one. And then we're going to compile our model. So compiling the model, atom, init, layer, decay, initial learning rate over epochs. And we go ahead and compile. Our loss is going to be the binary cross entropy, which will have that print out. Optimizer for opt, metrics is accuracy. Same thing we had before. Not a huge jump as far as the previous code. And then we go ahead and we've gone through all this, and now we need to go ahead and fit our model. So train the head of the network. Print info training head, run. Now I skipped a little time because you'll see the run time here is at 80 seconds per epoch. It takes a couple minutes for it to get through on a single kernel. One of the things I want you to notice on here while it's finishing the processing is that we have up here our augment going on. So anytime the train X and train Y go in, there's some randomness going on there, and is jiggling it around what's going into our setup. Of course, we're batch sizing it, so it's going through whatever we set for the batch values, how many we process at a time. And then we have the steps per epoch, the train X, the batch size, validation data. Here's our test X and test Y where we're sending that in. And this, again, it's validation. One of the important things to know about validation is when both our training data and our test data have about the same accuracy, that's when you want to stop. That means that our model isn't biased. If you have a higher accuracy on your testing, you've trained it, and your accuracy is higher on your actual test data, then something in there is probably has a bias and it's overfitted. So that's what this is really about right here with the validation data and validation steps. So it looks like let me go ahead and see if it's done processing. It looks like we've gone ahead and gone through 2 epochs. Again, you could run this through about 20 with this amount of data, and it would give you a nice refined model at the end. We're going to stop at 2 because I really don't want to sit around all afternoon, and I'm running this on a single thread. So now that we've done this, we're going to need to evaluate our model and see how good it is, and to do that we need to go ahead and make our predictions. These are our predictions on our test X to see what it thinks are going to be. So now it's going to be evaluating the network, and then we'll go ahead and go down here, and we will need to turn the indexing, because remember it's either 0 or 1. It's 0, 1, 0, 1. So you have 2 outputs: not wearing a mask, not wearing a mask. And so we need to go ahead and take that argument at the end and change those predictions to a 0 or 1 coming out. And then to finish that off, we want to go ahead and let me just put this right in here and do it all in one shot. We want to show a nicely formatted classification report so we can see what that looks like on here. And there we have it. We have our precision. It's 97% with a mask. There's our F1 score, support without a mask, 97%. So that's pretty high setup on there. 3 people are going to sneak into the store who are without a mask and that thinks they have a mask, and there's going to be 3 people with a mask that's going to flag the person at the front to go, oh hey, look at this person, he might not have a mask. That's I guess if it's set up in front of a store. So there you have it. And of course, one of the other cool things about this is if someone's walking into the store and you take multiple pictures of them, this is just it would be a way of flagging, and then you can take that average of those pictures and make sure they match or don't match if you're on the back end. And this is an important step because this is just cool. I love doing this stuff. So we're going to go ahead and take our model and we're going to save it. So model save maskdetector.model. We're going to give it a name. We're going to save the format. In this case, we're going to use the H5 format. And so this model we just programmed has just been saved. So now I can load it up into, say, another program. What's cool about this is, let's say I want to have somebody work on the other part of the program. Well, I just saved the model. They upload the model. Now they can use it for whatever. And then if I get more information and we start working with that, at some point I might want to update this model, make a better model. And this is true of so many things, where I take this model and maybe I'm running a prediction on making money for a company, and as my model gets better, I want to keep updating it, and then it's real easy just to push that out to the actual end user. And here we have a nice graph. You can see the training loss and accuracy as we go through the epochs. We only did only shows just the one epoch coming in here, but you can see right here as the value loss, train accuracy, and value accuracy start switching and they start converging. And you'll hear converging. This is the convergence they're talking about when they say I know when I work in the scikit with sklearn neural networks, this is what they're talking about, a convergence, is our loss and our accuracy come together, and also up here, and this is why I'd run it more than just 2 epochs. As you can see, they still haven't converged all the way. So that would be a cue for me to keep going. But what we want to do is we want to go ahead and create a new Python 3 program. And we just did our train mask. So now we're going to go ahead and import that and use it and show you in a live action. get a view of both myself in the afternoon, along with my background of an office, which is in the middle still of reconstruction for another month. And we'll call this mask detector. And then we're going to grab a bunch of a few items coming in. We have our MobileNet V2 import preprocessing input, because we're still going to need that. We still have our TensorFlow image to array. We have our load model. That's where most of the stuff's going on. This is our CV2 or OpenCV. Again, I'm not going to dig too deep into that. We're going to flash a little OpenCV code at you, and we actually have a tutorial on that coming out. Our NumPy array, our IM utilities, which is part of the OpenCV or CV2 setup. And then we have, of course, time and just our operating system. So those are the things we're going to go ahead and set up on here. And then we're going to create, this takes just a moment. Our module here, which is going to do all the heavy lifting. So we're going to detect and predict a mask. We have frame, FaceNet, MaskNet. These are going to be generated by our OpenCV. We have our frame coming in, and then we want to go ahead and create a mask around the face. So it's going to try to detect the face and then set that up so we know what we're going to be processing through our model. And then there's a frame shape here. This is just our height versus width. That's all HW stands for. They've called it blob, which is a CV2 DNN blob form image frame. So this is reformatting this frame that's going to be coming in literally from my camera. And we'll show you that in a minute, that little piece of code that shoots that in here. And we're going to pass the blob through the network and obtain the face detections. So FaceNet.setImport blob, detections FaceNet forward, print detections shape. So this is what's going on here. This is that model we just created. We're going to send that in there, and I'll show you in a second where that is, but it's going to be under FaceNet. And then we go ahead and initialize our list of faces, their corresponding locations, and the list of predictions from our face mask network. We're going to loop over the detections, and this is a little bit more work than you think as far as looking for different faces. What happens if you have a crowd of faces? So we're looping through the detections and the shapes going through here. And probability associated with the detection. Here's our confidence of detections. We're going to filter out weak detection by ensuring the confidence is greater than the minimum confidence. So we've set it, remember, 0 to 1. So 0.5 would be our minimal confidence, probably is pretty good. And then we're going to put in compute bounding boxes for the object. If I'm zipping through this, it's because we're going to do an OpenCV, and I really want to stick to just the Keras part. And so I'm just kind of jumping through all this code. You can get a copy of this code from Simplilearn and take it apart, or look for the OpenCV coming out. And we'll create a box. The box sets it around the image. Ensure the bounding boxes fall within the dimensions of the frame. So we create a box around what we hope is going to be the face. Extract the face, ROI, convert it from BGR to RGB channel. Again, this is an OpenCV issue. Not really an issue, but it has to do with the order. I don't know how many times I've forgotten to check the order colors when working with OpenCV. Causes all kinds of fun things when red becomes blue and blue becomes red. And we're going to go ahead and resize it, process it, frame it, face frame setup. Again, the face, the CV2 color, we're going to convert it. We're going to resize it, image to array, pre-process the input, pin the face, locate face, start X, start Y, and X. Boy, that was just a huge amount, and I skipped over a ton of it, but the bottom line is we're building a box around the face, and that box, because the OpenCV does a decent job of finding the face, and that box is going to go in there and see, hey, does this person have a mask on it? And so that's what all this is doing on here. And then finally we get down to this where it says predictions equals masknet.predict faces batch size 32. So these different images where we're guessing where the face is are then going to go through and generate an array of faces, if you will, and we're going to look through and say, does this face have a mask on it? And that's what's going right here is our prediction. That's the big thing that we're working for. And then we return the locations and the predictions. The location just tells where on the picture it is, and then the prediction tells us what it is. Is it a mask or is it not a mask? Alright, so we've loaded that all up. So we're going to load our serialized face detector model from disk. And we have the path that it was saved in. Obviously you're going to put it in a different path depending on where you have it or however you want to do it and how you saved it on the last one where we trained it. And then we have our weights path. And so finally our face net, here it is, equals cv2.dnn.readnet prototext path weights path. And we're going to load that up on here. So let me go ahead and run that. And then we also need to, I'll just put it right down here. I always hate separating these things in there. And then we're going to load the actual mask detector model from disk. This is the model that we saved. So let's go ahead and run that on there also. So this is pulling on all the different pieces we need for our model. And then the next part is we're going to open up our video. And this is just kind of fun because it's all part of the OpenCV video setup. And we just put this all in as one. There we go. So we're going to go ahead and open up our video. We're going to start it and we're going to run it until we're done. And this is where we get some real kind of live action stuff, which is fun. This is what I like working about with images and videos, is that when you start working with images and videos, it's all right there in front of you. It's visual and you can see what's going on. So we're going to start our video streaming. This is grabbing our video stream source 0 start. That means it's grabbing my main camera I have hooked up. And then starting video, you're going to print it out. Here's our video source equals 0 start. Loop over the frames from the video stream. Oops, a little redundancy there. Let me close. I'll just leave it. That's how they had it in the code. So while true, we're going to grab the frame from the threaded video stream and resize it to have the maximum width of 400 pixels. So here's our frame. We're going to read it from our visual stream. We're going to resize it. And then we're returning. Remember, we returned from our procedure the location and the prediction. So detect and predict mask. We're sending it the frame. We're sending it the face net and the mask net. So we're sending all the different pieces that say this is what's going through on here. And then it returns our location and predictions, and then for our box and predictions in the location and predictions. And the box is again, this is an OpenCV set that says, hey, this is a box coming in from the location. Because you have the two different points on there. And then we're going to unpack the box and predictions, and we're going to go ahead and do mask without a mask equals prediction. We're going to create our label, no mask. We're going to create color if the label equals mask L00225. And this is going to make a lot more sense when I hit the run button here. But we have the probability of the label. We're going to display the label and bounding box rectangle in the output frame. And then we're going to go ahead and show the output from the frame, CV2 IM show frame. And then the key equals CV2 wait key 1. We're just going to wait till the next one comes through from our feed. And we're going to do this until we hit the stop button pretty much. So are you ready for this? Let's see if it works. We've distributed our model. We've loaded it up into our distributed code here. We've got it hooked into our camera. And we're going to go ahead and run it. And there it goes. It's going to be running, and we can see the data coming down here, and we're waiting for the pop-up. And there I am in my office with my funky headset on. And you can see in the background my unfinished wall, and it says up here, no mask. Oh no, I don't have a mask on. I wonder if I cover my mouth, what would happen? You can see my no mask goes down a little bit. I wish I'd brought a mask into my office. It's up at the house. But you can see here that this says, there's a 95-98% chance that I don't have a mask on. And it's true, I don't have a mask on right now. And this could be distributed. This is actually an excellent little piece of script that you could start, you install somewhere on a video feed on a security camera or something, and then you'd have this really neat setup saying, hey, do you have a mask on when you enter a store or public transportation or whatever it is where they're required to wear a mask. Let me go ahead and stop that. Now, if you want a copy of this code, definitely give us a holler. We will be going into OpenCV in another one, so I skipped a lot of the OpenCV code in here as far as going into detail. Really focusing on the Keras, saving the model, uploading the model, and then processing a streaming video through it so you can see that the model works. We actually have this working model that hooks into the video camera, which is just pretty cool and a lot of fun. So I told you we're going to dive in and really roll up our sleeve and do a lot of coding today. We did the basic demo up above for just pulling in a Keras, and then we went into a Keras model where we pulled in data to see whether someone was wearing a mask or not. So very useful in today's world as far as a fully running application. Welcome to the RNN tutorial. That's the recurrent neural network. So we talk about a feed-forward neural network. In a feed-forward neural network, information flows only in the forward direction, from the input nodes through the hidden layers, if any, and to the output nodes. There are no cycles or loops in the network. And so you can see here we have our input layer. I was talking about how it just goes straight forward into the hidden layers. So each one of those connects and then connects to the next hidden layer, connects to the output layer. And of course we have a nice simplified version where it has a predicted output, and they refer to the input as X a lot of times and the output as Y. Decisions are based on current input, no memory about the past, no future scope. Why recurrent neural network? Issues in feed-forward neural network. So one of the biggest issues is because it doesn't have a scope of memory or time, a feed-forward neural network doesn't know how to handle sequential data. It only considers only the current input. So if you have a series of things, and because 3 points back affects what's happening now, and what your output affects what's happening, that's very important. So whatever I put as an output is going to affect the next one. A feed forward doesn't look at any of that. It just looks at this is what's coming in. And it cannot memorize previous inputs. So it doesn't have that list of inputs coming in. Solution to feed forward neural network. You'll see here where it says recurrent neural network, and we have our X on the bottom going to H, going to Y. That's your feed forward. But right in the middle it has a value C, so there's a whole other process. So it's memorizing what's going on in the hidden layers, and the hidden layers, as they produce data, feed into the next one. So your hidden layer might have an output that goes off to Y, but that output goes back into the next prediction coming in. What this does is this allows it to handle sequential data. It considers the current input and also the previously received inputs. And if we're going to look at general drawings and solutions, we should also look at applications of the RNN. Image captioning. RNN is used to caption an image by analyzing the activities present in it. A dog catching a ball in midair. That's very tough. I mean, we have a lot of stuff that analyzes images of a dog and the image of a ball, but it's able to add one more feature in there that's actually catching the ball in midair. Time series prediction. Any time series problem like predicting the prices of stocks in a particular month can be solved using RNN. And we'll dive into that in our use case and actually take a look at some stock. One of the things you should know about analyzing stock today is that it is very difficult. And if you're analyzing the whole stock, the stock market at the New York Stock Exchange in the U.S. produces somewhere in the neighborhood, if you count all the individual trades and fluctuations by the second, it's like 3 terabytes a day of data. So we're only going to look at one stock. Just analyzing one stock is really tricky. In here, we'll give you a little jump on that, so that's exciting, but don't expect to get rich off of it immediately. Another application of the RNN is natural language processing. Text mining and sentiment analysis can be carried out using RNN for natural language processing. And you can see right here the term natural language processing, when you stream those 3 words together, is very different than if I said processing language naturally. So the time series is very important when we're analyzing sentiments. It can change the whole value of a sentence just by switching the words around. Or if you're just counting the words, you might get one sentiment where if you actually look at the order they're in, you get a completely different sentiment. When it rains, look for rainbows. When it's dark, look for stars. Both of these are positive sentiments, and they're based upon the order of which the sentence is going in. Machine translation. Given an input in one language, RNN can be used to translate the input into a different languages as output. I myself am very linguistically challenged. But if you study languages and you're good with languages, you know right away that if you're speaking English, you would say big cat. And if you're speaking Spanish, you would say cat big. So that translation is really important to get the right order, to get, there's all kinds of parts of speech that are important to know by the order of the words. Here this person is speaking in English and getting translated. And you can see here a person is speaking in English in this little diagram. I guess that's denoted by the flags. I have a flag. I own it. No. But they're speaking in English and it's getting translated into Chinese, Italian, French, German, and Spanish languages. Some of the tools coming out are just so cool. So somebody like myself who's very linguistically challenged, I can now travel into worlds I would never think of, because I can have something translate my English back and forth readily, and I'm not stuck with a communication gap. So let's dive into what is a recurrent neural network. Recurrent neural network works on the principle of saving the output of a layer and feeding this back to the input in order to predict the output of the layer. Sounds a little confusing. When we start breaking it down, it'll make more sense. And usually we have a propagation forward neural network with the input layers, the hidden layers, the output layer. With the recurrent neural network, we turn that on its side. So here it is, and now our X comes up from the bottom into the hidden layers into Y, and they usually draw it very simplified, X to H, with C as a loop, A to Y, where A, B, and C are the perimeters. A lot of times you'll see this kind of drawing in here, digging closer and closer into the H and how it works. Going from left to right, you'll see that the C goes in, and then the X goes in. So the X is going upward bound, and C is going to the right. A is going out. And C is also going out. That's where it gets a little confusing. So here we have X in, C in, and then we have Y out and C out. And C is based on HT minus 1. So our value is based on the Y and the H value are connected to each other. They're not necessarily the same value because H can be its own thing. And usually we draw this, or we represent it as a function. H of T equals a function of C, where H of T minus 1, that's the last H output, and X of T going in. So it's the last output of H combined with the new input of X, where HT is the new state, FC is a function with the parameters C, that's a common way of denoting it, HT minus 1 is the old state coming out, and then X of T is an input vector at time of step T. Well, we need to cover types of recurrent neural networks. And so the first one is the most common one, which is a one-to-one single output. One-to-one neural network is usually known as a vanilla neural network, used for regular machine learning problems. Why? Because vanilla is usually considered kind of just a real basic flavor. But because it's very basic, a lot of times they'll call it the vanilla neural network, which is not the common term, but it is like kind of a slang term. People will know what you're talking about usually if you say that. Then we run one to many, so you have a single input and you might have multiple outputs. In this case, image captioning, as we looked at earlier, where we have not just looking at it as a dog, but a dog catching a ball in the air. And then you have many-to-one network, takes in a sequence of inputs. Examples, sentiment analysis, where a given sentence can be classified as expressing positive or negative sentiments. And we looked at that as we were discussing if it rains, look for a rainbow. So positive sentiment, where rain might be a negative sentiment if you were just adding up the words in there. And then, of course, if you're going to do a one-to-one, many-to-one, one-to-many, there's many-to-many networks, takes in a sequence of inputs and generates a sequence of outputs. Example, machine translation. So we have a lengthy sentence coming in English and then going out in all the different languages. Just a wonderful tool. Very complicated set of computations. If you're a translator, you realize just how difficult it is to translate into different languages. One of the biggest things you need to understand when we're working with this neural network is what's called the vanishing gradient problem. While training an RNN, your slope can be either too small or very large, and this makes training difficult. When the slope is too small, the problem is known as vanishing gradient. And you'll see here they have a nice image, loss of information through time. So if you're pushing not enough information forward, that information is lost, and then when you go to train it, you start losing the third word in the sentence or something like that, or it doesn't quite follow the full logic of what you're working on. Exploding gradient problem. Oh, this is one that runs into everybody. When you're working with this particular neural network, when the slope tends to grow exponentially instead of decaying, this problem is called exploding gradient. Issues in gradient problem: long training time, poor performance, bad accuracy. And I'll add one more in there. Your computer, if you're on a lower end computer testing out a model, will lock up and give you the memory error. Explaining gradient problem. Consider the following two examples to understand what should be the next word in the sequence. The person who took my bike and blank, a thief. The students who got into engineering with blank from Asia. And you can see in here we have our x value going in, we have the previous value going forward, and then you back propagate the error like you do with any neural network. And as we're looking for that missing word, maybe we'll have the person took my bike and blank was a thief. And the student who got into engineering with a blank were from Asia. Consider the following example: the person who took the bike, so we'll go back to the person who took the bike was blank a thief. In order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. So was a thief is singular. The student who got into engineering, well, in order to understand what would be the next word in the sequence, the RNN must memorize the previous context, whether the subject was singular noun or a plural noun. And so you can see here the students who got into engineering with blank were from Asia. It might be sometimes difficult for the error to back propagate to the beginning of the sequence to predict what should be the output. So when you run into the gradient problem, we need a solution. The solution to the gradient problem. First, we're going to look at exploding gradient, where we have three different solutions depending on what's going on. One is identity initialization. So the first thing we want to do is see if we can find a way to minimize the identities coming in instead of having it identify everything, just the important information we're looking at. Next is to truncate the back propagation. So instead of having whatever information it's sending to the next series, we can truncate what it's sending. We can lower that particular set of layers, make those smaller. And finally is the gradient clipping. So when we're training it, we can clip what that gradient looks like and narrow the training model that we're using. When you have a vanishing gradient, the option problem, we can take a look at weight initialization, very similar to the identity, but we're going to add more weights in there so it can identify different aspects of what's coming in better. Choosing the right activation function. That's huge. So we might be activating based on one thing and we need to limit that. We haven't talked too much about activation functions, so we'll look at that just minimally. There's a lot of choices out there. And then finally there's long short-term memory networks, the LSTMS. And we can make adjustments to that. So just like we can clip the gradient as it comes out, we can also expand on that. We can increase the memory network, the size of it, so it handles more information. And one of the most common problems in today's setup is what they call long-term dependencies. Suppose we try to predict the last word in the text. The clouds are in the, and you probably said sky. Here we do not need any further context. It's pretty clear that the last word is going to be sky. Suppose we try to predict the last word in the text. I have been staying in Spain for the last 10 years. I can speak fluent. Maybe you said Portuguese or French. No, you probably said Spanish. The word we predict will depend on the previous few words in context. Here we need the context of Spain to predict the last word in the text. It's possible that the gap between the relevant information and the point where it is needed to become very large. LSTMs help us solve this problem. So the LSTMS are a special kind of recurrent neural network capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. All recurrent neural networks have the form of a chain of repeating modules of neural network connections. In standard RNNs, this repeating module will have a very simple structure such as a single tangent H layer. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. LSTMS are a special kind of recurrent neural network, capable of learning long-term dependencies. Remembering information for long periods of time is their default behavior. LSTMSs also have a chain-like structure, but the repeating module has a different structure. Instead of having a single neural network layer, there are 4 interacting layers communicating in a very special way. As you can see, the deeper we dig into this, the more complicated the graphs get. In here, I want you to note that you have x at t minus 1 coming in, you have x at t coming in, and you have x at t plus 1. And you have h at t minus 1, and h at t coming in, and h at t plus 1 going out. And of course, on the other side is the output A. In the middle, we have our tangent H, but it occurs in 2 different places. So not only when we're computing the x at t plus 1 are we getting the tangent H from x at t, but we're also getting that value coming in from the x at t minus 1. So the short of it is as you look at these layers, not only does the propagate through the first layer goes into the second layer back into itself, but it's also going into the third layer. So now we're kind of stacking those up. And this can get very complicated as you grow that in size. It also grows in memory too, and in the amount of resources it takes. But it's a very powerful tool to help us address the problem of complicated, long sequential information coming in, like we were just looking at in the sentence. And when we're looking at our long short-term memory network, there's 3 steps of processing in the LSTMS that we look at. The first one is we want to forget irrelevant parts of the previous state. A lot of times, like, is, as, in, a, unless we're trying to look at whether it's a plural noun or not, they don't really play a huge part in the language, so we want to get rid of them. Then selectively update cell state values. So we only want to update the cell state values that reflect what we're working on. And finally, we want to only output certain parts of the cell state. So whatever's coming out, we want to limit what's going out too. And let's dig a little deeper into this. Let's just see what this really looks like. So step 1 decides how much of the past it should remember. First step in the LSTM is to decide which information to be omitted from the cell in that particular time step. It is decided by the sigmoid function. It looks at the previous state, h at t minus 1, and the current input, x at t, and computes the function. So you can see over here we have a function of t equals the sigmoid function of the weight of f, the h at t minus 1, and then x at t, plus, of course you have a bias in there with any of your neural networks, so we have a bias function. So f at t equals forget gate, decides which information to delete that is not important from the previous time step. Considering an LSTM is fed with the following inputs from the previous and present time step. Alice is good in physics. John, on the other hand, is good in chemistry. So, previous output. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our current input. So as we look at this, the first step is the forget gate realizes there might be a change in context after encountering the first full stop. Compares with the current input sentence of x at t. So we're looking at that full stop and then compares it with the input of the new sentence. The next sentence talks about John, so the information on Alice is deleted. Okay, that's important to know. So we have this input coming in, and if we're going to continue on with John, then that's going to be the primary information we're looking at. The position of the subject is vacated and is assigned to John. And so in this one, we've seen that we've weeded out a whole bunch of information, and we're only passing information on John, since that's now the new topic. So step 2 is then to decide how much should this unit add to the current state. In the second layer, there are 2 parts. One is the sigmoid function, and the other is the tangent h. In the sigmoid function, it decides which values to let through, 0 or 1. Tangent h function gives the weightage to the values which are passed, deciding their level of importance, -1 to 1. And you can see the 2 formulas that come up. The I of t equals the sigmoid of the weight of I, h at t minus 1, x at t plus the bias of I. And the c of t equals the tangent of h of the weight of c of h at t minus 1, x at t plus the bias of c. So our I of t equals the input gate, determines which information to let through based on its significance in the current time step. If this seems a little complicated, don't worry, because a lot of the programming is already done when we get to the case study. Understanding, though, that this is part of the program is important when you're trying to figure out what to set your settings at. You should also note when you're looking at this, it should have some semblance to your forward propagation neural networks, where we have a value assigned to a weight plus a bias. Very important steps in any of the neural network layers, whether we're propagating into the information from one to the next, or we're just doing a straightforward neural network propagation. Let's take a quick look at this, what it looks like from the human standpoint as I step out of my suit again. Consider the current input at x of t. John plays football well. He told me yesterday over the phone that he had served as a captain of his college football team. That's our input. Input gate analyzes the important information. John plays football and he was a captain of his college team is important. He told me over the phone yesterday is less important, hence it is forgotten. This process of adding some new information can be done via the input gate. Now this example is as a human form, and we'll look at training this stuff in just a minute. But as a human being, if I wanted to get this information from a conversation, maybe it's a Google Voice listening in on you or something like that, how do we weed out the information that he was talking to me on the phone yesterday? Well, I don't want to memorize that he talked to me on the phone yesterday, or maybe that is important. But in this case, it's not. I want to know that he was the captain of the football team. I want to know that he served. I want to know that John plays football and he was the captain of the college football team. Those are the two things that I want to take away as a human being. Again, we measure a lot of this from the human viewpoint, and that's also how we try to train them so we can understand these neural networks. Finally, we get to step 3, decides what part of the current cell state makes it to the output. The third step is to decide what will be our output. First, we run a sigmoid layer, which decides what parts of the cell state make it to the output. Then we put the cell state through the tangent h to push the values to be between -1 and 1, and multiply it by the output of the sigmoid gate. So when we talk about the output of t, we set that equal to the sigmoid of the weight of 0 of the h of t minus 1, back one step in time, by the x of t, plus of course the bias. The h of t equals the out of t times the tangent h of c of t. So our O of t equals the output gate, allows the passed in information to impact the output in the current time step. Let's consider the example to predicting the next word in the sentence. John played tremendously well against the opponent and won for his team. For his contributions, Brave blank was awarded player of the match. There could be a lot of choices for the empty space. Current input, Brave, is an adjective. Adjectives describe a noun. John could be the best output after Brave. Thumbs up for John, awarded player of the match. And if you were to pull just the nouns out of the sentence, team doesn't look right because that's not really the subject we're talking about. Contributions, brave contributions, or brave team, brave player, brave match. So you look at this and you can start to train this neural network. So it starts looking at it and goes, oh no, John is what we're talking about. So brave is an adjective. John's going to be the best output. And we give John a big thumbs up. And then of course we jump into my favorite part, the case study. Use case implementation of LSTM. Let's predict the prices of stocks using the LSTM network. Based on the stock price data between 2012 and 2016. We're going to try to predict the stock prices of 2017. And this will be a narrow set of data. We're not going to do the whole stock market. It turns out that the New York Stock Exchange generates roughly 3 terabytes of data per day. That's all the different trades up and down of all the different stocks going on. And each individual one second to second or nanosecond to nanosecond. But we're going to limit that to just some very basic fundamental information. So don't think you're going to get rich off this today. But at least you can give a step forward in how to start processing something like stock prices, a very valid use for machine learning in today's markets. Use case implementation of LSTM. Let's dive in. We're going to import our libraries. We're going to import the training set and get the scaling going. Now, if you watch any of our other tutorials, a lot of these pieces just start to look very familiar because it's a very similar setup. But let's take a look at that. And just a reminder, we're going to be using Anaconda, the Jupyter Notebook. So here I have my Anaconda Navigator. When we go under environments, I've actually set up a cross Python 3.6. I'm in Python 3.6. And nice thing about Anaconda, especially the newer version, I remember a year ago messing with Anaconda in different versions of Python in different environments. Anaconda now has a nice interface. And I have this installed both on a Ubuntu Linux machine and on Windows, so it works fine on there. And you can go in here and open a terminal window. And then in here, once you're in the terminal window, this is where you're going to start installing using pip to install your different modules and everything. Now we've already pre-installed them, so we don't need to do that in here. But if you don't have them installed in your particular environment, you'll need to do that. And of course, you don't need to use the Anaconda or the Jupyter. You can use whatever favorite Python IDE you like. I'm just a big fan of this because it keeps all my stuff separate. You can see on this machine I have specifically installed one for Keras, since we're going to be working with Keras under TensorFlow. When we go back to home, I've gone up here to Application, and that's the environment I've loaded on here, and then we'll click on the Launch Jupyter Notebook. Now, I've already, in my Jupyter Notebook, have set up a lot of stuff so that we're ready to go. Kind of like Martha Stewart's in the old cooking shows. We want to make sure we have all our tools for you so you're not waiting for them to load. And if we go up here to where it says New, you can see where you can create a new Python 3. That's what we did here underneath the setup, so it already has all the modules installed on it. And I'm actually renamed this. If you go under File, you can rename it. I'm calling it RNN Stock. And let's just take a look at, start diving into the code. Let's get into the exciting part. Now we've looked at the tool, and of course you might be using a different tool, which is fine. Let's start putting that code in there and seeing what those imports and uploading everything looks like. Now, the first half is kind of boring when we hit the Run button, because we're going to be importing NumPy as NP. That's the number Python, which is your NumPy array, and the matplot library, because we're going to do some plotting at the end, and our pandas for our data set. Our pandas is PD. And when I hit Run, it really doesn't do anything except for load those modules. Just a quick note, let me just do a quick draw here. Oops, Shift-Alt, there we go. You'll notice when we're doing this setup, if I was to divide this up, oops, I'm going to actually, let's overlap these, here we go. This first part that we're going to do is our data prep. A lot of prepping involved. In fact, depending on what your system is, since we're using Keras, I put an overlap here, but you'll find that almost maybe even half of the code we do is all about the data prep. And the reason I overlap this with Keras, let me just put that down because that's what we're working in, is because Keras has like their own preset stuff, so it's already pre-built in, which is really nice. So there's a couple steps a lot of times that are in the Keras setup. We'll take a look at that to see what comes up in our code as we go through and look at stock. And then the last part is to evaluate. And if you're working with shareholders or classroom, whatever it is you're working with, the evaluate is the next biggest piece. So the actual code here, Keras is a little bit more, but when you're working with some of the other packages, you might have like 3 lines. That might be it. All your stuff is in your pre-processing and your data. Since Keras is cutting edge and you load the individual layers, you'll see that there's a few more lines here and Keras is a little bit more robust. And then you spend a lot of times, like I said, with the evaluate, you want to have something you present to everybody else and say, hey, this is what I did, this is what it looks like. So let's go through those steps. This is like a kind of just general overview. And let's just take a look and see what the next set of code looks like. And in here we have a dataset train, and it's going to be read using the PD, or pandas.readCSV, and it's the Google stock price train.csv. And so under this we have training set equals dataset train.ilocation, and we've kind of sorted out part of that. So what's going on here? Let's just take a look at, let's look at the actual file and see what's going on there. Now if we look at this, ignore all the extra files on this, I already have a train and a test set where it's sorted out. This is important to notice because a lot of times we do that as part of the pre-processing of the data. We take 20% of the data out so we can test it, and then we train the rest of it. That's what we use to create our neural network. That way we can find out how good it is. But let's go ahead and just take a look and see what that looks like as far as the file itself. And I went ahead and just opened this up in a basic WordPad and text editor just so we can take a look at it. Certainly you can open up an Excel or any other kind of spreadsheet. And we note that this is a comma-separated variables. We have a date, open, high, low, close, volume. This is the standard stuff that we import into our stock, and we're the most basic set of information you can look at in stock. It's all free to download. In this case, we downloaded it from Google. That's why we call it the Google stock price. And it specifically is Google. This is the Google stock values from, as you can see here, we started off at 1/3/2012. So when we look at this first setup up here, we have a dataset train equals PD_CSV. And if you noticed on the original frame, let me just go back there, they had it set to home Ubuntu downloads Google stock price train. I went ahead and changed that because we're in the same file where I'm running the code. So I've saved this particular Python code, and I don't need to go through any special paths or have the full path on there. And then of course we want to take out certain values in here. And you're going to notice that we're using our data set, and we're now in pandas. So pandas, basically it looks like a spreadsheet. And in this case, we're going to do iLocation, which is going to get specific locations. The first value is going to show us that we're pulling all the rows in the data. And the second one is we're only going to look at columns 1 and 2. And if you remember here from our data, as we switch back on over, columns, we always start with 0, which is the date. And we're going to be looking at open and high, which would be 1 and 2. We'll just label that right there so you can see. Now, when you go back and do this, you certainly can extrapolate and do this on all the columns. But for the example, let's just limit a little bit here so that we can focus on just some key aspects of stock. And then we'll go up here and run the code. And again, I said the first half is very boring. Whenever you hit the run button, it doesn't do anything because we're still just loading the data and setting it up. Now that we've loaded our data, we want to go ahead and scale it. We want to do what they call feature scaling. And in here we're going to pull it up from the sklearn or the skKit pre-processing import min-max scaler. And when you look at this, you got to remember that biases in our data, we want to get rid of that. So if you have something that's like a really high value, let's just draw a quick graph. And I have something here like maybe the stock has a value, one stock has a value of 100 and another stock has a value of 5. You start to get a bias between different stocks. And so when we do this, we go ahead and say, okay, 100 is going to be the max, and 5 is going to be the min, and then everything else goes, and then we change this, so we just squish it down. I like the word squish. So it's between 1 and 0. So 100 equals 1, or 1 equals 100, and 0 equals 5. And you can just multiply. It's usually just a simple multiplication we're using. Multiplication. So it's going to be minus 5 and then 100 divided, or 95 divided by 1. So, or whatever value is divided by 95. And once we've actually created our scale, we've telling us going to be from 0 to 1. We want to take our training set and we're going to create a training set scaled. And we're going to use our scaler, SC, and we're going to fit. We're going to fit and transform the training set. So we can now use the SC, this particular object. We'll use it later on our testing set. Because remember, we have to also scale that when we go to test our model and see how it works. And we'll go ahead and click on the run. Again, it's not going to have any output yet because we're just setting up all the variables. Okay, so we paste the data in here, and we're going to create the data structure with the 60 time steps and output. First note, we're running 60 time steps, and that is where this value here also comes in. So the first thing we do is we create our xtrain and ytrain variables, and we set them to an empty Python array. Very important to remember what kind of array we're in and what we're working with. And then we're going to come in here, we're going to go for I in range 60 to 1258. There's our 60 time steps. And the reason we want to do this is as we're adding the data in, there's nothing below the 60. So if we're going to use 60 time steps, we have to start at point 60 because it includes everything underneath of it. Otherwise, you'll get a pointer error. And then we're going to take our xtrain and we're going to append training set scaled. This is the scaled value between 0 and 1. And then as I is equal to 60, this value is going to be 60 minus 60 is 0. So this actually is 0 to I. So it's going to be 0 to 60, 1 to 61. Let me just circle this part right here. 1 to 61, 2 to 62, and so on and so on. And if you remember, I said 0 to 60. That's incorrect because it does not count. Remember, it starts at 0, so this is a count of 60. So it's actually 59. Important to remember that as we're looking at this. And then the second part of this that we're looking at, so if you remember correctly, here we go. We go from 0 to 59 of I, and then we have a comma, a 0 right here. And so finally, we're just going to look at the open value. Now, I know we did put it in there for 1 to 2. If you remember correctly, it doesn't count the second one, so it's just the open value we're looking at, just open. And then finally, we have ytrain.append training set I to 0. And if you remember correctly, I2 or I comma 0. If you remember correctly, this is 0 to 59, so there's 60 values in it. So when we do I down here, this is number 60. So we're going to do this is we're creating an array, and we have 0 to 59. And over here we have number 60, which is going into the Y train. It's being appended on there. And then this just goes all the way up. So this is down here is 0 to 59, and we'll call it 60. Since that's the value over here, and it goes all the way up to 1258. That's where this value here comes in. That's the length of the data we're loading. So we've loaded two arrays. We've loaded one array that has, which is filled with arrays from 0 to 59, and we loaded one array which is just the value. And what we're looking at, you want to think about this as a time sequence. Here's my open. What's the next one in the series? So we're looking at the Google stock, and each time it opens, we want to know what the next one, 0 through 59, what's 60? 1 through 60, what's 61? 2 through 62, what's 62? And so on going up. And then once we've loaded those in our for loop, we go ahead and take xtrain and ytrain equals np.array xtrain.nparray ytrain. We're just converting this back into a numpy array. That way we can use all the cool tools that we get with numpy array, including reshaping. So if we take a look and see what's going on here, we're going to take our xtrain, we're going to reshape it. Wow, what the heck does reshape mean? That means we have an array, if you remember correctly, so many numbers by 60. That's how wide it is. And so when you do xtrain.shape, that gets one of the shapes. And you get xtrain.shape of 1 gets the other shape. And we're just making sure the data is formatted correctly. And so you use this to pull the fact that it's 60 by, in this case, where's that value? 60 by 1199, 1258 minus 60, 1199. And we're making sure that that is shaped correctly. So the data is grouped into 1199 by 60 different arrays. And then the 1 on the end just means at the end, because when you're dealing with shapes and NumPy, they look at this as layers. And so the end layer needs to be one value. That's like the leaf of a tree, where this is the branch, and then it branches out some more, and then you get the leaf. np.reshape comes from and using the existing shapes to form it. We'll go ahead and run this piece of code. Again, there's no real output. And then we'll import our different Keras modules that we need. So from Keras models, we're going to import the sequential model. We're dealing with sequential data. We have our dense layers. We have actually 3 layers we're going to bring in. Our dense, our LSTM, which is what we're focusing on, and our dropout. And we'll discuss these 3 layers more in just a moment. But you do need with the LSTM, you do need the dropout, and then the final layer will be the dense. But let's go ahead and run this, and that'll import our modules. And you'll see we get an error on here. And if you read it closer, it's not actually an error, it's a warning. What does this warning mean? These things come up all the time when you're working with such cutting-edge modules that are completely being updated all the time. We're not going to worry too much about the warning. All it's saying is that the H5PY module, which is part of Keras, is going to be updated at some point. And if you're running new stuff on Keras and you start updating your Keras system, you better make sure that your H5Pi is updated too, otherwise you're going to have an error later on. And you can actually just run an update on the H5Pi now if you wanted to. Not a big deal. We're not going to worry about that today. And I said we were going to jump in and start looking at what those layers mean. I meant that. And we're going to start off with initializing the RNN, and then we'll start adding those layers in. And you'll see that we have the LSTM and then the dropout. LSTM, then dropout. LSTM, then dropout. What the heck is that doing? So let's explore that. We'll start by initializing the RNN, regressor equals sequential, because we're using the sequential model. And we'll run that and load that up. And then we're going to start adding our LSTM layer and some dropout regularization. And right there should be the cue, dropout regularization. And if we go back here and remember our exploding gradient, well, that's what we're talking about. The dropout drops out unnecessary data, so we're not just shifting huge amounts of data through the network. So we go in here. Let's just go ahead and add this in. I'll go ahead and run this. And we had 3 of them. So let me go ahead and put all 3 of them in, and then we can go back over them. There's the second one, and let's put 1 more in. Oops, put that in, and we'll go ahead and put 2 more in. I said 1 more in, but it's actually 2 more in. And then let's add 1 more after that. And as you can see, each time I run these, they don't actually have an output. So let's take a closer look and see what's going on here. So we're going to add our first LSTM layer in here. We're going to have units 50. The units is the positive integer, and it's the dimensionality of the output space. This is what's going out into the next layer. So we might have 60 coming in, but we have 50 going out. We have a return sequence, because it is a sequence data, so we want to keep that true. And then you have to tell it what shape it's in. Well, we already know the shape by just going in here and looking at xtrain shape. So input shape equals the xtrain shape of 1, 1. It makes it real easy. You don't have to remember all the numbers that put in 60 or whatever else is in there. You just let it tell the regressor what model to use. And so we follow our STM with a dropout layer. Now, understanding the dropout layer is kind of exciting because one of the things that happens is we can overtrain our network. That means that our neural network will memorize such specific data that it has trouble predicting anything that's not in that specific realm. To fix for that, each time we run through the training mode, we're going to take 0.2 or 20% of our neurons and just turn them off. So we're only going to train on the other ones. And it's going to be random. That way, each time we pass through this, we don't overtrain. These nodes come back in the next training cycle. We randomly pick a different 20. And finally, I see a big difference as we go from the first to the second and third and fourth. The first thing is we don't have to input the shape. Because the shape's already, the output units is 50 here, the next step automatically knows this layer is putting out 50, and because it's the next layer, it automatically sets that and says, oh, 50 is coming out from our last layer. It's coming out, goes into the regressor, and of course we have our dropout. And that's what's coming into this one, and so on, and so on. And so the next 3 layers, we don't have to let it know what the shape is. It automatically understands that. And we're going to keep the units the same. We're still going to do 50 units. It's still a sequence coming through, 50 units and a sequence. Now, the next piece of code is what brings it all together. Let's go ahead and take a look at that. And we come in here, we put the output layer, the dense layer. And if you remember up here, we had the 3 layers. We had LSTM, dropout, and dense. Dense just says we're going to bring this all down into one output. Instead of putting out a sequence, we just want to know the answer at this point. And let's go ahead and run that. And so in here, you notice all we're doing is setting things up, one step at a time. So far, we've brought in our, way up here, we brought in our data, we brought in our different modules, we formatted the data for training it, we set it up, we have our xtrain and our ytrain, we have our source of data and the answers we know so far that we're going to put in there. We've reshaped that, we've come in and built our Keras, we've imported our different layers, and we have in here, if you look, we have 5 total layers. Now, Keras is a little different than a lot of other systems because a lot of other systems put this all in one line and do it automatic, but they don't give you the options of how those layers interface, and they don't give you the options of how the data comes in. Keras is cutting edge for this reason. So even though there's a lot of extra steps in building the model, this has a huge impact on the output and what we can do with these new models from Keras. So we brought in our dense, we have our full model put together, our regressor. So we need to go ahead and compile it, and then we're going to go ahead and fit the data. We're going to compile the pieces so they all come together, and then we're going to run our training data on there and actually recreate our regressor so it's ready to be used. So let's go ahead and compile that, and I can go ahead and run that. And if you've been looking at any of our other tutorials on neural networks, you'll see we're going to use the optimizer Atom. Atom is optimized for big data. There's a couple other optimizers out there beyond the scope of this tutorial, but certainly Atom will work pretty good for this. And loss equals mean squared value. So when we're training it, this is what we want to base the loss on. How bad is our error? Well, we're going to use the mean squared value for our error and the Atom optimizer for its differential equations. You don't have to know the math behind them, but certainly it helps to know what they're doing and where they fit into the bigger models. And then finally we're going to do our fit, fitting the RN into the training set. We have the regressor.fit, xtrain, ytrain, epochs, and batch size. So we know where this is. This is our data coming in. For the xtrain, our ytrain is the answer we're looking for of our data, our sequential input. Epochs is how many times we're going to go over the whole data set. We created a whole data set of xtrain. So this is each of those rows, which includes a time sequence of 60. And batch size, Another one of those things where Keras really shines is if you were pulling this, say, from a large file, instead of trying to load it all into RAM, it can now pick smaller batches up and load those indirectly. We're not worried about pulling them off a file today because this isn't big enough to cause the computer too much of a problem to run, not too straining on the resources. But as we run this, you can imagine what would happen if I was doing a lot more than just one column in one set of stock, in this case Google stock. Imagine if I was doing this across all the stocks and I had, instead of just the open, I had open, close, high, low, and you can actually find yourself with about 13 different variables times 60 because it's a time sequence. Suddenly you find yourself with a gig of memory you're loading into your RAM, which will just completely, if you're not on multiple computers or cluster, you're going to start running into resource problems. But for this, we don't have to worry about that. So let's go ahead and run this, and this will actually take a little bit on my computer because it's an older laptop. And give it a second to kick in there. There we go. Alright, so we have Epic. So this is going to tell me it's running the first run through all the data. And as it's going through, it's batching them in 32 pieces. So 32 lines each time. And there's 1198. I think I said 1199 earlier, but it's 1198. I was off by one. And each one of these is 13 seconds. So you can imagine this is roughly 20 to 30 minutes runtime on this computer. Like I said, it's an older laptop running at 0.9 gigahertz on a dual processor. And that's fine. What we'll do is I'll go ahead and stop, go get a drink of coffee, and come back, and let's see what happens at the end and where this takes us. And like any good cooking show, I've gotten my latte. I also had some other stuff running in the background, so you'll see these numbers jumped up to like 19 seconds, 15 seconds. But you can scroll through, and you can see we've run it through 100 steps, or 100 epics. So the question is, what does all this mean? One of the first things you'll notice is that our loss is over here. It kind of stopped at 0.0014, but you can see it kind of goes down until we hit about 0.014 3 times in a row. So we guessed our epic pretty close since our loss has remained the same on there. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And real stock price, dataset test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. And you see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open. Stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data. So to find out what we're looking at, we're going to go ahead and load up our test data, the test data that we didn't process yet. And real stock price, dataset test allocation. This is the same thing we did when we prepped the data in the first place. So let's go ahead and go through this code. And we can see we've labeled it Part 3, Making the Predictions and Visualizing the Results. So the first thing we need to do is go ahead and read the data in from our test CSV. And you see I've changed the path on it for my computer. And then we'll call it the real stock price. And again, we're doing just the one column here and the values from iLocation. So it's all the rows and just the values from that one location. That's the open. Stock open. And let's go ahead and run that. So that's loaded in there. And then let's go ahead and we have our inputs. We're going to create inputs here. And this should all look familiar because this is the same thing we did before. We're going to take our data set total. We're going to do a little pandas concat from the data set train. Now remember, the end of the data set train is part of the data going in. And let's just visualize that just a little bit. Here's our train data. Let me just put TR for train. And it went up to this value here. But each one of these values generated a bunch of columns. So it was 60 across, and this value here equals this one, and this value here equals this one, and this value here equals this one. And so we need these top 60 to go into our new data, because that's part of the next data, or it's actually the top 59. So that's what this first setup is over here, is where we're going in, we're doing the real stock price, and we're going to just take the data set test, and we're going to load that in, and then the real stock price is our data test location. So we're just looking at that first column, the open price. And then our data set total, we're going to take pandas and we're going to concat, and we're going to take our data set train for the open and our data set test open. And this is one way you can reference these columns. We've referenced them a couple different ways. We've referenced them up here with the 1, 2, but we know it's labeled as a panda set as open. So pandas is great that way. Lots of versatility there. And we'll go ahead and go back up here and run this. There we go. And you'll notice this is the same as what we did before. We have our open data set. We appended our two different, or concatenated our two data sets together. We have our inputs equals data set total length, data set total minus length of data set minus test minus 60 values. So we're going to run this over all of them. And you'll see why this works, because normally when you're running your test set versus your training set, you run them completely separate. But when we graph this, you'll see that we'll be looking at the part that we didn't train it with to see how well it graphs. And we have our inputs equals inputs dot reshape, so reshaping like we did before. We're transforming our inputs. So if you remember from the transform between 0 and 1. And finally we want to go ahead and take our X test, and we're going to create that X test, and for I in range 60 to 80. So here's our X test, and we're appending our inputs I to 60, which remember is 0 to 59, and I comma 0 on the other side. So it's just the first column, which is our open column. And once again, we take our X test, we convert it to a numpy array. We do the same reshape we did before, and then we get down to the final two lines, and here we have something new. Right here on these last two lines, let me just highlight those or mark them. Predicted stock price equals regressor.predicts X test. So we're predicting all the stock, including both the training and the testing model here. And then we want to take this prediction and we want to inverse the transform. So remember, we put them between 0 and 1. Well, that's not going to mean very much to me to look at a float number between 0 and 1. I want the dollar amounts. I want to know what the cash value is. And we'll go ahead and run this, and you'll see it runs much quicker than the training. That's what's so wonderful about these neural networks. Once you put them together, it takes just a second to run the same neural network that took us, what, a half hour to train? Head and plot the data. We're going to plot what we think it's going to be, and we're going to plot it against the real data, what the Google stock actually did. So let's go ahead and take a look at that in code. And let's pull this code up. So we have our PLT. That's our, if you remember from the very beginning, let me just go back up to the top. We have our matplotlibary.pyplot as PLT. That's where that comes in. And we come down here, we're going to plot, and let me get my drawing thing out again. We're going to go ahead, and PLT is basically kind of like an object. It's one of the things that always threw me when I'm doing graphs in Python, because I always think you have to create an object, and then it loads that class in there. Well, in this case, PLT is like a canvas you're putting stuff on. So if you've done HTML5, you'll have the canvas object. This is the canvas. So we're going to plot the real stock price. That's what it actually is. And we're going to give that color red, so it's going to be in bright red. We're going to label it real Google stock price. And then we're going to do our predicted stock, and we're going to do it in blue, and it's going to be labeled predicted. And we'll give it a title, because it's always nice to give a title to your graph, especially if you're going to present this to somebody, to your shareholders in the office. And the X label is going to be time, because it's a time series. And we didn't actually put the actual date and times on here, but that's fine. We just know they're incremented by time. And then, of course, the Y label is the actual stock price. PLT.legend tells us to build the legend on here so that the color red and real Google stock price show up on there. And then the plot shows us that actual graph. So let's go ahead and run this and see what that looks like. And you can see here we have a nice graph, and let's talk just a little bit about this graph before we wrap it up. Here's our legend I was telling you about. That's why we have the legend to show the prices. We have our title and everything. And you'll notice on the bottom we have a time sequence. We didn't put the actual time in here. Now we could have. We could have gone ahead and plotted the X, since we know what the dates are, and plotted this to dates. But we also know that it's only the last piece of data that we're looking at. So last piece of data, which ends somewhere probably around here on the graph, I think it's like about 20% of the data, probably less than that. We have the Google price, and the Google price has this little up jump and then down, and you'll see that the actual Google, instead of a turn down here, just didn't go up as high and didn't go down. So our prediction has the same pattern, but the overall value is pretty far off as far as stock. But then again, we're only looking at one column. We're only looking at the open price. We're not looking at how many volumes were traded. Like I was pointing out earlier, when we talk about stock, just right off the bat, there's 6 columns. There's open, high, low, close, volume. Then there's whether how many volume shares. Then there's the adjusted open, adjusted high, adjusted low, adjusted close. They have a special formula to predict exactly what it would really be worth based on the value of the stock. And then from there, there's all kinds of other stuff you can put in here. So we're only looking at one small aspect, the opening price of the stock. And as you can see here, we did a pretty good job. This curve follows the curve pretty well. It has like little jumps on it, bends. They don't quite match up. So this bend here does not quite match up with that bend there, but it's pretty darn close. We have the basic shape of it, and the prediction isn't too far off. And you can imagine that as we add more data in and look at different aspects in the specific domain of stock, we should be able to get a better representation each time we drill in deeper. Of course, this took a half hour for my computer to train, so you can imagine that if I was running it across all those different variables, it might take a little bit longer to train the data. Not so good for doing a quick tutorial like this.
And that brings us to the end of this live session on AI and machine learning full course.
Until next time, thank you, stay safe and keep learning to be future ready. Don't forget to subscribe to stay tuned for more from Simplilearn.